Unacademy. Let's crack it.
So dear students, before starting this particular session, the ones who are new to the channel, the ones who do not know me, a quick introduction about me. My name is Wassim and I'm your chemistry educator on this particular Unacademy NEET English channel, right? And this is all about me. You can check it out afterwards when you get the time. Yeah. And at the same time, the ones who have not liked this particular session, I would want every one of you to like this video, share this particular video with everyone, whosoever cannot afford the paid batches, whosoever cannot afford the quality education. Let them know that this is the channel which does not compromise on the content, right? Whatever we teach on the paid batches, same is the content which we give here on YouTube as well, right? So for that purpose, you need to like the video, share the video with everyone, right? Let all your friends get benefited out of these sessions. And at the same time, if you have not subscribed to the channel yet, I would want every one of you to subscribe to the channel so that you remain updated about all the sessions which we take live on this Unacademy NEET English channel. Yeah? Perfect? All right, people. Just give me a second. Just give me a second. All right. So let's get going then. Let's get started with the chapter. Again, I'm telling you, I'll be starting exactly from the basics. And whatever points I'll be noting down on the screen, I would want all of you to take a note of every single thing, because every single thing is equally important, my dear student. Right? And we'll be exactly starting from the basics. So first of all, if I talk about equilibrium, how do we define equilibrium basically? My dear students, as per thermodynamics point of view is concerned, equilibrium is defined as that state of the system. Equilibrium is defined as that state of the system at which entropy attains its maximum value and Gibbs free energy attains its minimum value. This is the definition of equilibrium as per thermodynamics point of view. Equilibrium is nothing, it is just the state of the system. It is one of the state of the system at which entropy of the system attains the maximum value, Gibbs free energy attains the minimum value. And you must be knowing now, as per thermodynamics is concerned, whenever entropy attains its maximum value and Gibbs free energy attains its minimum value, that state of the system is considered to be the most stable state of the system. So what is equilibrium? What is equilibrium? I would say equilibrium is basically a state of the system at which entropy of the system becomes maximum, Gibbs free energy of the system becomes minimum, and as far as thermodynamics is concerned, that state of the system where entropy is maximum, Gibbs free energy is minimum, that is considered to be the most stable state of the system. That is why your equilibrium, that is considered to be the most stable state, right? This is the general definition as per thermodynamics is concerned, right? Perfect. This is the general definition as far as the thermodynamics point of view is concerned. Now let's go into the details of this equilibrium and let's get to know one by one what this equilibrium is all about. Yeah. Now, my dear students, try to understand what exactly I'm going to say. Try to understand what exactly I am going to say. Okay? Try to understand everything. Now I'm going to start the chapter basically. All right. So first thing, what exactly we are going to do? We are going to talk about the equilibrium as per chemical reactions are concerned. We are going to discuss the equilibrium of chemical reactions. Okay? The first point which I would want every one of you to remember. Equilibrium in chemical reactions, how do we define it? I would say it is the state of the system. It is the state of the system. It is the state of the system at which all the measurable properties, all the measurable properties of the system like moles, concentration, pressure, temperature, color, etc. attains a fixed value. Attains a fixed value. Or you can say becomes constant. Becomes constant. What this particular point exactly means? My dear students, it's again very simple. See, first of all, when do we say that equilibrium has attained in a chemical reaction? When do we say that equilibrium has attained in a chemical reaction? What is equilibrium, first of all? It is the state of the system. So when do we say that equilibrium state has attained in a chemical reaction? My dear students, when all the measurable properties like moles, like pressure, like concentration, when they become fixed. What does that mean? You will see one particular point in a chemical reaction. You will see one particular stage in a chemical reaction at which all the moles of reactants and products, they will become fixed. They won't change at all. You will see a particular state in a chemical reaction at which the concentration of all the reactants and products, they will become fixed. They won't change at all. Right? You will see a particular state in a chemical reaction at which the pressure of reactants and products, it becomes fixed, it becomes constant, it does not change at all. That particular state in a chemical reaction, at which moles of reactants and products, they become fixed, they become constant. Concentration of reactants and products, they become constant. Pressure of reactants products, they become constant. That particular state is something we call as equilibrium state in a chemical reaction. Right? This is something which we are going to study in detail in some time. Right? So first of all, I would want you guys to remember this particular statement. It's very, very, very important. Right? The detailed explanation of this particular statement you will get in some time. Just you take a note of things first. So what is equilibrium in a reaction? It is that state in a chemical reaction at which the moles of reactants and products, they become fixed. They do not change at all. Concentration reactant products, it becomes fixed. It becomes constant. It does not change at all. Pressure of reactants products, it becomes fixed. It does not change at all. And that particular state is something which I'll be calling as equilibrium state in a chemical reaction. Point number one. My dear students, point number two. Equilibrium is always attained in reversible reactions. Equilibrium is attained always in a reversible reaction. Now the point is, what are reversible reactions? Just the quick idea. For example, I'm going to denote a reaction like this. A gives B and B gives A. A gives B, B gives A. That particular reaction which can proceed in both the directions, forward as well as backward. That particular reaction which can proceed in both the directions, forward as well as backward. That's something which you call as a reversible reaction. And equilibrium is always attained only in case of reversible reactions. In irreversible reactions, equilibrium cannot be attained, right? So equilibrium is what? It's the state of the system, right? It's the state basically, which is attained only in reversible reactions. And the reversible reactions are the ones which proceed in both the directions, forward as well as backward. This is second point. My dear students, the third point. The third point. Understand properly what exactly I'm trying to say. I'm writing over here as the reaction proceeds. As the reaction proceeds. As the reaction proceeds. The concentration of reactants, it decreases. And the concentration of products, it increases. As the reaction proceeds, the concentration of reactant decreases with time. And the concentration of products, it increases with time. Now you must be thinking, what is meant by the term concentration? Concentration is nothing. It is represented by square brackets, and concentration is defined as number of moles per unit volume of the system in liters. What does it mean? Try to understand what I'm going to say. For example, I have got a reaction like this. A gives B. Let's assume this is a reaction. Okay. Now this particular reaction has to take place basically. This reaction has to happen. I'm assuming that this particular reaction will be taking place in a container whose volume is V liters, right? So what is V liters? It is the volume of the container in which this particular reaction has to proceed, in which this particular reaction has to occur, right? Now guys, if I say time t is equal to 0, time t is equal to 0 means the reaction has not started yet. Reaction has not started yet. What does that mean? That means the reactant has not started getting converted into product. The reactant has not started getting converted into the product. I'm assuming that at time t is equal to 0, I have got 10 moles of reactant with me. Since the reaction has not started, so product formation at this particular point will be 0. Now, my dear students, what is going to happen? When the reaction will proceed, what is going to happen? When the reaction proceeds, I'll say the number of moles of reactants will keep on decreasing with time. And number of moles of products will keep on increasing with time, right? So number of moles of reactants will keep on decreasing with time, and number of moles of products will keep on increasing with time. So what I got to know? I got to know with time, when the reaction starts, moles of reactants keep on decreasing, and moles of products in a reaction, it keeps on increasing, right? Concentration is number of moles per unit volume. If I write concentration of reactant, what does that mean? That means number of moles of reactant divided by volume of the system in liters. If I write concentration of products, which means number of moles of products divided by volume of system in liters. Now you are going to tell me one thing. When the reaction proceeds, are the moles of reactant increasing or decreasing? When the reaction starts, the number of moles of reactants, they decrease with time. And if number of moles of reactant decrease with time, that means concentration of reactants, it decreases with time. Similarly, number of moles of products in a reaction, it increases with time. Therefore, concentration of products, it again increases with time. So my dear students, this is a very important statement and simple, basic at the same time. When the reaction starts, moles of reactant decrease with time. Concentration of reactants decrease with time. Moles of products increases with time. Concentration of products increases with time as well, right? Let me note down this particular statement in terms of graph. Let me note down this particular statement in terms of graph. Have a look exactly what I'm going to say. My dear students, I'm going to plot a graph. The graph is between concentration versus time. The graph is between concentration versus time, right? So first of all, if I need to plot a graph between concentration versus time for reactants, how exactly we are going to do that? My dear students, we know with time, concentration of reactants, it decreases with time, right? So this is the graph which is valid for what? It is the graph which is valid for the reactant. Similarly, I want you guys to plot a graph again between concentration versus time, but for products. And you know, for products, with time, the concentration of product increase with time, right? The concentration of product increase with time. Yeah. At time t is equal to 0, number of moles of product are 0. So when the reaction starts with time, the moles of product increases. That means the concentration of product increase as well. So this is how your concentration of products increase with time. So first of all, I would want you guys to remember these two basic graphs. With time, the concentration of reactant keeps on decreasing. With time, the concentration of products keeps on increasing, right? One basic thing. Now guys, try to understand one more important point. First of all, there is one law which we have to discuss here in this chapter only after some time. But I would want its basic thing over here as well. After some time, I'm going to discuss that law in detail, but I would want one of its points. And what is that point? There is a law called as law of mass action. As far as law of mass action is concerned, we can say rate of reaction, it is directly proportional to concentration of reactants. It is basically active mass of reactants, but since we have not discussed active mass yet, so I'm directly writing rate of reaction is directly proportional to active mass of reactants or concentration of reactants. What does it mean? Why do I need this particular term? Try to understand what I'm going to say. For example, imagine that you have got a reaction like this. A gives B. So first of all, it is a reversible reaction. This reaction can proceed in both the directions, forward as well as backward, right? It can proceed in both the directions. Now, my dear students, try to understand one simple thing. Let's assume that at time t is equal to 0. Let's assume that, or let's do one thing. Tell me one thing. whether it's actually a single reaction or these are actually the two reactions. If you ask me, I would say these are actually the two reactions. The first reaction is the forward reaction in which A gives B. The second reaction is the backward reaction in which B gives A. So this is my forward reaction and this has to be my backward reaction. This has to be my backward reaction. Perfect. My dear students, for the forward reaction, the reactant is A. And for the backward reaction, the reactant is B. Right? So, as per law of mass action is concerned, I would say rate of forward reaction is directly proportional to concentration of reactant. Which is the reactant in the forward reaction? It's A, right? Similarly, I can say as per law of mass action, rate of backward reaction is directly proportional to concentration of this B, which is the reactant of the backward reaction. Perfect. I can say something like this. Rate of forward reaction is directly proportional to concentration of reactant here. Rate of backward reaction is directly proportional to concentration of reactant here. And B is the reactant in this particular case. Perfect. Now you tell me one thing. Few minutes back I told you. If you talk about this particular reaction, in this general reaction, this A is your reactant, B is your product. When the reaction starts, the concentration of this A will start to decrease. And when the reaction starts, the concentration of this B, it will start to increase. Right? And my dear students, if the concentration of A decreases with time, that means the rate of forward reaction, it decreases with time. If the concentration of B increases with time, that means the rate of backward reaction increases with time. So can I say something like this? When the reaction starts, rate of forward reaction, the rate with which forward reaction moves, it decreases with time. And rate of backward reaction increases with time. So can I say a stage will come at which rate of forward and backward reaction becomes equal? And that particular stage in a chemical reaction at which rate of forward and rate of backward reaction becomes equal, you call that particular stage in a chemical reaction as the equilibrium stage. So I would say when rate of forward and backward reaction becomes equal, we would say at this particular point of time, we can say equilibrium is established in the reaction. So in the reaction, a state has reached at which the system would have attained its maximum entropy and Gibbs free energy of the system would have attained its minimum value. So this particular state of the system will be considered as the most stable state of the system, right? That is the reason why every reversible reaction wants to attain equilibrium as soon as possible, because equilibrium is the most stable state of the system. And every reversible reaction would want to go towards stability as soon as possible, right? Let me know once in the chats if this particular point is clear to everyone. Quickly. So, equilibrium is that state of the system at which rate of forward and rate of backward reaction becomes equal. Yeah? Quickly, my dear students. If you would want to do one simple thing, if you would want to represent all these things graphically, you can do that as well. I told you at equilibrium, rate of forward and rate of backward reaction becomes equal, right? Rate of forward and rate of backward reaction becomes equal. Why is that? Because with time, when the reaction starts, rate of forward reaction decreases with time and rate of backward reaction that increases with time. So if this particular statement you will have to represent with the help of graph, you can do that as well with the help of graph. If you want to plot a graph between rate of reaction versus time, you know, as I told you a few minutes back, rate of forward reaction that decrease with time, right? And I can say rate of backward reaction, it increases with time. And this is the point. After which rate of forward and rate of backward reaction becomes equal. So I would say this point represents the time when we say equilibrium has established in the reaction. So after this particular point, rate of forward and rate of backward reaction, it has become equal. So I would say at this particular point of time, equilibrium has attained in the reaction. I hope this particular point is clear to everyone, right? This particular graph, it is the rate of forward reaction. And this one, it is the rate of backward reaction. Rate of forward reaction decreases with time and rate of backward reaction increases with time. Therefore, a stage will come when rate of forward and backward reaction becomes equal, and that particular state in the system is what we call as equilibrium state. It's what I call as equilibrium state, right? Isn't it simple, my dear students? Isn't it simple? Isn't it simple? Say yes or no in the chat quickly. Yeah? I hope this particular statement is clear, right? At the same time, my dear students, let me tell you one more thing about equilibrium. I would say equilibrium is always dynamic in nature. Equilibrium is always what? It's always dynamic in nature. That means when equilibrium is attained in the reaction never stops because the rate of forward and backward reaction is equal. The rate with which forward reaction moves, with the similar rate, backward reaction also moves. So it keeps on going. The rate with which forward reaction goes, in the similar way, backward reaction also goes. The rate with which forward reaction moves, in the similar way, rate of backward reaction is the same. Perfect. So the reaction keeps on going continuously. Forward and backward reaction, they keeps on taking place at equal rates. That's why once equilibrium is established in the reaction never stops. It's always dynamic. Forward, backward, continuous rate will keep on moving. Yeah. At the same time, one more important point about equilibrium. What is that going to be? Try to understand. Try to understand. Any reaction, any reversible reaction involving gaseous reactant or product. Involving gaseous reactant or product can attain equilibrium only in a closed container, only in a closed vessel, closed container. Why is that? Try to understand this particular point as well. Try to understand this particular point as well. For example, my dear students, I'm taking one container. This is, for example, a container which is open on one side. The container is open on one side. Now, for example, over here, we have got calcium carbonate. Calcium carbonate solid, right? You know, when calcium carbonate is heated, it gets converted into calcium oxide. And with this, you'll be getting carbon dioxide gas. Perfect. So, my dear students, if the vessel is open on one side, I have introduced calcium carbonate in the container, right? After introducing calcium carbonate in the container, I'm going to heat it up. When I'll heat it up, it will start getting converted into calcium oxide. And with calcium oxide, you'll be getting carbon dioxide gas as well. So a gas is getting produced here. When calcium carbonate is heated, gas is getting produced. Where would that gas go? Since the container is open on one side, whatever carbon dioxide is produced, that will come out of the container. And if carbon dioxide will come out of the container, there will be no carbon dioxide left in the container. If there is no carbon dioxide left in the container, is it possible for the backward reaction to happen? The backward reaction won't happen. And if the backward reaction won't happen, that means the reaction cannot be reversible. And if the reaction won't be reversible, what will happen? Equilibrium cannot be established in the reaction. Yeah? So for any reaction which involves minimum one gaseous reactant or product, equilibrium will be established only in that particular reaction in a closed container. Yeah? I hope this is super clear to everyone. Say yes or no in the chats quickly. Say yes or no in the chats quickly. Say yes or no in the chats quickly. Try to understand one more important point, which is the most important point related to equilibrium, right? Yeah, which is the most important point related to equilibrium. See guys, this is the most important point. What is that? I would say at equilibrium, what happens? Number of moles of reactant and number of moles of product, they become constant. They do not change at all. Concentration of reactant and concentration of product, they also attain a fixed value. That means they become constant. Partial pressure of reactant and partial pressure of product. Partial pressure of reactant and product, it also becomes fixed. It also becomes constant. Now what it means exactly, what these things mean. Try to understand these three important points, which are very, very, very important. So at equilibrium, the moles of reactant and products, they do not change after that. Once equilibrium is established in the reaction, Once equilibrium is established in the reaction, after that, the moles of reactants and products won't change. The concentration of reactant product, it won't change. The partial pressure of reactant and product, it won't change. Why is that? Let's try to understand. For example, I've got a reaction A in equilibrium with B. This is a reaction, a reversible reaction. Let's say, for example, at time t is equal to 0, I have got 10 moles of reactant with me. So that means there will be 0 moles of product present in the container in which this reaction has to happen. I'm assuming that the container in which reaction has to take place, volume of that container is, for example, 1 liter. Just to make you understand. Right? Now, my dear students, try to understand one thing. At time t is equal to 0, we have got 10 moles of reactant. We have got 0 moles of products in the container in which reaction has to take place. Let's assume that when the reaction is, for example, 20% completed, equilibrium is established in the reaction. When the reaction is 20% completed, let's assume that equilibrium is established in the reaction. Now you tell me one thing. What does this 20% completion mean? It means that 20% of the reactant would have got converted into the product, right? You tell me, how many moles of reactant we had? We had 10 moles of reactant. Out of 10 moles, 20% of 10. 20% of 10 means 2 moles, right? So out of 10 moles of reactants, I would say 2 moles of reactant would have got converted into products. Now you tell me, if out of 10 moles of reactants, if 2 moles of reactant got converted into product, let's say I'll be left with 8 moles of reactant at equilibrium. Similarly, how many moles of product would have got formed? I would say 2 moles of product would have got formed. Right? I would say 2 moles of product would have got formed. Perfect. So my dear students, try to understand one more important thing. It's important. At time t is equal to 0, I'm assuming that we have got 10 moles of reactant, 0 moles of product. I'm assuming when 20% of reaction gets completed, equilibrium is established in the reaction. 20% completion means that 20% of reactant has got converted into products. So initially I had 10 moles of reactant. 20% of 10 moles has got converted into product. 20% of 10 is 2, right? So out of 10 moles, 2 moles of reactant has got converted into product. So I'll be left with 8 moles of reactant, and I would say 2 moles of product would have got formed as well. Now what has established in the reaction? Equilibrium. If equilibrium is established in the reaction, I would say now the rate of forward and backward reaction would have got equal. What does that mean? That means if 1 mole of reactant will start getting converted into product, at the same time 1 mole of product will come into reactant side. If 1 mole of reactant gets converted into product, at the same time 1 mole of product will get converted into reactant. What does that mean? That means the number of moles of reactant and product will not change now. The number of moles of reactant and product, they have become constant. They are not going to change now. That's what I told you. When equilibrium is established in the reaction, the moles of reactant and product are not going to change. Right? Now, my dear students, what is concentration? Concentration is number of moles divided by volume, right? So if I ask you, at equilibrium, how many moles of A we have? 8. So if I ask you, at equilibrium, what will be the concentration of A? At equilibrium, what will be the concentration of A? You will say moles of A divided by volume. Moles of A at equilibrium is 8, volume is 1. So the concentration of reactant at equilibrium is 8 molar. The concentration of product at equilibrium is 2 molar. Now you tell me, since equilibrium is established in the reaction, will the concentration of reactant change now? The concentration of reactant and product is not going to change because the moles of reactant and product are not going to change. As simple as that, right? That's why I told you, when equilibrium is established in the reaction, the moles of reactant product, they become fixed. The concentration of reactant product, they become fixed. In the similar way, the partial pressure, the pressure of reactant product, it becomes fixed as well. So one thing which I would want you guys to analyze here. What do you think? At equilibrium, whose concentration is more? I would say concentration of reactant at equilibrium is greater than that of concentration of product at equilibrium in this particular scenario. So if you will have to represent it with the help of graph, you can do that as well. Concentration versus time. concentration versus time. What is happening to the concentration of reactant with time? The concentration of reactant is decreasing. The concentration of product is increasing, right? The concentration of reactant is decreasing with time. The concentration of reactant is decreasing with time. So concentration of reactant decreases and attains a fixed value, does not change afterwards. Similarly, concentration of product, it increases for some time and then attains a fixed value, right? So can I say this is the time after which, the concentration of reactant as well as product has attained a fixed value. It does not change at all. So this particular time represents what? It represents equilibrium. Now you can see at equilibrium, what is the concentration of reactant? This point represents concentration of reactant at equilibrium, and this particular point, it represents concentration of product at equilibrium. Now you try to understand, is the concentration of reactant at equilibrium more or concentration of product? I would say concentration of reactant is greater than that of concentration of product at equilibrium. So this is one of the scenarios which clearly shows you the equilibrium basically. I hope this is clear to everyone. Yeah? Right, my dear students? This was one case. This was case number 1. Now looking at case number 2. Let's try to understand equilibrium a bit more in detail with case number 2. This was case number 1. Now let's have a look on case number 2. My dear students, for example, I'm again going to take the same reaction. A gives B. This is the reaction. Volume of the vessel in which reaction takes place, that's 1 liter. For example, initially at time t is equal to 0, I have got 10 moles of reactant. There will be 0 moles of product. I'm assuming that when 50% of reaction is completed, equilibrium is established in the reaction. So when 50% of reaction is completed, what does that mean? That means out of 10 moles of reactant, 50% of 10 would have got converted into product, right? So 50% of 10 means 5. So out of 10 moles of A, 5 moles of A would have got converted into product. So I'll be left with 5 moles of reactant. I had 10 moles. Out of 10, 5 moles are getting converted. So I'll be left with 5 moles of A. So if I ask you how many moles of B would have got formed, 5 moles of B would have got formed as well. Now I'm assuming that equilibrium is established when 50% reaction is completed, right? When 50% reaction is completed, I would say equilibrium is established. And my dear students, when equilibrium is established in the reaction, I would say the rate of forward and backward reaction would have got equalized, right? And if the rate of forward and backward reaction would have got equal, that means now if 1 mole of reactant will start getting converted into product, at the same time, 1 mole of product will start getting converted into reactant as well. So what will happen? Will the moles of reactant and product change now? No. The moles of reactant product, they have attained a fixed value. Right? They have attained a fixed value. Similarly, the concentration of reactant and product, they have attained a fixed value at equilibrium. Perfect. And this is one clear example at which you can say the moles of reactant and product at equilibrium, they are same. The concentration of reactant and product at equilibrium, it is same. What is the condition? The condition is the moles of reactant product, they should be constant, right? In this case, the moles of reactant, they were constant, but they were not same, right? Over here, they are constant, but at the same time, they are same as well. So that is one more case over here. So if I want you guys to represent it with the help of graph, concentration versus time. So you can say concentration of reactant decrease with time, then attains a fixed value. Concentration of product increase with time, then attains a fixed value, right? And my dear students, this is the time after which the concentration of reactant has attained a fixed value. So I would say this point represents equilibrium, right? And this is the graph which shows that the concentration of reactant and product at equilibrium is same. Yeah. So both these graphs, they do represent equilibrium. What is the condition for equilibrium? The concentration of reactant products, they should be fixed. They should be constant, right? They can be constant. They can be same as well as in this case. Over here, the concentration of reactant product was not same, but they were fixed, right? And the condition is they should be fixed. So this represents equilibrium. Perfect. Even this represents equilibrium, right? Is this clear to everyone? Let me know once in the chats. Then I'll make you understand the third case. Let me know quickly in the chats if all these things are clear till here. Then I'll be showing you the third case. The third case for equilibrium. For example, I've got a reaction like this. A gives B. I'm assuming that 80% reaction when completed, equilibrium is established. Okay. So for example, time t is equal to 0. I've got 10 moles of A in the container. This will be 0. Now at equilibrium, 80% of reactant has got converted into product. What is 80% of 10? That is 8. So out of 10 moles of reactant, 8 moles would have got converted into products. So I'll be left with 2 moles of reactants at equilibrium. And 8 moles of products would have got formed. Now I'm assuming equilibrium is established. That means the rate with which forward reaction moves. With the same rate, backward reaction moves. If 1 mole of reactant starts getting converted into product, at the same time, 1 mole of product will start getting converted into reactant. With that, the number of moles of reactant and product won't change, right? Similarly, the concentration of reactant and product won't change. Perfect. And this is the scenario in which you can see, no doubt, the concentrations have become fixed, but the concentration of reactant at equilibrium is less than that of concentration of product at equilibrium. As you can see the values, you can show it with the help of graph as well. This is, for example, concentration. This is, for example, time. And you know, concentration of reactant decrease with time, attains a fixed value. Concentration of product increase with time, attains a fixed value. This is reactant, this is product. And this is the point after which the concentration of reactant product does not change. So this is the point which represents equilibrium basically. And this graph represents that equilibrium in which the concentration of reactant is less than that of concentration of product at equilibrium. So quickly in the charts, if this is clear. So my dear students, there are 3 graphs. There are 3 graphs which are correctly representing equilibrium. This is representing equilibrium. Absolutely. Even this is representing. The other one is also representing. Perfect. Right? So when you want to show equilibrium on the graph for concentration versus time, there are 3 graphs which represents equilibrium, and all the 3 graphs which I showed you. When you want to show equilibrium on rate versus time curve, there is only one graph. Rate of forward backward reaction, that should become equal. So my dear students, I just want you guys to remember one thing. When you define equilibrium in terms of concentration, when you define equilibrium in terms of concentration of reactant and product, the condition is the concentration of reactant product should become constant. It can be same as well, right? But when you define equilibrium in terms of rate, the condition is the rate of forward backward reaction should be equal, should be same. Over here the term is constant, over here the term is same, equal, right? Is this clear to every single guy? Quickly in the chats. I'm going to give you one simple question over here. Tell me how many curves represent equilibrium over here. This is rate, this is time. Rate versus time. Tell me how many graphs represent equilibrium over here. This is concentration, this is time. Again, this is concentration, this is time. Again, this is rate, this is time. Tell me how many graphs correctly represent equilibrium out of the 4 graphs. I'm just waiting for your answers. From this question, I'll get to know whether you got the concept of equilibrium or not. Quickly. See, as per concentration of reactant product should become fixed. So this represents equilibrium. Concentration of reactant product should become fixed. It can be equal as well. This represents, right? As per rate of forward reaction and backward reaction should become equalized. This represents equilibrium. But over here, if you see, this point is the rate of forward reaction. This point represents rate of backward reaction. So is the rate of forward and backward reaction same? No, it's not same. So the first graph does not represent equilibrium, right? Right, people? Quickly. Is this clear to everyone? Is every single thing clear till here? Say yes or no in the chats. Say yes or no in the chats. Say yes or no in the chats. Quickly. Quickly, guys, everyone. Yes, done and dusted? Perfect. Now, my dear students, there is one law, which is what you call as the law of mass action. This law of mass action, let me tell you, it's a complete theoretical concept. It is a complete theoretical concept. It does not have any experimental background. It does not have any experimental background. Point number one. Point number two, this law of mass action was given by two scientists. This law of mass action was given by two scientists, Gullberg and Lave, right? Now the point is, what this law of mass action states. As far as its statement is concerned, as per the law of mass action is concerned, rate of reaction is directly proportional to the product of active masses of reactants raised to the powers of their stoichiometric coefficient. Now, what does that mean? Have a look what that means. For example, you have got a reaction like this. A plus B, it gives C plus D. This is one general balanced chemical equation, right? Let's say this is N1, or just a second. Let's say we have got a balanced chemical equation in this format, N1A plus N2B. For example, it gives N3C, and with this, you get N4D as well. This is a balanced chemical equation in which N1, N2, N3, N4, these are the stoichiometric coefficients of reactants and products. Now, what law of mass action states that? Law of mass action states that rate of reaction is directly proportional. Rate of reaction, the speed with which reaction moves, that's rate. Rate of reaction, that's directly proportional to the product of active masses of reactants. Reactant here is A and B, so I'll write active mass of A multiplied by active mass of B. Product of active masses of reactants raised to the powers of their stoichiometric coefficients. What is the stoichiometric coefficient of A? That's N1. So this is active mass of A raised per N1. This active mass of B raised per N2. Right? Now you must be thinking what active masses are. You'll get the idea in some time. But first, try to remember this particular statement. As per law of mass action is concerned, rate of reaction, the speed with which reaction moves, is directly proportional to the product of active masses of reactants raised to the powers of their stoichiometric coefficients. Right? Now, my dear students, before talking about the active masses in detail, let me tell you one more important thing. Try to understand what exactly I'm going to say. Try to understand what exactly I'm going to say. Have a look, people. For example, I've got a reaction like this. N1A plus N2B. I'm showing the reversible sign in the middle. It is N3C plus N4D. This is a balanced chemical equation. Now, if I ask you whether this is only one reaction or these are actually two reactions. These are actually two reactions. Forward, backward. Right? Forward, backward. Right, people? These are actually two reactions. One is forward and one is backward. Now, people, if these are two reactions, one forward, one backward, let's say this is your forward reaction. And what is my backward reaction then? The backward reaction is going to be this. N3C plus N4D, it gives N1A plus N2B. This is my forward reaction and this is my backward reaction. Now, as per the law of mass action is concerned, rate of reaction. Over here, I'll write rate of forward reaction. Directly proportional to product of active masses of reactants. So, active mass of A multiplied by active mass of B raised to the powers their stoichiometric coefficient. This N1, this N2. So, active mass of A raised per N1, active mass of B raised per N2. Right? Similarly, rate of backward reaction. It is directly proportional to product of active masses of reactants. Here, reactants are C and D. So, it's going to be active mass of C raised per N3, active mass of D raised per N4. Perfect. Now, if you remove the proportionality sign, it's going to be Kf, which is a constant, active mass of A raised per N1, active mass of B raised per N2. And over here, rate of backward reaction is equal to, the constant here is Kb, this is active mass of C raised per N3, active mass of D raised per N4. Now, my dear students, just tell me one simple thing. We got two constants basically. This Rf, first of all, what do I call this? This is called as the rate of forward reaction. This is called as the rate of forward reaction. What is this Kf? This Kf is called as the rate constant. This is called as the rate constant of forward reaction. rate constant of forward reaction. Similarly, what is this RB? This is the rate of backward reaction. This is the rate of backward reaction. And what is this KB over here? This is the rate constant of backward reaction. This is the rate constant for backward reaction. Now, my dear students, try to understand few things. I told you a few minutes back, when the reaction starts, the rate of forward reaction decreases and rate of backward reaction increases with time. And there comes a time when rate of forward and backward reaction becomes equal. That stage in a reaction is what we call as equilibrium. So we know at equilibrium, rate of forward and backward reaction becomes equal. If rate of forward and backward reaction becomes equal, I would say Kf multiplied by active mass of A raised by N1, active mass of B raised by N2, it becomes equal to Kb, active mass of C raised by N3 and active mass of D raised by N4. Correct till here? Absolutely correct. Now, dear students, try to understand. This Kf I'm writing as such, divided by this Kb I'm taking into the denominator. Kf divided by Kb is equal to, this is active mass of C raised by N3, active mass of D raised by N4 divided by active mass of A raised by N1 and active mass of B raised by N2. Right? What is Kf? Rate constant of forward reaction. What is Kb? Rate constant of backward reaction. So this is constant, this is constant. Division of two constants, it becomes one more constant, which is what you call as equilibrium constant. And equilibrium constant is nothing. It is represented by Keq. It is represented by Keq. As simple as that. So, my dear students, how do you represent equilibrium constant? How do you write the expression of equilibrium constant? Equilibrium constant, again, I'm telling you, it's nothing. It is just the ratio of rate constant of forward reaction to that of rate constant of backward reaction. And how do you write its expression? In the numerator, these are active masses of products. Active masses of products raised by their stoichiometric coefficients. Active masses of reactants raised by their stoichiometric coefficients. This is the general way by means of which you can write the equilibrium constant of the reaction. Right? Perfect. Now, let's try to analyze this a bit more in detail. Let's try to analyze this a bit more in detail. Have a look, people. What did I say? I said equilibrium constant. How do I write its expression? Active mass of C raised by N3, active mass of D raised by N4 divided by active mass of A raised by N1, active mass of B raised by N2. Right? Now, dear students, three things which I would want you guys to remember directly from now onwards. Three things, just three things. Whenever you see any reactant or product, in aqueous state, that means in the bracket, it will be mentioned as AQ. Do remember, for that particular reactant or product, which will be in aqueous state, its active mass will be taken its concentration. Similarly, my dear students, whenever you have any reactant or product in gaseous phase, its active mass can be taken its concentration or pressure. Because for gases, both the terms are defined. Concentration as well as pressure, both the terms are defined for gases. Right? Now, dear students, for any reactant or product which is in pure solid state, right? That means in the bracket it will be mentioned as S. Its active mass is taken as constant. Its active mass is a constant. And to reduce our calculation, basically, that constant is taken as 1. Similarly, whenever any reactant and product is present in pure liquid state, in the bracket it's mentioned as L. So generally, its active mass will be also taken as constant, which will be taken as unity. Right? These are the four things which I would want every one of you to remember. Any reactant product in aqueous state, its active mass is concentration. Gaseous state, its active mass can be concentration as well as pressure. Solid liquid, unity, directly. Now, based on all this, based on active mass, I'm going to classify equilibrium constant into many types. One is 1 Keq. One equilibrium constant is called as Kc, one is called as Kp, and one more equilibrium constant is called as Kx. There is one more, that is Kpc, which we do not need here. That's something which we need in electrochemistry, not here. Right? So first of all, what is this Kc, what is this Kp, and what is Kx? In the expression of equilibrium constant, what do we have? We have got active masses. We have got active masses. Whenever in place of active masses, you use the term concentration. Whenever in place of active masses, you use the term concentration. For example, you write concentration of C raised power n3, concentration of D raised power n4, etc. Like this. At that point of time, your KEQ becomes Kc. So, your KEQ becomes Kc. So, if I want you guys to write the Kc expression, how you are going to write it? It's going to be concentration of C at equilibrium raised by n3, concentration of D at equilibrium raised by n4 divided by concentration of A at equilibrium raised by n1, concentration of B at equilibrium raised by n2. All these concentrations of reactants and products, they are measured at equilibrium, right? Now, what is Kp? My dear students, if for example, in place of active masses, you use the term pressure, then KEQ is what I'll be calling as Kp. And Kp expression, how will I be writing it? It's going to be partial pressure of C at equilibrium raised by n3, partial pressure of D at equilibrium raised by n4, partial pressure of A at equilibrium raised by n1, partial pressure of B at equilibrium raised by n2. Right? Now you must be thinking what these partial pressures are. You'll get the idea in some time. If you want to write the expression for Kx, so what do you need to do? Replace active masses by the term mole fraction. So it's going to be mole fraction of C at equilibrium raised by n3, mole fraction of D at equilibrium raised by n4, mole fraction of A at equilibrium raised by n1, mole fraction of B at equilibrium raised by n2. So this is how you write the expressions of Kp, Kc and Kx. Right? Say yes or no in the chat if this point is clear to everyone. If this point is clear to everyone quickly. Yeah? Say yes or no quickly with the thumbs ups in the chats. Then only I can move ahead. Then only, my dear students, I can move ahead. Till now, I've not done any questions because this is all basics going on right now. Perfectly done? Yeah? Perfectly done? Okay, this partial pressure, I'll let you know in some time what it means. Okay, when I'll be teaching you Kp-Kc relation, then I'll make you understand what this partial pressure is. Or if you have studied states of matter from me, I've done states of matter already, right? There we have discussed Dalton's law of partial pressure. In Dalton's law of partial pressure, you would have studied it, right? When will you come to Tamil Nadu? Tamil Nadu, I'll be coming soon, maybe next week or after that. Just be ready to meet. Yeah. All right, people. So let's move on now. Let's move on and talk about a few interesting things. All right. These are two reactions which I've taken over here. Will we be able to write their Kp-Kc expressions? We should be able to write their Kp-Kc expression, right? My dear students, if I write the Kc expression, then I should use the term concentration. I'll start with the product. It's going to be concentration of Hi at equilibrium raised by stoichiometric coefficient divided by concentration of H2 at equilibrium raised by stoichiometric coefficient, concentration of I2 at equilibrium raised by stoichiometric coefficient. Similarly, if you want to write the expression for Kp, for gases, concentration as well as pressure is defined. So you can write Kc expression as well as Kp expression. Kp expression is going to be partial pressure of H2 at equilibrium, partial pressure of Hi at equilibrium raised by stoichiometric coefficient divided by partial pressure of H2 at equilibrium raised by stoichiometric coefficient, partial pressure of I2 at equilibrium raised by stoichiometric coefficient, right? Similarly, my dear students, if I ask you to calculate delta Ng for the reaction, can you calculate delta Ng for this reaction? What is delta Ng? If you remember, number of moles of gaseous products minus number of moles of gaseous reactants. So first of all, in order to calculate delta Ng, what do we need? We need number of moles of gaseous products and number of moles of gaseous reactants. So how many moles of gaseous products we have? We have got 2 moles of gaseous products minus. How many moles of gaseous reactants we have? We have got 1 plus 1. 2 moles of gaseous reactants. So delta Ng for this reaction will definitely come out to be 0. Simple. Look at the next reaction. All the reactants products, they are present in gaseous state. Right? Try to write Kc expression. Start from the product. It is concentration of PCl3 at equilibrium raised by stoichiometric coefficient, concentration of Cl2 at equilibrium raised by stoichiometric coefficient divided by concentration of TCl5 at equilibrium raised by stoichiometric coefficient, right? Similarly, for gases, you know concentration as well as pressure is defined. Now write the Kp expression. Write the Kp expression. Start with the product. It's going to be partial pressure of PCl3 at equilibrium raised by 1, partial pressure of Cl2 at equilibrium raised by 1, divided by partial pressure of PCl5 at equilibrium raised by 1. This is how you write Kp expression for this particular reaction, right? And my dear students, if I ask you to calculate delta Ng for this reaction, it's going to be number of moles of gaseous products. These are your gaseous products. So 1 plus 1 makes it 2, minus number of moles of gaseous reactant, which is 1. So 2 minus 1 will make it 1 only. So delta Ng for this particular reaction is 1 over here, right? Perfect. Is this clear to everyone? Is this clear to everyone? Now, dear students, have a look over here. This is, so by the way, these reactions which I took over here, these were homogeneous gaseous phase reactions. All the reactants and products were in gaseous state. So it was the homogeneous gaseous phase reaction. Now, all the reactants and products, they are not in gaseous state. They are not in gaseous state. It is just one product is in gaseous state. So this is something which I'll be calling as heterogeneous gaseous phase reaction, right? Heterogeneous gaseous reaction. Similarly, this is solid, this is gas, this is gas. All are not gas. If all were in gaseous phase, they're homogeneous. But all are not, so it's heterogeneous. Now try to understand. First of all, write the expression for Kc. Kc expression. Start with the product. This is solid, its ectomass is 1. This is gas, its concentration of carbon dioxide at equilibrium raised by stoichiometric coefficient. Divided by reactant is in solid state, its ectomass is 1. Nothing to do with that. Write the Kp expression. Kp expression. Again, it's just going to be partial pressure of carbon dioxide at equilibrium raised by stoichiometric coefficient. That's all. Calculate delta Ng for the reaction. Delta Ng for the reaction. Number of moles of gaseous products, which is 1, minus number of moles of gaseous reactants. These are in solid, nothing to do with them. So 1 is basically the delta Ng for the reaction, right? What happened to this? Okay, so I hope this is clear. Now talking about other one. This is solid, this is gas, this is gas. Write the Kc expression first of all. So solid, I've got nothing to do with solid, the ectomass is 1. So Kc, concentration of SO3 at equilibrium raised by stoichiometric coefficient divided by its concentration of O2 at equilibrium raised by stoichiometric coefficient. I've got nothing to do with solid. What about the Kp expression? Again, start with the product. It's partial pressure of SO3 at equilibrium raised by 1 divided by, it's going to be partial pressure of O2 at equilibrium raised by 3 by 2. This is how you guys are going to write Kp expression as well. Now, if you got Kp and Kc expression, then easily you can calculate delta Ng for this reaction. Number of moles of gaseous product, which is 1, minus number of moles of gaseous reactant, which is 3 by 2. So 1 minus 3 by 2 makes it minus 1 by 2. So this is delta Ng for the reaction. So I hope you got to know how to write Kp expression, how to write Kc expression, how to get the delta Ng, right? Perfect, guys? Perfect? Perfect? I'm sure these things you can easily do now. I'm sure these things you can easily do. You can write Kp Kc expression for this. You can write Kp Kc expression for this as well. You can calculate delta Ng for this reaction, delta Ng for this reaction, right? You should be in a position to write that. Okay? Or let me write one example. Kc for this particular reaction. Concentration of NO2 at equilibrium raised by 2 divided by concentration of N2O4 at equilibrium raised by 1. What about Kp? Kp is going to be partial pressure of NO2 at equilibrium raised by 2 divided by partial pressure of N2O4 at equilibrium raised by 1. Perfect. Delta Ng for this reaction, if you want to calculate, it's number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, which is 1. The value of delta Ng comes out to be 1 only. Correct? Now similarly, the next one. Write the Kc expression. Kc is going to be concentration of NH3 at equilibrium raised by 1, concentration of H2S at equilibrium raised by 1 divided by, this is solid, its ectomass is unity, nothing to do with that. Similarly, Kp expression. Partial pressure of NH3 at equilibrium raised by 1, partial pressure of H2S at equilibrium raised by 1. This is solid, its ectomass is unity. If I ask you, what about the delta Ng for this reaction? Number of moles of gaseous products, This is 1 plus 1, that's 2, minus number of moles of gaseous reactant. This is solid, so nothing to do with that, right? So it's 2 only. So 2 is going to be the delta Ng for the reaction. I hope you can easily do it, right? Perfect. Harish, you can check the live session. I have taken a video in which I have given the test planner. Just go to the lives category. You'll find at the bottom, you'll find like last week, I've taken a session in which I've given the whole test plan. Just watch it. Perfect. Where are you? Even we have made one Telegram channel as well for the test series students. I don't know where are you basically, right? So then you'll keep on commenting, where is the schedule? I have given the already schedule like 2 times on my Telegram everywhere. I've made a separate Telegram group for the test series students. So you should be active basically. It's your loss. It's not my loss. All right. So I hope till now, every single thing is clear. Now, my dear students, now comes something interesting. Over here, I'm going to write relation between Kp and Kc. This is something important. A relation between Kp and Kc. A relation between Kp and Kc. This is important, okay? Try to understand what exactly I'm going to do. For example, I'm going to make a reaction. N1A, for example, N1A gas, it gives N2B gas. This is one very simple reaction. N1A gas gives N2B gas. First of all, if I ask you, what about the delta Ng for this reaction? Delta Ng for this reaction is number of moles of gaseous products minus number of moles of gaseous reactant. So N2 minus N1. N2 minus N1, it is the delta Ng for the reaction. N2 minus N1, it is the delta Ng for the reaction. Now, dear students, if I ask you to write the Kc expression is going to be concentration of B at equilibrium raised to the power N2 divided by concentration of A at equilibrium raised to the power N1. If I ask you to write Kp expression, it's going to be partial pressure of B at equilibrium raised to the power N2 divided by partial pressure of A at equilibrium raised to the power N1. Now, first of all, before doing any sort of calculation here, let me ask you what these partial pressure of A and B are. See guys, it's simple. At time t is equal to 0, there will be only a reactant in the container, right? At time t is equal to 0, when the reaction has not started, there will be only gas A in the container, right? Now, when the reaction will start, that means moles of reactant will keep on decreasing. Moles of product will keep on increasing. Can I say at one point of time, equilibrium will be established, at which rate of forward and backward reaction becomes equal? So if I ask you at equilibrium, how many gases will be there in the container? Will there be only gas A or gas B also in the container at equilibrium? Can you let me know in the chats? I would say at equilibrium, there will be 2 gases in the container. Gas A, some moles of gas A left in the container, and some moles of gas B which would have got formed. So at equilibrium, there will be 2 gases in the container. So can I say at equilibrium, there will be a gaseous mixture? At equilibrium, there will be a gaseous mixture, right? Perfect. In that gaseous mixture, how many gases are there? 2 gases. So I would say at equilibrium, there will be a gaseous mixture present in the container. This gaseous mixture, it contains the moles of gas A left in the container, similarly the moles of gas B which would have formed. So this is the mixture of gases which is present at equilibrium. Let me assume that the total pressure of this particular gaseous mixture is Pt. Pt represents the total pressure of the mixture at equilibrium. Now, the total pressure of the mixture at equilibrium will be due to Pa as well as Pb. What is Pa? Pa is basically the contribution made by gas A towards the total pressure of the mixture. Similarly, Pb, it is the contribution made by gas B towards the total pressure of the mixture. Contribution made by A towards the total pressure, that's something which you call as partial pressure of A. Contribution made by gas B towards the total pressure of the mixture, that's called as partial pressure of B. I hope you got to know what this partial pressure is, right? So basically at equilibrium, you'll find a mixture of gas, right? There will be some moles of A left in the container, some moles of B which would have got formed. Perfect. So there is a mixture of gases in the container, right? Contribution made by gas A towards the total pressure, that's partial pressure of A. at equilibrium. Contribution made by gas B towards the total pressure of the mixture. That's partial pressure of B at equilibrium. As simple as that. Now guys, what exactly I'm going to tell you right here. Try to understand what exactly I'm going to tell you. Have a look. We know as far as ideal gas equation is concerned, P is equal to nRT divided by V. Yes, every one of you will be knowing as far as the ideal gas equation is concerned. So can I say P is equal to, what is N by V? Number of moles per unit volume. Should I be calling it a concentration? So concentration multiplied by R multiplied by T. Absolutely. So if I say partial pressure of A will be equal to concentration of A multiplied by R multiplied by T. If I say pressure of B, it's going to be concentration of B multiplied by R multiplied by T. Absolutely. Right. Now look at this particular scenario. KP is equal to partial pressure of B at equilibrium. Can I write concentration of B at equilibrium multiplied by R multiplied by T whole raised by what? Whole raised by N2, right? Divided by partial pressure of A at equilibrium. Partial pressure of A at equilibrium will be equal to concentration of A at equilibrium multiplied by R multiplied by T whole raised by N1. Correct? Right, people? So can I write the whole scenario like this? Concentration of B at equilibrium raised by N2 divided by concentration of A at equilibrium raised by N1. This is RT, this is RT. RT raised by N2, RT raised by N1. So this has to be RT raised to the power RT raised by N2 minus N1. And what is N2 minus N1? N2 minus N1 is nothing. That's delta Ng for the reaction. If I ask you what about this whole term? This whole term over here, which you can check, it is basically Kc. So it is Kc multiplied by RT raised to the power what? Raised power delta Ng. So basically we got one direct result which you guys are going to remember from now onwards. For a gaseous phase reaction, Kp is equal to Kc RT raised to the power delta N, right? So this is the first and the important result which you guys are going to remember from now on. Kp is equal to Kc. This particular reaction, this particular equation, it is used many a times. For example, Kp of the reaction will be given and you are supposed to calculate Kc. You can use this equation. Kc of the reaction is given. You are supposed to calculate its Kp. You can use this particular result as well to do the same. Yeah. So dear students, we got one very, very, very important result. And let's try to utilize this particular result in a proper format. Have a look. I told you Kp is equal to Kc RT raised by delta Ng. This is the reaction, this is the relation between Kp and Kc. Now, what all things we can generalize from here? See guys, what is this R? R is basically the gas constant, right? Do you remember its value? It's one of the values 0.0821 atm liter per Kelvin per mole. In order to reduce the calculation, this 0.0821 is written as 1 by 12, right? 0.0821 is written as 1 by 12 to reduce the calculation. Now, my dear students, try to understand. T stands for the temperature at which the reaction takes place. Now, the case number 1. If, for example, the reaction is taking place at 12 Kelvin temperature. If the temperature of the reaction is 12 Kelvin. If the reaction is proceeding at 12 Kelvin. If the reaction is proceeding at 12 Kelvin, tell me what will be the value of R into T. What will be the value of R into T? R is 1 by 12. Temperature is 12. 12 cancel. RT value is 1, right? If RT value is 1, 1 raised per anything is 1. That means any such reaction which is carried out at 12 Kelvin temperature, or that particular reaction, Kp will be always equal to Kc. This is case number 1. This is your case number 1. Case number 2. If for example, the temperature at which the reaction proceeds is greater than 12 Kelvin. If temperature is greater than 12 Kelvin, what will happen to the RT value? R is 1 by 12 and T is greater than 12. So R multiplied by T will be greater than 1. R multiplied by T is greater than 1. Now over here, 3 cases arise. First case, if delta Ng of such reaction is 0, if delta Ng is 0, so anything raised by 0 is 1. So I would say at that point of time, Kp will be equal to Kc. Now second case in the same. If for example, delta Ng for the reaction is greater than 0. if delta Ng for the reaction is greater than 0, this term is already greater than 1. This term is greater than 0. So what can we conclude? We can conclude Kp value will be greater than Kc. Similarly, the third case which arises here, if for example delta Ng value is less than 0, at that point of time you can categorically say Kp value is less than Kc. Right? Simple. Perfect. Similarly, case number 3. Case number 3. What is case number 3? Case number 3 is if temperature of the reaction is less than 12 Kelvin. If the reaction is carried out at less than 12 Kelvin. If temperature is less than 12 Kelvin, R multiplied by T. R is 1 by 12, temperature is less than. It's going to be less than 1. It's going to be less than 1. If RT is less than 1, then over here case 1 arises. First case, if delta Ng for the reaction is 0. If delta Ng for the reaction is 0. This term right now is less than 1. Less than 1 raised power 0 is 1 only. Therefore, Kp value has to be equal to Kc. First point. Second point. If delta Ng over here for the reaction is greater than 0, and in this particular case, Kp will be less than Kc. And the third one, if delta Ng for the reaction is less than 0, you would say Kp will be greater than Kc. Right? So, it depends on the temperature at which the reaction proceeds. Accordingly, you can say whether Kp will be greater than Kc or less than Kc or equal to Kc, depending on the temperature at which the reaction proceeds. Perfect. Now, my dear students, there is one more thing. There is one more thing. Let's try to understand that as well. There is one more thing. See, I give you a result. The result is Kp is equal to Kc RT raised to the power delta Ng for a gaseous phase reaction, right? Now, if we use some mathematics over here, if I multiply throughout by log, it becomes log of Kp is equal to log of Kc RT raised power delta Ng. Now, my dear students, you can write it as log of Kp is equal to log of m into n is equal to log of m plus log of n plus log of n. Or finally, you can write it like this: log of Kp is equal to, it's going to be log of Kc plus log of m raised power n is L log n. So delta Ng comes to the front, then you would be writing log of RT. Perfect. This is the logarithmic form of the same equation. This is the logarithmic form of same equation. And as far as this particular equation is concerned, you can plot a curve. You can plot a graph. The graph is going to be between log of Kp versus what? Log of Kp versus log of RT. My dear students, you have to plot a graph between log of Kp, which you are plotting along y-axis, log of RT, which you are plotting along x-axis. This delta Ng has to be m. The sign over here is positive. This log of Kc is your intercept. So y is equal to mx plus c. Y is equal to mx plus c. It's absolutely going to be a straight line like this. What about the slope of this graph? The slope means m value, and m right here is equal to delta Ng. What about the intercept? Intercept means the c value, and c value when you compare, it comes out to be log of Kc. So this intercept is nothing, it's log of Kc over here. So this is one graph which might be asked. Anything can be asked out of this, right? You'll begin with the graph, you'll begin with the slope, and you will have to identify what is the delta Ng for the reaction. You can easily do that. Yeah? Perfect. So right now, what did we do? We saw the relation between Kp and Kc. Perfect. There is one more relation. What is that going to be? There is one more relation. Let's try to understand that as well. One more relation is between Kp and Kx. Let's see what exactly is the relation between Kp and Kx. Try to understand this one as well. This is again important and simple at the same time. For example, you have got the reaction like this: N1A gas in equilibrium with, for example, N2B gas. This is the reaction which we have. First of all, I want you guys to write its expression for Kp. Okay, before writing expression for Kp, can you let me know what is the delta Ng for the reaction? Number of moles of gaseous product, which is N2, minus number of moles of gaseous reactant, which is N1. Correct? So delta Ng you calculated. Now at the same time, Kp has to be equal to partial pressure of B at equilibrium raised by N2 divided by partial pressure of A at equilibrium raised by N1. Similarly, I am asking you, what is the expression for Kx? Kx is just going to be mole fraction of B at equilibrium raised power n2 divided by mole fraction of A at equilibrium raised to the power n1. Correct? Yes. Now, my dear students, you tell me one thing. When equilibrium will be established in the reaction, at equilibrium, there will be some moles of A in the container. There will be some moles of B in the container as well. So at equilibrium, will there be only one gas or two gases in the container? So at equilibrium, there will be gas A as well as gas B in the container. Few moles of gas A which are left and few moles of gas B which have got formed. So at equilibrium, there is a gaseous mixture present in the container. At equilibrium, there is a gaseous mixture present in the container. Now, the total pressure of the gaseous mixture at equilibrium, I'm representing it with PTEQ. This is the total pressure of the mixture. And the total pressure of the mixture will be equal to the sum of their partial pressures. So, partial pressure of A partial pressure of A at equilibrium plus partial pressure of B at equilibrium. Perfect. This will be equal to total pressure of the mixture. Now, you must be studied partial pressure of A at equilibrium will be equal to total pressure of the mixture at equilibrium multiplied by mole fraction of A at equilibrium. Similarly, partial pressure of B. How do we calculate partial pressure of gas? It's total pressure of the mixture at equilibrium multiplied by mole fraction of B at equilibrium. As simple as that, right? This is something which you know because we have discussed this in states of matter as well when I taught you the Dalton's law of partial pressure. Now, my dear students, try to understand what I'm going to say. Kp has to be equal. What is partial pressure of B at equilibrium? Partial pressure of B at equilibrium can be written as total pressure of the mixture at equilibrium multiplied by what? Mole fraction of B at equilibrium, right? Whole raised by what? Whole raised by N2 divided by partial pressure of A at equilibrium. It's going to be total pressure of mixture at equilibrium raised by total pressure of mixture at equilibrium multiplied by just a second, guys. This was B. Okay, this A. So it's mole fraction of A at equilibrium. And whole raised by what? Whole raised by N1. Let's try to understand what do we get over here. Let's try to understand what do we get over here. My dear students, you can write it like this. PT raised by N2, PT raised by N1. So is it going to be total pressure of the mixture at equilibrium raised by N2 minus N1? N2 minus N1 is delta Ng. Over here you got mole fraction of B at equilibrium raised by N2, mole fraction of A at equilibrium raised by N1. So mole fraction of B at equilibrium raised by N2 divided by mole fraction of A at equilibrium raised by N1. That basically denotes your Kx. So right here, you got one more amazing result. And what is this result? The result is very simple. Kp is equal to Kx multiplied by total pressure of the mixture at equilibrium raised by what? Raised by what? Raised by delta Ng. This is one result which connects your Kp with Kx. Right? This one result which connects your Kp and Kx. So finally, what did we get to know? Finally, what did we get to know? We got to know your Kp is equal to, we got to know your Kp is equal to Kx multiplied by total pressure of the mixture at equilibrium raised to the power delta Ng. This is the result which we got. This is the relation between your Kp and Kx. Now at the same time, if you want to convert it into the logarithmic form, so multiply throughout by log, it is going to be log of Kp has to be equal to log of Kx as such. This is total pressure at equilibrium raised to the power delta Ng. Now use a bit of maths here. So log of Kp has to be equal to log of m into n, which has to be equal to log of m plus log of n plus log of n. Now you can convert it like this. So log of Kp is equal to, it's log of Kx plus log of m raised by n, which is n log m. So delta Ng comes to the front, right? It's going to be log of total pressure of the mixture at equilibrium. That's all. So this is the logarithmic form of the same equation. This is the logarithmic form of the same equation. Now, if you got the logarithmic form of the same equation, you can directly make one curve, and the curve has to be between log of Kp versus log of total pressure of the mixture at equilibrium. Now, can you let me know what will be the nature of this curve? Can you let me know what is the nature of this curve? My dear students, log Kp, you are plotting along y-axis. Log of Pt, you are plotting along x-axis. So this has to be your m, and this has to be c. Y is equal to mx plus c. Isn't it again going to be a straight line? Absolutely, it's a straight line. What about the slope of this graph? Slope is basically m, and m value comes out to be delta ng. And my dear students, what about this intercept? Intercept is c, and c value after getting, we it as log of kx. Perfect. Perfect. So till now, we got two results. Till now, we got two results. The first result was Kp is equal to Kc RT raised power delta Ng for the gaseous phase reaction. The second result is Kp is equal to Kx multiplied by total pressure of the mixture at equilibrium raised power delta Ng. Now look at the two equations, my dear students. Kp is equal to this, Kp is equal to this. From equation 1 and equation 2, can't we say Kc multiplied by RT raised power delta Ng has to be equal to Kx multiplied by Pt at equilibrium raised power delta Ng? Correct? So I can say Kc is equal to Kx. This is total pressure of the mixture at equilibrium divided by RT whole raised power what? Whole raised power delta Ng. This is the final relation, and this is the relation which connects your Kc with Kx. So I hope all these things are absolutely clear, right? Is it clear, guys? Is it clear? Is it clear? Let me know once in the chats quickly if every single thing is clear till here. Yeah? Right? So I think everything is sorted. So Kc is equal to Kx. This is Pt divided by RT raised power delta Ng. Right. Okay, if I ask you one thing, if we multiply this equation throughout by log, after doing every calculation, the final result will be like this. Log of Kc is equal to log of Kx plus delta Ng log of Pt divided by RT. This will be the final expression. After multiplying with a log, this will be the final expression. So at the end, if I ask you to draw a graph, to plot a graph between log of Kc and log of Pt divided by RT, can you let me know what will be the nature of this curve? Can you let me know what will be the nature of this curve? Log of Kc you are plotting along y-axis. Log of Pt divided by RT you are plotting along x-axis. So this has to be your m, right? And this has to be your c. Y is equal to mx plus c. Y is equal to mx plus c is going to be something like this. Slope of this graph is delta Ng, right? What about the intercept? Intercept is going to be log of Kx. So this is something which every one of you must know. Okay? Perfect. So my dear students, one very simple question. What very simple question? Write the Kp expression in the form of Kc. You have to write Kp in terms of Kc basically. So for the reaction number one, what is delta Ng? Delta Ng is number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, which is 1 plus 1, that's 2. So 2 minus 2 is 0. So we know Kp is nothing, that is Kc. RT raised power delta Ng is 0. So for the first reaction, I must say Kp is equal to Kc. Simple. For the first reaction, Kp is equal to Kc. Second reaction. Calculate delta Ng. Delta Ng will be equal to number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactant. So the value comes out to be 1. So delta Ng is 1. If delta Ng is 1, you can say Kp is equal to Kc RT raised power delta Ng. Since delta Ng is 1, so you got to know Kp is equal to Kc raised power RT. And Kp is equal to Kc RT. Right? Similarly, look at the third equation. Calculate delta Ng. Delta Ng for the reaction is equal to number of moles of gaseous products, which is 2, minus number of moles of gaseous reactants, which is 1 plus 3, that's 4. The value comes out to be minus 2. So I would say Kp is nothing, that is Kc RT raised to the power delta Ng, which is minus 2. So this is the relation between Kp and Kc. And at the end, for the fourth reaction, calculate delta Ng. Delta Ng is equal to number of moles of gaseous products, which is 1, minus number of moles of gaseous reactant, that's 0. So the value comes out be 1. If delta Ng is 1, you can say Kp is equal to Kc RT raised power 1. So this is the relation between your Kp and Kc for the last reaction as well. Yeah? Perfect. I hope you can do these basic questions, basic things from now onwards. Easily you can do that. Now guys, there is something called as units of Kp and Kc. What are going to be the units of Kp and Kc? Right? It's again simple. For example, you have got a gaseous phase reaction. N1A gas, it's an equilibrium with N2B gas. It's a gaseous phase reaction. If I write the expression for Kc, it's going to be concentration of B at equilibrium raised power N2, concentration of A at equilibrium raised power N1. Similarly, if I ask you about the Kp expression, it's going to be Kp is going to be partial pressure of B at equilibrium raised to the power N2 divided by partial pressure of A at equilibrium raised to the power N1. Correct? Now, what about the units of Kc? This is concentration, which is moles per unit volume. Concentration moles per unit volume. So in the numerator, you have got moles liter inverse raised by N2. In the denominator, you have again got moles liter inverse raised by N1. So you can say Kc units are going to be moles liter inverse raised by N2 minus N1. So you can say Kc units are going to be moles liter inverse. N2 minus N1 is basically delta Ng for the reaction. So it's going to be delta N over here. Perfect. Right? So these are the units of your Kc. Similarly, Kp units if you ask me. So in the numerator there is pressure, in the denominator there is pressure as well. Let's assume we are taking pressure in atm. So it's atm raised by N2, atm raised by N1. So it's going to be atm raised by N2 minus N1, which is basically delta N for the reaction. Perfect. So this is how you can check the units of Kp and Kc for any sort of reaction which is given to us. I hope all these things are absolutely clear to you. So say yes or no in the chats if all the things are absolutely clear. Yeah. I hope all the things are absolutely clear till here, right? Right, people? Now, moving on to characteristics of equilibrium constant. Moving on to characteristics of equilibrium constant. When you write the expression of equilibrium constant Kc, for example, what do we need? We need concentration of reactants and products at equilibrium, right? We write concentration of product at equilibrium raised by stoichiometric coefficient divided by concentration of reactant at equilibrium raised by stoichiometric coefficient. That's what we do. So what do we need? We need the concentrations of reactants and products at equilibrium. Do we need the concentration of reactant initially? While writing the equilibrium constant expression Kc, do we need the initial concentration of reactants? No. What do we need? We need the concentration of reactants and products at equilibrium, not initial ones. So do remember, equilibrium constant, it does not depend upon initial concentration of reactants. Point number one. It does not depend upon the initial concentration of reactants. Now point number two. Equilibrium constant, it does not depend upon the catalyst as well. What the positive catalyst does? Positive catalyst, it speeds up the reaction. It speeds up the forward as well as backward reaction, due to which equilibrium is established earlier in the reaction, nothing else. But the equilibrium concentrations, they are same, right? In presence of positive catalyst, what does the positive catalyst do? Positive catalyst, it speeds up the reaction. It speeds up the forward and backward reaction. When the rate of forward and backward reaction increases, so I must say equilibrium in presence of positive catalyst is attained earlier in the reaction, nothing else, right? So in absence of catalyst, imagine that equilibrium was getting established in 1 hour. In presence of positive catalyst, same equilibrium, for example, in the reaction is being established in 10 seconds. So it just speeds up the forward backward reactions, due to which equilibrium comes in the reaction early. But the equilibrium concentrations in presence of catalyst or in absence of catalyst, it will remain the same only. If nothing happens to the equilibrium concentrations of reactants and products, that means nothing is going to happen to the value of equilibrium constant. So equilibrium constant, its value does not change in presence or absence of catalyst, whatever. Yeah. Equilibrium constant, it depends on temperature. Now you must be thinking how, right? That's something which we have to discuss afterwards. Perfect. So keep it as such. Keep it as such. I'm just telling you, equilibrium constant, it depends on the temperature. So we will have to discuss in detail how equilibrium constant changes on changing the temperature for endothermic reactions, same for exothermic reactions. That's something which is a good debate, but afterwards, not now. Okay. Equilibrium constant, it depends on the stoichiometric representation of a reaction. Stoichiometric representation of a reaction. What does that mean? For example, I've got the reaction like this. A gives B. Perfect. I'm writing its expression for Kc. Kc expression is concentration of B raised per n, concentration of B raised per stoichiometric coefficient 1 at equilibrium divided by concentration of A at equilibrium raised per 1. Correct? Right? Now, for example, if I multiply the same reaction with 2, now Kc expression will be concentration of B at equilibrium raised per 2 divided by concentration of Ba at equilibrium raised per 2 as well. So what has happened? On changing the stoichiometric representation, the value of equilibrium constant changed over here. So Kc value is coming out to be concentration of B at equilibrium raised per 1. Here it's 2, right? Perfect. Right, people? Now, the actual 3 things which you need to know about equilibrium constant, which are very important, from which questions can be easily asked. What is that? Look at the statement. When the reaction is reversed, its equilibrium constant gets inversed. What does that mean? For example, you have got the reaction like this. A gives B. This is the general reaction, whose equilibrium constant, for example, is K. Now, my dear students, when you reverse this reaction, when you reverse the same reaction, on reversing the reaction, equilibrium constant is inversed. Now, I would say the equilibrium constant of this particular reaction, it won't be K, it will be 1 by K. So the first point which you will be remembering directly from now on, right? On reversing the reaction, equilibrium constant is inversed. Point number 1. Point number 2. If the reaction is multiplied by any number, that number goes to the power of equilibrium constant. What does that mean? Over here, we have got a general reaction. A gives B, whose equilibrium constant, for example, is K. Now, for example, I'm multiplying this reaction by a number X. I'm multiplying this reaction by a number X. When you multiply the reaction by any number, that number goes to the power of equilibrium constant. Now, its equilibrium constant is going to be K raised per X, right? If you are multiplying by 2, it's K square. If you are multiplying by 3, it's K cube. If you are multiplying by 1 by 2, it's K raised per 1 by 2. Nothing else. Okay? If 2 reactions are added together, the equilibrium constant gets multiplied. For example, you have got the reaction like this. A plus B in equilibrium with C, its equilibrium constant is K1. Now, D plus E, it's in equilibrium with F. Let's say its equilibrium constant is K2. Now, for example, if I add these 2 reactions, after adding the reactions, the net reaction is going to be A plus B plus D plus C. It gives what? It gives E plus F. My dear students, it gives C plus F. Okay, so on adding the reactions, what happens to the equilibrium constants? I would say equilibrium constant of this reaction will be K1 multiplied by K2. So basically, these are 3 basic things which, if you remember, you can easily solve all the questions, my dear students, right? Which are based on characteristics. So point number 1, which you have to remember. What is that? Number 1. When a reaction is multiplied by some number, that number goes to the power of its equilibrium constant. Point number 1. Point number 2. If a reaction is reversed, its equilibrium constant is inversed. Point number 2. Point number 3. When you add 2 reactions, right, which are in equilibrium, the equilibrium constants are multiplied, right? Perfect? Perfect, guys? So these are some basic things which I would want all of you to remember for now. Okay? So this was the last slide, I believe, which I discussed with all of you in the last session. That is characteristics of equilibrium constant. And as I told you in the last session, there are 3 important points which you have to remember basically. Yeah. The first point was, for example, you have got the reaction which is at equilibrium. And the you have got a reaction which is at equilibrium. Let's assume the equilibrium constant of this particular reaction is K. The first important point was, which I told you, when you reverse this reaction, on reversing the reaction, what happens to the equilibrium constant? It is inversed. If the equilibrium constant of the reaction was K, now on reversing the reaction, equilibrium constant will become 1 by K. This was point number 1. Point number 2. Whenever you multiply a reaction by some number, that number goes to the power of equilibrium constant. See, this was the reaction whose equilibrium constant was K basically. When I multiplied this reaction by X, that X goes to the power of equilibrium constant. Now the equilibrium constant of this particular reaction will be K raised by X. This was one more thing which we discussed. Similarly, on adding the reactions, the equilibrium constants are multiplied. These were few basic things which I discussed with you in the last session, right? So my dear students, let's try to solve few questions based on the same concepts so that you'll get to know how questions are asked in your NEET from the same concept. Okay, let's try to understand. See guys, as far as the question is concerned, we are given with a reaction, and the reaction is like this: N2 gas plus 3 times H2 gas. It is in equilibrium with 2 times NH3 gas. The equilibrium constant Kp for this particular reaction, as per the question, that is 49. What are we supposed to calculate? We are supposed to calculate the equilibrium constant for this particular reaction. Only one thing which you have to remember. My dear students, the reaction for which you are supposed to calculate the equilibrium constant. The reaction for which you are supposed to calculate equilibrium constant. You will be making that reaction out of the given reaction whose equilibrium constant will be given to us. Okay? So the one whose equilibrium constant is to be calculated, you'll be making this particular reaction out of the reaction whose Kp or Kc we already know. Now how exactly? Let's have a look. My dear students, I'll first of all reverse the given reaction. When I reverse the reaction, it becomes 2 times NH3 in equilibrium with N2 plus 3 times H2. And you know, on reversing the reaction, what happens to the equilibrium constant? I would say equilibrium constant of this particular reaction now will be 1 upon 49, right? Now, for example, if I multiply this reaction by 1 by 2, if I multiply this particular reaction with the number 1 by 2, what happens? Upon multiplying this whole reaction by 1 by 2, 1 by 2 and 2 gets cancelled. So you'll be left with NH3, which gives 1 by 2 times N2 plus 3 by 2 times H2. So what exactly I did? I multiplied this reaction by 1 by 2. That 1 by 2 will go to the power of equilibrium constant. So the new equilibrium constant of this reaction will be 1 upon 49 raised power 1 by 2. The value is going to be 1 upon 7, right? Now, my dear students, just have a look on this particular reaction and this particular reaction. Are these same or different? These are absolutely same. That means what we did, we made the reaction whose equilibrium constant was to be calculated. And accordingly, we got its equilibrium constant as well. Done and dusted, right? Let me know once in the chat if it is clear. This is a very simple and basic question which can be asked from the things which I told you in the last session, right? Let me show you one more question out of the same so that you can properly understand it. My dear students, you are given with 3 reactions basically, right? Equilibrium constant of the first reaction is K1, equilibrium constant of the second reaction is K2, and equilibrium constant of the third reaction, that is K3. What exactly we are supposed to do? This is the reaction whose equilibrium constant we have to calculate. This is the reaction whose equilibrium constant we have to calculate. So what exactly we are going to do? We will try to make this particular reaction out of the given reaction. We'll try to make this particular reaction out of the given reactions. Now, how exactly? Let's have a look. The reaction which we have to make, in that reaction, NH3 is on left side. NH3 is on left side. But if you look at the first reaction, here NH3 is on right side. So let's try to do one thing. Let's try to reverse the first reaction. Let's try to reverse the first reaction. Upon reversing the first reaction, what do we get? We'll be getting 2 times NH3 in equilibrium with N2 plus 3 times H2. And you know, upon reversing the reaction, what happens to the equilibrium constant? It is inversed. So the equilibrium constant of this particular reaction now is going to be 1 upon K1. Correct? Let me write the second reaction as such. Second reaction is N2 plus O2. It gives 2 times NO. Its equilibrium constant is equal to K2, right? Its equilibrium constant is equal to K2. Now, my dear students, what else can we do? Have a look. If I multiply this particular reaction by number 3, I'm multiplying this reaction by 3. What will happen due to that? Let's try to understand. It becomes 3 times H2 plus 3 by 2 times O2. It is in equilibrium with 3 times H2O. And you know, when we multiply a reaction by some number, that number goes to the power of equilibrium constant. So I would say the equilibrium constant of this particular reaction now will be K3 raised power 3. I hope this is clear till here, right? Now, my dear students, the 3 reactions which I made over here, if I add them up, what will happen? If I add them up, what is going to happen? So first of all, N2 and N2 will absolutely get cancelled out. 3 times H2 will absolutely get cancelled out. What am I left with on LHS side? I'm left with 2 times NH3. I'm left with 2 times NH3. O2 plus 3 by 2 O2. O2 plus 3 by 2 O2 makes it 5 by 2 O2. It is in equilibrium with. It's in equilibrium with. Here we have got 2 times NO and I'll be writing 3 times water as well. So my dear students, look at this particular reaction. Were we supposed to make the same reaction? Just compare them. Were we supposed to make the same reaction? Absolutely. And how did you make this reaction? When you added these 3 reactions over here. And you know, on adding the reactions, the equilibrium constants are multiplied. So the equilibrium constant of this particular reaction now will be 1 upon K1 multiplied by K2 multiplied by K3 raised to the power 3. This is the new equilibrium constant for the reaction which we were supposed to calculate. Give me some thumbs up in the chats if you got to know how to deal with these sort of questions. These are the basic questions which are asked in equilibrium. And questions are asked from these concepts. Say yes or no in the chats if it is super clear to you. Quickly. Everyone in the chats. Quickly, guys. All right. One more question on your screen. Give it a try. We are given the reaction whose equilibrium constant is K1. One more reaction whose equilibrium constant is K2. We have to get the relation between K1 and K2. We are supposed to get the relation between K1 and K2. And how exactly are we going to do that? My dear students, what I'll be doing, let me write this reaction again. It is basically 6 times AB in equilibrium with 3 times A2 plus 3 times B2. This is the reaction that's given to me, whose equilibrium constant is K2, correct? Now, for example, let me just do one thing. My dear students, I'll be first of all reversing this reaction. And when I reverse this reaction, it becomes 3 times A2 plus 3 times B2. It is in equilibrium with 6 times AB. And you know, on reversing the reaction, the equilibrium constant is inversed. Now it becomes 1 upon K2. Yeah? Let me do one more thing. Let me multiply this reaction by the number 1 by 3. If I multiply this reaction by 1 by 3, 1 by 3 and 3 gets cancelled, it's A2. 1 by 3 and 3 gets cancelled, it is B2 here. And 1 by 3 into 6 makes it 2 times AB. So what I did, I multiplied this reaction by the number 1 by 3. That number will go to the power of its equilibrium constant. So it's 1 by K2 whole raised power 1 by 3. Correct? Right, guys? Perfect. Now try to understand one thing. Look at this particular reaction and look at this particular reaction. Are these reactions same or different? These reactions are same, right? As per the question, the equilibrium constant of the reaction is K1, and as per us, this is the equilibrium constant of the reaction. That means this particular value has to be equal to what? It has to be equal to K1. So this is going to be the relation between K1 and K2 in this particular scenario, right? Isn't it again simple, my dear students? Isn't it again simple? Quickly, let me know in the chats. If all these things are absolutely clear. This is the relation between your K1 and K2 over here in this particular question. Yeah? Say yes or no in the chats if it is super clear. Quickly. Quickly, guys. Right? Wonderful. Now, my dear students, let me see one more question, which I'm 100% sure you can easily solve. Look at this basic question. I'm right now showing you basic questions only. With time, we'll increase the level of the questions when we enter into the actual calculation process. In the following equilibrium reaction, we are given with a reaction which is 2 times A. It's in equilibrium with B plus C, right? The equilibrium concentration of A, B and C are, so concentration of A at equilibrium is given to us, how much? That is 1 into 10 raised power minus 3 molar. The concentration of B at equilibrium is also given to us, how much? That is 2 into 10 raised power minus 3 molar. Similarly, the concentration of C at equilibrium, that's also given to us, that is 3 into 10 raised power minus 3. 3 into 10 raised power minus 3 molar. What am I supposed to calculate? I'm supposed to calculate the value of Kc for this particular reaction. Do you remember how do we write the expression for Kc? Do you remember that? I'll be starting with the product. I'll write concentration of B at equilibrium raised to the power its stoichiometric coefficient, that's 1, multiplied by concentration of C at equilibrium raised to the power its stoichiometric coefficient, that's 1, divided by concentration of A at equilibrium raised to the power its stoichiometric coefficient, that is 2. Now, my dear students, am I given with all these values? Absolutely, I'm given with all the values, right? Now, you tell me one thing. What is the concentration of B at equilibrium? That is 2 multiplied by 10 raised power minus 3. What is the concentration of C at equilibrium? Which is 3 into 10 raised power minus 3 divided by concentration of A at equilibrium. That is 10 raised power minus 3. 10 power minus 3 raised power 2. So it's 10 raised power minus 6, right? So the question is done. 10 raised power minus 6, 10 raised power minus 6 cancel. 3 into 2 comes out to be 6. So 6 is basically going to be the value of Kc for the reaction which we were supposed to calculate. So let me know once in the chats quickly if it is again clear to you. Let me know quickly in the chats, people, if it is again clear to you. Quickly. Yes? Again, a basic question this was. Look at one more question. In which of the following equilibrium Kc and Kp are not equal? Do you remember the relation between Kp and Kc which I gave you? You know Kp is equal to Kc RT raised power delta n. Do you remember that? In the last session we discussed. Perfect. Now you tell me one thing. If, for example, if delta n is equal to 0, anything raised power 0 is 1, then I can say Kp will be equal to Kc. Correct? So Kp will be equal to Kc, while delta n will be equal to 0. Perfect. But they are not mentioning it. They are mentioning when Kp and Kc won't be equal. This is the criteria for Kp and Kc to be equal. But they are asking you, when Kp and Kc won't be equal, I'll say if delta n is non-zero, at that point of time only, Kp won't be equal to Kc. Do you agree with this? Yeah? Now you have to select that reaction whose delta n is not equal to 0. Whose delta n is not equal to 0. You can check one by one. Well, if you talk about the first reaction, in the first reaction, delta Ng is equal to number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactant, which is again 2. So 2 minus 2 is 0. So for the first reaction, delta Ng value is 0, right? So for the first reaction, Kp will be equal to Kc. But my dear students, if you check the last reaction, calculate delta Ng for this reaction, it's going to be equal to number of moles of gaseous products, which is 2, minus number of moles of gaseous reactant, that's 1. So the value comes out to be 1. So is delta Ng coming out to be 0? No, it's not coming out to be 0. It's coming out to be 1. Therefore, Kp and Kc for the last reaction, they won't be equal. Correct? Agreed? Let me know quickly in the chats. All right. One more simple question. One more simple question. Look at this question. Value of Kp in the reaction. We are given with the reaction. We have to write the expression of Kp. Can't you do it? Can't you do it? Kp expression we have to write. We'll be starting with the product. We'll be starting with the product. This is in solid state. Its active mass is unity. This carbon dioxide is in gaseous state. Since I'm writing the expression for Kp, so I'll have to use partial pressure of carbon dioxide at equilibrium raised to the power its stoichiometric coefficient, that's 1, divided by, look at the reactant, it's also in solid state, so its active is unity, nothing to do with this. So this is the expression for Kp, nothing else. So option A. Isn't it simple? Isn't it simple, my dear students? Absolutely, your equilibrium is damn simple till here. Now we are going to enter into the actual stuff, where student mess up basically, right? Let's get into the actual part now. Let's get in the actual part now. This is something which is amazing. It's interesting at the same time, provided you know the concept. And I'll be exactly starting from the basics. I'll make sure that you should be able to solve all the questions from this particular topic. Relation between Kp and Kc, right? So, this particular topic is calculation of Kp and Kc. How Kp and Kc for a particular reaction is calculated. Try to understand everything, my dear students. Let me first of all tell you, there are two methods which we have to discuss for the calculation of Kp and Kc. One is called as mole method, one is called as degree of dissociation method. These are the two methods by means of which we can calculate Kp and Kc for a particular reaction. You just have to follow a sequence basically. A sequence. There are some steps which you need to follow to calculate Kp for a reaction. Similarly, there are some steps which you have to follow to calculate Kc for the reaction. And before going into that, let me teach you some real basic stuff, my dear students. Some real basic stuff. Understand properly what I'm going to teach you. First part, I'm going to teach you the calculation. The calculation of moles. Calculation of moles of reactants and products at equilibrium. This is the most important point, right, which you have to understand. How do we calculate the moles of reactants and products at equilibrium? Once you get to know how to calculate the moles of reactants products at equilibrium, then easily you can calculate Kp and Kc for a particular reaction, right? Yes? Now guys, have a look. Understand. The first example which I'm taking, for example, I have got the reaction like this. A is in equilibrium with B plus C. Let's assume this is a particular reaction which is at equilibrium. I'm going to show you how to calculate the moles of reactants and products present in the container at equilibrium. Since this reaction will be taking place in a closed container, right? So, how do we calculate the moles of reactants and products at equilibrium? Let's try to understand. For example, my dear students, let's say I'm starting with time t is equal to 0. For example, at time t is equal to 0, we have got some A moles. We have got some A moles of reactant in the container. Let's assume at time t is equal to 0, when the reaction has not started, when there is no product formation, there will be only reactant in the container whose moles are A. Since the reaction is not started, so number of moles of B and C present in the container at time t is equal to 0. That's absolutely going to be 0, right? Now, my dear students, what will happen? When the reaction will start, the number of moles of reactants, they'll keep on decreasing. And number of moles of product will keep on increasing. A time will come, a stage will come, when rate of forward and backward reaction becomes equal. That stage is what we call as equilibrium. So, let's assume when equilibrium is established in the reaction. Let's assume when equilibrium is established in the reaction. At that point of time, let's assume that out of A moles of reactant, let's assume X moles of reactant got converted into products. When equilibrium is established, at that point of time, let's assume that out of A moles of reactant, X moles of reactant got converted into products. So, can you let me know how many moles of reactants I'll be left with? Initially, I had A. Out of A, X moles are getting converted into products. So, at equilibrium, I'll be left with A minus X moles of reactants. So, these are the moles of reactants which are present in the container at equilibrium. Now, guys, after this, try to use the stoichiometry all the time. Have a look. 1 mole of A gives 1 mole of B. Therefore, X moles of A will give X moles of B. As simple as that. Similarly, 1 mole of A, it gives 1 mole of C. Therefore, X moles of A will give us X moles of C. So try to understand what I calculated exactly. Try to understand. These are the moles of these are the moles of C present in the container at equilibrium. These are the moles of B present in the container at equilibrium. And these are the moles of reactant present in the container at equilibrium. Perfect. One more thing. Initially at time t is equal to 0, there was only reactant in the container. So there was only one gas in the container. There was only one gas in the container initially. Initially, there was only one gas in the container. There were only A moles of reactant in the container. Now at equilibrium, what we are observing? We are observing there are some A minus X moles of reactant, X moles of B, X moles of C as well. So if I ask you, how many gases are there in the container at equilibrium? You will say there will be 3 gases present in the container at equilibrium. There will be A minus X moles of gas A, X moles of gas B, X moles of gas C. So there are basically 3 gases. There are basically 3 gases present in the container at equilibrium. So can I say at equilibrium, what do we have? I'll say at equilibrium, we will be having a gaseous mixture in the container. We will be having a gaseous mixture in the container, right? Perfect. Now, my dear students, tell me one more thing. When equilibrium is established, once equilibrium is established, can I say after that, the moles of reactants and products, they have become constant, they have become fixed. They are not going to change now because the rate with which the forward reaction takes place, same as the rate with which the backward reaction takes place. As simple as that. Yeah? Right, people? This was the case number 1. Similarly, let me have a look on case number 2. This is something important which I'm teaching you right now. If this is clear to you, that means Kp, Kc calculation easily you can do. Try to understand one more thing. For example, I've got the reaction like this. A gas is in equilibrium with 2 times B gas plus 3 times C gas. For example, this is the reaction. Okay. Now, my dear students, for example, initially at time t is equal to 0, we have got A moles of reactant. We have got, for example, A moles of reactant at time t is equal to 0. Since the reaction has not started, therefore, the moles of product at time t is equal to 0. That's going to be 0. Right? Now, my dear students, let's assume that at equilibrium, out of A moles of reactant, let's assume X moles got converted into product. So I'll be left with A minus X moles of reactant. So I would say this A minus X, these are the moles of reactant present in the container at equilibrium. Perfect. Now use the stoichiometry. 1 mole of A gives 2 moles of B. If 1 mole of A gives 2 moles of B, I would say X moles of A will give us 2X moles of B. Right? Similarly, 1 mole of A gives 3 moles of C. Therefore, X moles of A will give us 3X moles of C. So what did I calculate? These are the moles of reactant present in the container at equilibrium. These are the moles of B present in the container at equilibrium. These are the moles of C present in the container at equilibrium. Initially, at time t is equal to 0, there was only one gas in the container whose moles were equal to A. Now, at equilibrium, there are 3 gases present in the container. These are the moles of gas A present in the container at equilibrium. These are the moles of gas B in the container at equilibrium. These are the moles of gas C present in the container at equilibrium. Right? Perfect. This was case number 2. For example, let's have a look on case number 3. Case number 3. Try to understand. I'm giving you different scenarios. For example, you have got the reaction like this. 2 times A in equilibrium with, for example, B. Or let's write it as B plus C. 2 times A in equilibrium with B plus C. Try to understand. I'll start with time t is equal to 0. At time t is equal to 0, I'm starting with A moles of reactant. This is 0, this is 0, right? Now at equilibrium, let's assume out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactant, correct? Now, the stoichiometric coefficient here is 2 and here it is 1. Can I say 2 moles of A gives 1 mole of B? So 1 mole of A gives 1 by 2 moles of B. So x moles of A gives 1 by 2 into x by 2 moles of B. As simple as that. Similarly, 2 moles of A gives 1 mole of C. So 1 mole of A gives 1 by 2 moles of C. So x moles of A gives x by 2 moles of C. So what did I calculate? These are the moles of reactant present in the container at equilibrium. Right? These are the moles of product B present in the container at equilibrium. Right? These are the moles of C present in the container at equilibrium. I hope all these things you can calculate easily from now onwards. Right? Perfect, guys. Perfect. Let me know once in the chats quickly. Let me take one more scenario. I'm going to take case number 4. These are different examples basically I'm giving you so that you can understand it clearly, so that there will be no issue in understanding things afterwards. Yeah? Have a look. For example, I'm giving you the reaction like this. 2 times A, it gives 3 times B plus 5 times C. This is the reaction, for example. Now you are going to tell me everything. At time t is equal to 0, we are starting with A moles of reactant. This is 0, this is 0. At equilibrium, let's assume that out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactants. Right? These are the moles of reactants present in the container at equilibrium. Now we use the stoichiometry. Can I say 2 moles of A gives 3 moles of B? 1 mole of A gives 3 by 2 moles of B. X moles of A gives 3 by 2 X moles of B. Simple. 2 moles of A gives 5 moles of C. 1 mole of A gives 5 by 2 moles of C. So X moles of A gives 5 by 2 X moles of C. So what did I calculate? These are the moles of A in the container at equilibrium. Moles of B in the container at equilibrium. Moles of C in the container at equilibrium. Right? Perfect. Now, my dear students, there can be few more things as well, wherein you can maybe get the doubt. Right? Let me show all those things here only. For example, you're going to reaction like this. 2 times A gives B plus C. Correct? Now, for example, I'm giving you a scenario like this. Let's say at time t is equal to 0. Already there are A moles of reactant present in the container. For example, before the start of this reaction itself, let's say there are B moles of this particular product in the container and C moles of this particular product in the container already. Before the start of the reaction, I'm assuming that we have got A moles of reactant in the container. Already before the start of the reaction, there is B in the container. How many moles? B moles of product B in the container. C moles of product C in the container already before the start of the reaction. Now when the reaction starts, what's going to happen? The same thing which we discussed. At equilibrium, let's assume that out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactant in the container. Right? Now, my dear students, already in the container, there were B moles of this particular product. Right? Now, due to reaction, can I say some more moles of B would have got formed? Right? Now understand. 2 moles of A gives 1 mole of B. 1 mole of A gives 1 by 2 moles of B. X moles of A gives X by 2 moles of B. So I'll say these are the total moles of B present in the container at equilibrium. Similarly, P plus X by 2. These are going to be the total moles of this product C present in the container at equilibrium. Right? Is this clear to everyone? Let me know once in the chats. Quickly. Let me know once in the chats quickly, people. Everyone with the thumbs ups. Yeah? Perfect. Let me give you one more example. A plus 3 times B. It gives 2 times C. This is the reaction, for example. Try to understand now. Try to understand. What do we do? Let's assume at time t is equal to 0, we have got A moles of this reactant present in the container. We have got, for example, B moles of this particular reactant in the container. For example, there is no C present in the container initially, right? Now, my dear students, what is going to happen? A will start reacting with B and will lead to the formation of C. When the reaction starts, A and B will start to react and they will lead to the formation of C. Let me assume when equilibrium is established in the reaction at that point of time, for example, out of A moles of reactant, let's assume X moles of reactant A. Let's assume out of A moles of this particular reactant, X moles reacted with B. So I'll be left with A minus X moles. I'll be left with A minus X moles of this particular reactant at equilibrium. Now tell me one thing. Use the stoichiometry. Since 1 mole of A reacts with 3 moles of B, if 1 mole of A reacts with 3 moles of B, so X moles of A will react with 3X moles of B. And I had taken B, out of B, 3X is reacting, so I'll be left with B minus 3X moles of this particular reactant at equilibrium, right? Now, my dear students, 1 mole of A gives 2 moles of C. So X moles of A will be giving 2X moles of C. So I got the moles of each reactant product present in the container at equilibrium. Let me know once quickly in the chat if all the things are super clear to you. Everyone, people. Everyone. This is something which is really very important, right? To get the moles of each reactant product at equilibrium. Once you get to know how do we calculate the moles of each reactant product at equilibrium, you can easily calculate Kp, Kc for any reaction. I'm telling you that. Yeah? Now let me show you how do we calculate the Kp and Kc exactly. If you got clear with this, and by the way, which method I'm teaching you right now? I'm teaching you the first method, the mole method, right? Now guys, let's get to know the calculation of Kp and Kc with the help of mole method. Try to understand. I'm marking the heading as calculation of Kp and Kc by mole method. I'll be giving you only one example to understand this, then we'll do the questions directly. And I'm damn sure you can easily solve the question. Try to understand, guys. For example, I have got a reaction. A gas, or let me make it like this, 2 times A gas in equilibrium with B gas plus C gas. Try to understand every single thing. First of all, this reaction will be taking place in a closed container whose volume, for example, is V liters. Whose volume is V liters, right? Now, for example, my dear students, I need to calculate Kc for this reaction. I need to calculate Kc for this particular reaction. What is Kc? How do we write the expression for Kc? It has to be concentration of B present in the container at equilibrium raised power stoichiometric coefficient, that's 1. Concentration of C at equilibrium raised power 1 divided by concentration of A at equilibrium raised power stoichiometric coefficient, that's 2. Right? What do we need to calculate? We need to calculate Kc. Can we say in order to calculate Kc of this reaction, we need the concentration of each reactant and product at equilibrium. We need the concentration of each reactant and product at equilibrium. Now, if you ask me what is concentration, number of moles per unit volume. So, in order to get the concentration of each reactant and product at equilibrium, what do we need? We need the moles of each reactant and product present in the container at equilibrium. Once we get the moles of each reactant and product at equilibrium, just divide them by the total volume of the system. We'll be getting the concentration. That's all. Now have a look. For example, at time t is equal to 0, we have got A moles of this reactant. So this will be 0, this will be 0. Let's assume at equilibrium, out of A moles of reactant, X moles got converted. So I'll be left with A minus X moles of reactant. Now use the stoichiometry. 2 moles of A gives 1 mole of B. 1 mole of A gives 1 by 2 moles of B. X moles of A gives X by 2 moles of B. Similarly, X by 2 moles of C. So can you let me know what did I calculate? I got the moles of each reactant and product in the container at equilibrium. Do I need the moles or I need the concentration? I need the concentration. I got the moles of each reactant product at equilibrium. Now, I'm going to get the concentration of each reactant and product at equilibrium. How do we convert moles into concentration? Moles are supposed to be divided by total volume. Total volume of the system is V liters. So if I divide this particular term, A minus X, if I divide it with V, if I divide this particular term with V, if I divide this particular term with V, what did I get? Just say it. What did I get? What are these terms now? Are these moles or these are concentrations? These are concentrations of each reactants and products present in the container at equilibrium. These are concentrations at equilibrium. If you got the concentrations, you're done. You're done, right? So get the Kc value. So Kc for this particular reaction has to be equal to concentration of B at equilibrium is X by 2V. Concentration of C at equilibrium is X by 2V. So it makes it X by 2V, X by 2V. So X square divided by 4V square in the numerator. In the denominator, it's concentration of A ka square. Concentration of A at equilibrium, that's A minus X divided by V ka square. So V square got cancelled out. So I would say Kc value will be equal to X square divided by 4 multiplied by A minus X square. So my dear students, you are not supposed to remember this result. No, don't remember it. It is just, you should be able to make this result. You should be able to make this result. So this is how you calculated Kc for the given reaction. First, get the moles of each reactant product, divide by total volume, you'll be getting the concentrations. Write the expression for Kc, that's all. Agreed? Yes or no in the chats, quickly. And one thing which I'm sure you guys did not observe. If you look at this particular reaction, can you just tell me what is the delta Ng for the reaction? Can you tell me what is the delta Ng for the reaction? Number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactants, that's also 2. So 2 minus 2 is 0. Delta Ng of the reaction is 0. And that reaction whose delta Ng is 0. For that reaction, Kp and Kc will be equal, right? That means Kp for the reaction should also be equal to this. Kp for the same reaction should be also equal to X square divided by 4 into this. Now, you must be thinking how Kp will come out to be this. Let's try to understand how do we get Kp for the same reaction. Have a look, guys. What was the reaction? The reaction was like this. 2 times A gas in equilibrium. Try to understand. This is again important. B gas plus C gas. This was the reaction, right? My dear students, tell me one thing. At time t is equal to 0, we had A moles of reactant, 0 moles of product, 0 moles of product. Now at equilibrium, we were left with A minus X moles of A. Similarly, X by 2 moles of B and X by 2 moles of C, right? This is something which we already did. We calculated the moles of each reactant product present in the container at equilibrium. What do we have to calculate? We have to get the value of Kp. How do you write the expression for Kp? Start with the product. Partial pressure of B at equilibrium raised by stoichiometric coefficient 1. Partial pressure of C at equilibrium raised by stoichiometric coefficient 1 divided by partial pressure of A at equilibrium raised by stoichiometric coefficient, that is 2, right? Perfect. Now guys, if I ask you, when equilibrium was established in this reaction, when equilibrium is established in the reaction, how many gases do we have in the container in which the reaction is taking place? How many gases? We'll be having 3 gases present in the container. These are the moles of gas A present in the container at equilibrium, moles of gas B in the container at equilibrium, moles of gas C in the container at equilibrium. So can I say at equilibrium we have got a gaseous mixture? At equilibrium there is a gaseous mixture in the container. There are some moles of gas A in the container. There are some moles of gas B in the container. There are some moles of gas C in the container as well. So what do we have? We have got a gaseous mixture present in the container at equilibrium. Let's assume that the total pressure of the gaseous mixture at equilibrium, that is Pt. Pt represents total pressure. It represents total pressure of what? of gaseous mixture. Where? At equilibrium. Okay. Now guys, one thing which is clear. Total pressure of the gaseous mixture at equilibrium. It is not only due to A, it's not only due to B, not only C. All the three gases would have contributed towards the total pressure of the mixture at equilibrium. And I would say total pressure of the mixture at equilibrium will be equal to contribution made by gas A towards the total pressure plus contribution made by gas B towards the total pressure plus contribution made by gas C towards the total pressure at equilibrium. As per Dalton's law, the total pressure of the mixture is the sum of partial pressures. What is PA? Either you call it as partial pressure of A, or you can say this is the contribution made by gas A towards the total pressure of the mixture at equilibrium. Right? Okay, tell me one more thing. If you remember, how do we calculate the partial pressure? Partial pressure of A at equilibrium. As per Dalton's law, it used to be equal to total pressure of the mixture multiplied by mole fraction of the gas. Right? This is how you calculate partial pressure basically. So we have to calculate Kp. For Kp, we need partial pressures of ABC at equilibrium. To get the partial pressure of ABC at equilibrium, what do I need? Total pressure and mole fraction of A. Try to understand. At equilibrium, we have got these many moles of reactant, these many moles of product B, these many moles of product C in the container at equilibrium, right? Now, if I ask you, how many total moles are there in the container at equilibrium? You'll say at equilibrium, A minus X plus X by 2 plus X by 2. When you add them up, the value comes out to be A. These are the total moles present in the container at equilibrium. These are the total moles of the gaseous mixture at equilibrium. Now do one thing. If I divide A minus X by A, if I divide X by 2 by A, if I divide this X by 2 by A, what did I get? What was A minus X? These were moles of reactant, moles of gas A in the container at equilibrium. You divided the moles of gas A by the total moles. You divided the moles of gas B by the total moles. You divided the moles of gas C by the total moles. Can I say I got the mole fraction of each reactant product at equilibrium? These are basically the mole fractions now. These are the mole fractions of each reactant product at equilibrium. And mole fraction is to be multiplied by total pressure. For example, the total pressure of the mixture at equilibrium is PT. So, if I multiply A minus X by A by total pressure at equilibrium, what do I get? This is something which you call as partial pressure. This is the partial pressure of a reactant at equilibrium. Similarly, X divided by 2A multiplied by PT. This is the partial pressure of product B at equilibrium. Similarly, X divided by 2A multiplied by PT. This is the partial pressure of product C at equilibrium. Right? And my dear students, once you got the partial pressures, you just have to put the values of these partial pressures here in this expression. So, what do you think I'll get? Try to understand. What do you think I'll get? I'll say Kp is equal. Partial pressure of B at equilibrium is this. Partial pressure of C at equilibrium is this. So, this into this. How much it will be? It will be X into X, X square. PT into PT, PT square. Divided by 2A to A. 4A square. This is the numerator. Denominator. Partial pressure of A ka square. Partial pressure of A is A minus X ka square. Multiplied by, it will be PT ka square. Divided by A ka square. Perfect. Let's see what all terms will get cancelled out. PT square cancelled out. A square cancelled out. Look at the value of Kp. Kp value is again coming out to be X square divided by 4 multiplied by A minus X square. Look at this particular expression. Look at this particular expression. Kp is coming out to be X square divided by 4 into A minus X square. For the same reaction, Kc was coming out to be the same. X square divided by 4 into A minus X square. And it's proved. I told you already, for any reaction whose delta and G is 0, Kp and Kc for that reaction will be equal. And you understood exactly how Kp and Kc are coming out to be equal for the reaction whose delta and G is 0. Right? My dear students, my point is not that. My point is simple. Remember the steps to be followed to calculate Kc. Remember the steps to be followed to calculate Kp. Whenever you want to calculate Kc, get the moles of reactant product at equilibrium. Divide them by the total volume. Get the concentrations. And use in the expression of Kc. When you want to calculate Kp, get the moles of each reactant product at equilibrium. Divide them by the total moles present in the container at equilibrium. Get the mole fraction. Multiply each mole fraction by the total pressure of the mixture at equilibrium. Get the partial pressure. Once you get the partial pressure of each reactant and product, use it in the expression of Kp. You're done. Sorted. right? Let's try to use all these concepts in the questions, and let me see exactly whether you will be able to solve these questions or not. Look at the question. Look at the question. Let's try to solve few questions first. See guys, as far as the question is concerned, we are given the reaction, and the reaction is A gas plus B gas. It's in equilibrium with 2 times C gas. Understand how exactly I'm going to solve the question. As far as the question, it's mentioned that 2 moles of A, 1 mole of B, and 1 mole of C are placed in a 10-liter vessel. So volume of the container in which the reaction takes place, that's 10 liters, right? So we have got 2 moles of A, we have got 1 mole of B, and already as per question, there is 1 mole of C already present in the container, right? There is 1 mole of C already present in the container. Now, as per the question, when the reaction starts, finally, equilibrium is established. Equilibrium is finally being established in the reaction. If the final concentration of C is 0.2 molar, what does that mean? We know when equilibrium is established in the reaction, the moles of reactant and product, they become fixed. The concentration of reactant product, it becomes fixed. I'm given with the final concentration of C. That means I'm given with the concentration of C at equilibrium, which is equal to 0.2 molar. This is something which I'm given. Now guys, the same procedure. For example, at equilibrium, out of 2 moles of A, X moles reacted with B. So I'll be left with 2 minus X moles. Now 1 mole of A reacts with 1 mole of B. So X moles of A would have reacted with X moles of B. So I had taken 1 out of 1, X moles are reacting. So I'll be left with 1 minus X moles of B in the container at equilibrium, right? Now 1 mole of A gives 2 moles of C. So X moles of A are going to give me 2X moles of C. Already there was 1 mole. Now apart from that 1 mole, 2X moles of C are being formed. So what did I get? These are the moles of each reactant products present in the container at equilibrium, right? My dear students, just tell me one thing. If I divide all these terms by total volume in liters, what do I get? This is the concentration of C present in the container at equilibrium. Concentration of C present in the container at equilibrium, which is 1 plus 2x divided by 10. As per the question, it's already given to us as 0.2. 0.2 means 2 by 10. 10 cancelled. X value will be 0.5. So first of all, I got the value of X. After getting the value of X, put the value of X in all these terms over here. So I would say at equilibrium, 2 minus 0.5 is 1.5. 1.5 divided by 10, 0.15. This is the actual concentration of A in the container at equilibrium. 1 minus 0.5. 0.5 divided by 10, 0.05 molar. This is the concentration of B in the container at equilibrium. 1 plus 2x by 10. 1 plus 2x by 10 is 0.2. So 0.2 molar. This is the concentration of product C in the container at equilibrium. Since we got the concentration of each reactant product, what was I supposed to calculate? Kc. How do I write the expression for Kc? It's concentration of C at equilibrium raised for stoichiometric coefficient, that's 2, divided by concentration of A at equilibrium raised for stoichiometric coefficient 1, concentration of B at equilibrium raised for stoichiometric coefficient, that's 1. Now, my dear students, all these terms we already have. All these terms we have calculated. So, Kc from here will be equal to concentration of C, that is 0.2, equilibrium raised for 2. Concentration of A at equilibrium, 0.15 raised for 1, multiplied by 0.05. Now, it's a matter of calculation. Calculate it, get the value of Kc, that's all. So, first step of question is done and dusted, and I'm damn sure you can easily solve this sort of a question from now on. Say yes or no in the chats quickly. Say yes or no in the chats quickly, my dear students. Yeah? Perfectly done. Now look at this particular question. We are given the reaction X plus Y. It gives 2 times Z. This is the reaction. Initially at time t is equal to 0, 1 mole of X 1.5 moles of Y, and 0.5 moles of Z were taken in a 1 liter vessel. Allowed to react. At equilibrium, the concentration of Z was 1 molar. The equilibrium constant of the reaction is given to us as x by 15. We are supposed to get the value of x. Similar type of question, guys. Now, first of all, initial moles are given. Calculate the moles of each reactant product at equilibrium. Let's assume out of 1 mole of x, for example, x moles reacted. So I'll be left with 1 minus x moles of this reactant. Now 1 mole of x reacts with 1 mole of y. So x moles of x reacts with x moles of y. I had taken 1.5. Out of 1.5, x moles are reacting. So I'll be left with 1.5 minus 6. Now 1 mole of x gives 2 moles of z. X moles of x will give 2x moles of z. Already there were 0.5. Some new 2x moles of z would have got formed. Right? Moles of each reactant product present in the container at equilibrium. Now, my dear students, volume of the vessel is 1 liter. So divide by 1, divide by 1, divide by 1. So I think I got the concentration of each reactant product present in the container at equilibrium. Now it's mentioned that concentration of Z at equilibrium is 1 molar. But we know concentration of Z at equilibrium, that is 0.5 plus 2x. That's equal to 1. So it has to be 2x is equal to 0.5. So x value will be 0.25. This is the value of x. X is 0.25. Now you got the value of x. Perfect, you got the value of x. Put the value of x here. 1 minus 0.25. 0.75 molar. 1.5 minus 0.25. So 1.25 molar. 0.5 plus 2x. That's 1 molar. So what did I get? Concentration of x at equilibrium. Concentration of y at equilibrium. Concentration of z at equilibrium. If you got the concentration of each reactant product present in the container at equilibrium, write the expression for Kc. Kc expression will be equal to concentration of Z, which is 1, raised power, stoichiometric coefficient 2, divided by concentration of X at equilibrium, 0.75, raised power, stoichiometric coefficient, that's 1. Concentration of Y at equilibrium, 1.25, raised power, stoichiometric coefficient, that's 1. And as per the equation, this value is equal to x upon 15. My dear students, don't you think we got one equation and one unknown? Don't you think we got one equation and one unknown? Can't you get the value of x from here? Isn't it damn simple? So x value after solving, it comes out to be 16. Let me know once in the chats if this type of question is also done and dusted. Quickly. Quickly, everyone. Let me move on to one more. Let's see exactly what this question is. Just read the question carefully. On starting with 1 mole of HI in a 2 liter container, calculate the concentration of each species at equilibrium if Kp for the decomposition of HI is 16. First of all, do you know the decomposition reaction of HI? It is 2 times HI gives H2 gas plus I2 gas. This is the decomposition reaction of HI. I hope you already know it. Yeah? My dear students, first of all, as per the question is concerned, Kp for the reaction is equal to 16. Correct? Try to understand one thing. What is the delta Ng for this reaction? Number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactant, which is again 2. So 2 minus 2 is 0. Delta Ng for the reaction is 0. If delta Ng for the reaction is 0, that means Kp has to be equal to Kc. Kp has to be equal to Kc. The question is almost done. Now guys, initially at time t is equal to 0, as per the question, we are starting with 1 mole of HI in the container. So this has to be 0, this has to be 0. This reaction is taking place in a container whose volume is 2 liters. Now at equilibrium, out of 1 mole of HI, let's assume X moles reacted. So I'll be left with 1 minus X moles of HI in the container. 2 moles of HI gives 1 mole of H2. 1 mole of HI gives 1 by 2 moles of H2. X moles will give x by 2 moles of H2. Even this is x by 2. So I got the moles of each reactant product present in the container at equilibrium. Divide the moles by the total volume. Total volume is 2 liters. So 2 divided by 2 divided by 2. So I got the concentration of each reactant product present in the container at equilibrium. This is the concentration. If you got the concentration of each reactant product present in the container at equilibrium, can't you write the value of Kc? Can't you write the expression of Kc? Concentration of H2 at equilibrium, which is x by 4. Concentration of I2 at equilibrium, again x by 4. So it's x squared divided by 4, 4 that's 16, divided by concentration of Hi at equilibrium, which is 1 minus x divided by 2, whole raised power 2. Right? So this value will be equal to x square divided by 16, and this is 1 minus x square divided by 2 2s are 4. So while solving, what do I get? While solving, what do I get? There's a bit of calculation needed here, and you have to be super fast in the calculation as well. So my dear students, we got to know Kc value is coming out to be, it's going to be x square divided by 4 multiplied by 1 minus x square. And Kc already you know that's 16, right? So this x square divided by 4 into 1 minus x square, can't I write it like this? X divided by 2 multiplied by 1 minus x whole square is equal to 16. So I get x divided by 2 minus 2x is equal to 4. So I'll be getting x is equal to 8 minus 8x, or you can say 9x is equal to 8. So from here, you'll be getting the value of x. X is 8 by 9. X is 8 by 9. So you got the value of x. You got the value of x. What was I supposed to calculate? I was supposed to calculate the concentration of each species at equilibrium. Now, if I ask you, what is the concentration? If I ask you, what about the concentration of Hi at equilibrium? Concentration of Hi at equilibrium. How much that is? That is 1 minus x by 2. 1 minus x divided by 2. So which is 1 minus 8 by 9 whole divided by 2. So 9 minus 8. So 1 by 9 is going to be 1 by 18. So this is the concentration of Hi in the container at equilibrium. Concentration of H2 present in the container at equilibrium will be equal to x by 4. X by 4, right? X by 4. X value already you know, that's 8 by 9, and there is 4 in the denominator. So it's 8 divided by 9, 4, 36 mole. This is the concentration of H2 in the container at equilibrium. Similarly, concentration of I2 in the container at equilibrium will be again x by 4, so 8 by 36 mole. So let me know once in the chats if every single thing is clear till here. Yeah? These were the 3 things which you were supposed to calculate, that's all. Correct, guys? Clear to everyone? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Look at one more. 1 mole of N2, 3 moles of H2 are placed in a 1 liter vessel. Find the concentration of NH3 at equilibrium. If equilibrium pressure is 1 atm and equilibrium constant Kc is 4 by 27. Again, one simple question only, but calculation will be needed. As per the question, the reaction is, you know, when N2 reacts with H2, it leads to the formation of NH3. So this has to be the reaction. This has to be the reaction. As per the question, we have got 1 mole of N2, 3 moles of H2 placed in a container. So 0 moles of NH3 would have got formed. Now at equilibrium, out of 1 mole of N2, let's assume that X moles reacted. So I'll be left with 1 minus X. Now 1 mole reacts with 3 moles. X moles would have reacted with 3X moles. So I'll be left with 3 minus 3X moles of H2 in the container at equilibrium. 1 mole gives 2 moles. So X moles gives 2X moles. I got the moles of each reactant product present in the container at equilibrium, right? Volume of the container is 1 liter. If I divide all these terms by 1, I'll be getting the concentration. Basically, I got the concentration of each reactant product in the container at equilibrium. So let me just write the expression of Kc. Kc expression is equal to concentration of NH3 at equilibrium, which is 2x, raised power stoichiometric coefficient, which is 4x square, divided by concentration of N2 at equilibrium, which is 1 minus x, raised power stoichiometric coefficient. Concentration of H2, which is 3 minus 3x, raised power stoichiometric coefficient, right? And this Kc value, as per the question, That is given to us as 4 by 27. Now, how do we calculate it? How do we calculate it? Let's see. So first of all, this 4 and 4 got cancelled. So in the numerator, you got x square divided by. Now, if I take this 3 out, 3 here, 3 here, if I take 3 common, 3 will come out as 3 cube. 3 cube means 27. 3 cube means 27. You'll be left with 1 minus x, and here will be 1 minus x ka cube, which makes it 1 minus x raised power 4, right? Is equal to 1 upon 27. So 27 gets cancelled here also. So you got x square divided by 1 minus x raised power 4 is equal to 1. Now, how do I solve it? Again, simple. You can write it as x divided by 1 minus x ka square whole raised power 2 is equal to 1. Correct? We can do it like this. Now, tell me one thing. Take the root on both the sides. It's going to be x divided by a square plus b square minus 2ab is equal to 1. Right? A square plus b square minus 2ab. So, finally, it's going to be x is equal to 1 plus x square minus 2x, or you got x square minus 3x plus 1 is equal to 0. My dear students, we got a quadratic equation. You got the quadratic equation. Since you got the quadratic equation, can't you find its roots? What are its roots? Its roots are x values basically. And that x you have to calculate basically by solving minus b plus minus root of b square minus 4ac divided by 2. You'll be getting the value of x. Once you get the value of x, put it here in these values. You'll be getting the exact concentration of each reactant and product present in the container at equilibrium. That's all. Perfect. Here you'll be getting two values of x. Here you'll be getting two values of x. Then you have to see exactly, after putting both the values in these terms, you'll have to see which one satisfies it. For example, one of the x value comes out to be 2. 1 minus 2 is minus 1, which is not possible, right? So you have to see the possible correct value. You'll be getting two values of x. Perfect. Put one value, try to satisfy all these terms. Put another value, try to satisfy all these terms. That particular value which satisfies everyone, that's going to be the value of x. Yeah? Perfect. Is it clear? Is it clear? Quickly. Can you solve all these questions from now onwards if they are asked? Perfect, guys. Perfect. Let's move on. Let's move on. For example, you have got a question like this. You have got a question like this. For the reaction, N2 plus 3 times H2 gives 2 times NH3. The partial pressure of N2 and H2 are 0.8 and 0.4 atm at equilibrium. The total pressure of the system at equilibrium is 2.8 atm. Calculate Kp for the reaction. It's one simple question, please. See how I'm going to approach this question. My dear students, the reaction is N2 gas plus 3 times H2 gas. It is in equilibrium with 2 times NH3 gas. Now, first of all, if I ask you, initially at time t is equal to 0, there will be only reactants present in the container. There will be no product. When the reaction starts, moles of reactants will keep on decreasing. Moles of products will keep on increasing. Then there will be a time when equilibrium will be established in the reaction. Right? When the moles of reactants and products will become constant. You tell me one thing, at equilibrium, what all things will be there in the container? At equilibrium. What all at equilibrium? Tell me quickly. At equilibrium, what all substances will be there in the container? You tell me in the chats quickly. Quickly, guys. Exactly. At equilibrium, there will be some moles of N2 left in the container. There will be some moles of H2 left in the container. There would have been some moles of NH3 formed in the container. So I must say, there will be 3 gases present in the container at equilibrium. Some moles of N2, some moles of H2, and some moles of NH3. So 3 gases are there in the container at equilibrium. So basically, at equilibrium, we have got a gaseous mixture. At equilibrium, we have got a gaseous mixture. There are some moles of N2 left in the container, some moles of H2 left in the container and some moles of NH3 which have got formed in the container at equilibrium, right? All the three. Now tell me one thing. Can I say we have got a gaseous mixture present in the container? Absolutely. The total pressure of this gaseous mixture as per the question. The total pressure of the gaseous mixture as per the question. That's given to me as 2.8 atm. Now you tell me the total pressure of the mixture as per Dalton's law is equal to the sum of partial pressure, right? I'll say total pressure is equal to partial pressure of N2 at equilibrium plus partial pressure of H2 at equilibrium plus partial pressure of NH3 at equilibrium. This is equal to 2.8. Partial pressure of N2 is given 0.8. Partial pressure of H2 is given 0.4, which makes it 1.2. So partial pressure of NH3 we can easily calculate as 1.6 atm. Correct? We got the partial pressure of NH3 present in the container at equilibrium. Yeah. Now, if you got all the things, what were we supposed to calculate? Kp. Write the expression for Kp. Kp is nothing. It is partial pressure of NH3 at equilibrium raised to the power its stoichiometric coefficient. That's 2 divided by partial pressure of N2 present in the container at equilibrium raised power stoichiometric coefficient 1 and partial pressure of H2 present in the container at equilibrium raised power 3. Now, put all the values. This particular term is 1.6 raised power 2 whole divided by partial pressure of N2 was how much? Partial pressure of N2 at equilibrium was 0.8 and partial pressure of H2 at equilibrium is 0.4 ka square. When you solve it, the value comes out to be 50. When you solve it, the value comes out to be 50, right? Now, my dear students, if I ask you what are going to be the units of Kp? Units of Kp. Pressure is given in atm. Kp units are atm raised by delta Ng. Delta Ng for the reaction. Number of moles of gaseous products, which is 2, minus number of moles of gaseous reactant, which is 4. So 2 minus 4 makes it minus 2, right? So this is going to be the Kp for the reaction which we were supposed to calculate. Yeah? So let me know quickly if all these things are super clear to you. Quickly, guys. Yeah? Quickly, everyone. Everyone in the chats. Will you be able to solve these sort of questions from now on? Perfect. Wonderful. Wonderful, guys. Now, let's move on then. Let's move on. Let's move on to this particular question. It might confuse you. This particular question might confuse you. The question is if the total pressure at equilibrium for the following reaction is 2 atm. So basically a reaction is given and it's said that the reaction is at equilibrium, right? And the total pressure of the mixture at equilibrium is given. Then calculate the volume fraction of Cl2 at equilibrium. My dear students, do remember one simple thing which will solve everything. Let's have a look. Do remember one thing. At constant pressure and temperature, just remember one thing. At constant pressure and temperature, mole fraction of gas is something which you call as volume fraction of gas. At constant pressure and temperature, whatever will be the mole fraction of gas, that's something which is going to be same as the volume fraction of gas. What does that mean? For example, imagine that you have got two gases present in the container. You have got two gases present in the container, gas 1 and gas 2. Right? Now, this particular gaseous mixture, for example, it's present at constant pressure and temperature. It is present at constant pressure and temperature. At constant pressure and temperature, whatever will be the mole fraction of gas 1, same is going to be the volume fraction of gas 1. Whatever is going to be the mole fraction of gas 2, same is going to be the volume fraction of gas 2. Right? Same is going to be the volume fraction of gas 2. So whenever they ask you to calculate the volume fractions, understand you have to calculate mole fraction basically. Right? Perfect. Now guys, try to understand what is given in the question. As per the question, we are given with a reaction and the reaction is very simple. PCl5 gas is in equilibrium with PCl3 gas plus Cl2 gas. This is the reaction which is given to us, right? If the total pressure at equilibrium for the following reaction is 2, So in the question, it's mentioned that the total pressure of the mixture at equilibrium is equal to atm, right? Then calculate the volume fraction of Cl2 at equilibrium. Calculate the volume fraction of Cl2 at equilibrium. So first of all, tell me one thing. Volume fraction of Cl2 at equilibrium. Can I say that is basically mole fraction of Cl2 at equilibrium? So you actually have to calculate mole fraction of Cl2 at equilibrium. Correct? Now use the same procedure which we keep on doing all the time. So at time t is equal to 0, let's assume that we have got A moles of PCl5. So this is 0, this is 0. So at equilibrium, out of A moles of reactants, X moles got converted into products. So I'll be left with A minus X moles of PCl5 at equilibrium, right? Yes? Now guys, try to understand. 1 mole of PCl5 gives 1 mole of PCl3. So X moles should give me X moles. 1 mole gives 1 mole. So X moles should give me X moles. So this particular term, these are the moles of PCl5 in the container at equilibrium. These are the moles of PCl3 in the container at equilibrium. These are the moles of Cl2 in the container at equilibrium, right? Yes? Now guys, try to understand. If I ask you how many total moles we have in the container at equilibrium, total moles in the container at equilibrium will be equal to A minus X plus X plus X, which makes it A plus X. These are the total moles in the container at equilibrium, right? So I'll be dividing with the total moles. A plus X here, A plus X here. So what did I get? I got the mole fraction of each reactant product. Mole fraction of Cl2 at equilibrium is X divided by A plus X. And mole fraction of Cl2 only we have to calculate. So we got to know that we have to get the value of X divided by A plus X. So this particular value we have to calculate actually, right? But the question is not done yet. The question is not done yet. Try to understand. We got the mole fraction of each reactant and a product. The total pressure of the mixture is also given. If I multiply these mole fractions by the total pressure, what do I get? I'll be getting the partial pressures of each reactant product at equilibrium. So partial pressure of PCl5 at equilibrium, it's A minus X divided by A plus X multiplied by total pressure, that's 2. Similarly, multiply this term by 2. It's 2x divided by A plus X. Similarly, it's going to be 2x divided by again A plus X. So what did we get? We basically got the partial pressures of each reactant and product in the container at equilibrium, right? We got the partial pressures. Now what exactly we are going to do? Since as per the question, the value of Kp is given to us. Kp is given to us as 0.2. How do I write the expression for Kp? It's partial pressure of PCl3, which is 2x divided by A plus X, multiplied by partial pressure of Cl2, 2x by A plus X, which is basically 2x divided by A plus X ka square, right? Whole divided by partial pressure of PCl5, which is 2 multiplied by A minus X divided by A plus X. And this value is equal to 0.2. 0.2 makes it 2 by 10, right? So one of the A plus X, one of the A plus X cancel, right? So what do I get finally? This is 2 to the 4, 4 by 2 is 2. So this is going to be 2x square divided by A plus X. Just a second. This is A plus X and here it's A minus X. A plus X, A minus X is A square minus X square is equal to 2 by 10. So 2 got cancelled. Now it's a matter of calculation only. So you got X square divided by A square minus X square. It's equal to 1 by 10. So which means 10x square is equal to A square minus X square, which means 11x square is equal to A square, which tells you that X has to be equal to A divided by root 11. So X value is equal to A by root 11. Put the value of X here in this expression. So it's X. X is A by root 11. Whole divided by. It's A plus A by root 11. So A cancelled out in both the ways. So finally, what do I get? I get 1 by root 11 divided by 1 plus 1 upon root 11. So the final answer which you'll be getting, how much is that? It's going to be 1 divided by root of 11 plus 1. So this is the final answer. This is the mole fraction. This is the volume fraction of Cl2 present in the container at equilibrium. Quickly guys, let me know in the chats if all these things are clear. Let me know in the chats if all these things are clear. You should be able to solve these questions now. Yeah? Perfect, guys. Wonderful. Now, there is one more concept. There is one more concept. My dear students, usage of pressure instead of moles in the gaseous phase reaction. What is meant by this? How to use it exactly? It's very simple. First of all, tell me one thing. For example, you have got the reaction like this. A gas. For example, it gives B gas plus C gas. Let's assume that this reaction has to take place in a container which is closed. This reaction, for example, has to take place in a container which is closed, right? For example, I'm assuming that volume and temperature is constant. If volume and temperature of the system is constant, if the volume and temperature of the system is constant, tell me one thing. As per ideal gas equation, PV is equal to nRT. If volume and temperature is constant, can I say pressure is directly proportional to moles? What does that mean? That means at constant volume and temperature, if moles will be increasing, pressure will be also increasing. If moles will be decreasing, pressure will be also decreasing. Now try to understand. Initially in the container, there will be only a reactant, right? Initially in the container, there will be only reactant. There will be some moles of A in the container. There will be some moles of A in the container initially. There will be no moles of product, right? So whatever will be the total pressure of the container at time t is equal to 0, that will be only due to this A, right? Now, my dear students, when the reaction will proceed, the moles of A will decrease with time. The moles of B and C will increase with time, right? If the moles of A is decreasing with time, that means pressure due to A will also decrease with time. Pressure due to B and C will increase with time. Moles of reactant is decreasing. Pressure due to reactant is decreasing. And the proportion in which moles of reactant will be decreasing, in the same proportion, pressure of the reactant will be decreasing. Since the moles of the products are increasing with time, the proportion in which, the ratio in which the moles of products will be increasing, in the same ratio, pressure due to products will be also increasing. What I'm trying to say is, moles of reactants decrease with time. Pressure due to reactant also decrease with time. Moles of product increase with time. Pressure due to product also increase with time, right? The ratio in which the moles of reactant decrease with time. In the same ratio, pressure due to reactant decrease with time. The ratio in which moles of products increase with time. In the same ratio, pressure due to product will increase with time, right? So, what exactly we are going to do? We are going to do one simple thing. We are going to treat pressure in the similar way as we used to treat the moles. That's all, right? We are going to, my dear students, we are going to treat the pressure in the similar way as we used to treat the moles. Just try to understand. At time t is equal to 0, there will be only A in the container. Let's say pressure due to A is P naught. Pressure due to B and C will be 0 and 0, right? At equilibrium, for example, imagine that this is not pressure. Imagine these are moles. Just imagine. So this has to be at equilibrium P naught minus X. 1 mole gives 1, X gives X, 1 gives 1, X gives X. So these are not actually the moles. These are actually the pressure, right? So this is P naught minus X ATM, for example. This is X ATM. This is X ATM. So you directly got the partial pressures. Pressure due to A at equilibrium. Pressure due to B at equilibrium. Pressure due to C at equilibrium, right? Perfect. So if I ask you the total pressure of the mixture at equilibrium, how much that is going to be? Total pressure of the mixture at equilibrium. The mixture contains 3 gases at equilibrium, right? Total pressure of the mixture at equilibrium will be equal to P naught minus X plus X plus X, which makes it P naught plus X. So basically, total pressure of the mixture at equilibrium will be the sum of the partial pressures, right? Simple. Right, people? Let's try to take one more example so that you can solve all the questions, basically. I'm taking the example as 2 times A gas. It is an equilibrium. For example, 3 times B gas plus 5 times C gas. This is the reaction. This is the reaction. For example, at time t is equal to 0, pressure due to A is P naught. This is 0, this is 0. Now treat the pressure in the similar way as we treat moles, right? So at equilibrium, it has to be P naught minus X, right? 2 moles gives 3 moles. 1 mole gives 3 by 2. X moles gives 3 by 2x. Similarly, this has to be 5 by 2x. So what is this? This is the pressure due to A at equilibrium. This is the pressure due to B at equilibrium. This is the pressure due to C at equilibrium. Right? Now, my dear students, all these things, whatever I'm telling you, usage of pressure instead of moles. Let's see exactly how do we solve the questions based on the same concept. Try to understand what I'm going to say. Yeah? Right? So first of all, as per this particular question is concerned, we are given the reaction. The reaction is AB3 gas. AB3 gas. AB3 gas is in equilibrium with AB2 gas plus half of B2 gas. This is the reaction, right? Now, my dear students, at time t is equal to 0, it's mentioned that if the initial pressure of AB3 is 900 torr, initial pressure of reactant is 900 torr. So this is 0, this has to be 0 because initial conditions are there. Now, my dear students, at equilibrium, right? What will be the pressure due to AB3? It has to be 900 minus x. 1 mole gives 1, so x gives x. 1 gives 1 by 2, x gives x by 2. What did I get? This 900 minus x atm, this is x atm, and this is x by 2 atm. I got the pressure due to each reactant and product in the container at equilibrium. Now, as per the question, total pressure of the mixture at equilibrium, that's given to me as 1000 torr. And the total pressure of the mixture will be the sum of these partial pressures at equilibrium, which is just going to be 900 minus x plus x by 2. This value is equal to 1000. So x got cancelled. I would say x by 2 is equal to 100. So x value will come out to be 200 atm. So dear students, you got the value of x, which is 200 atm. You got the value of x, 200 atm. So 900 minus 200, 700. X values 200. 200 by 200, 100. This is atm. This is atm. This is atm. What was I supposed to calculate? What was I supposed to calculate? Quickly. What was I supposed to calculate? Kp. If I'm supposed to calculate Kp, write the expression of Kp is equal. Partial pressure of AB2 at equilibrium, that is 200. Raise power, stoichiometric coefficient. Partial pressure of B2 at equilibrium, that's 100. Raise power, stoichiometric coefficient. Divided by partial pressure of AB3 at equilibrium, that's 700 atm. Raise power, stoichiometric coefficient. So this is 10. This is 2000 by 700, which comes out to be 20 by 7. So 20 by 7, and its units are atm raised by delta Ng. Delta Ng for the reaction is moles of gaseous products. 1 plus 1 by 2 makes it 3 by 2. 3 by 2 minus 1 is 1 by 2. So this is the Kp for the reaction. So let me know once in the chats quickly if this is again super duper clear to you. Quickly, guys. Clear, guys? Yeah? All right. Let's try to have a look on one more question. Look at this particular question carefully. Yeah? Look at this particular question. The total pressure at equilibrium is 30 atm. And the partial pressure of HNO2 at equilibrium is 2 atm. Calculate Kp. The total pressure of the mixture at equilibrium, is equal to 30 atm, right? And the partial pressure of what? Partial pressure of HNO3 at equilibrium is equal to how much? Is equal to 2 atm. Calculate Kp for the reaction. The reaction is 4 times HNO3. It is in equilibrium with 4 times NO2 gas plus 2 times H2O gas plus O2 gas. This is the reaction that's given. Now, my dear students, try to use the same procedure. Start with P naught. This has to be 0. This has to be 0. This has to be 0. Now, you tell me at equilibrium, it has to be P naught minus X. Now, 4 moles gives 4 moles. 1 mole gives 1 mole. So, X will give X moles. Similarly, this is going to be X by 2 and this is going to be X by 4. Right? Now, as per the question, partial pressure of HNO3 at equilibrium. Partial pressure of HNO3 at equilibrium is P naught X. So P naught minus X is basically equal to 2. Right? Total pressure of the mixture at equilibrium. Total pressure of the mixture will be equal to P naught minus X plus X by 2 plus X by 4. And as per this is the total pressure of the mixture. It's given to me as 30 atm. P naught minus X. P naught minus X. This term already you know that's 2. So 30 minus 2 makes it 28. Right? So I'll be getting X plus X by 2 plus X by 4 is equal to 28. Correct? Take the LCM of denominators. That's 4. So it's going to be 4x plus 2x plus x is equal to 28. Now tell me, 4 to 6, 7. So it's going to be 7x divided by 4. This is going to be equal to 28. So 7, 1, 7, 4. So x value will come out to be 16 atm. You got to know the value of x, 16 atm. If x is 16, that means P naught minus x is equal to 2. So P naught is equal to 2 plus x, which comes out to be 18 atm. So P naught value you got, x value you got. What am I supposed to calculate? Kp. The question is done, right? So P naught minus x, 18 minus 16, that's 2 atm. So partial pressure of HNO3, right, at equilibrium is 2 atm. X value 16. So partial pressure of NO2, that is 16 atm. X by 2. So 16 by 2, that's 4. This is 4. 16 by 4, this is 16 divided by 2, which comes out to be 8. So this whole term is 8 atm, right? This whole term, 16 by 4, that's 4 atm. So basically, I got the partial pressure of each reactant product in the container at equilibrium, right? Yes? Right, guys? Perfect. If you got the partial pressure of each reactant in product, can't you calculate the value of Kp now? Isn't it simple? Isn't it simple, guys? Quickly. See now, when the data of pressures will be given at that point of time, you should be using this particular one, right? And it is particularly mentioned, valid at constant volume and temperature. So my dear students, there comes one more topic, that is degree of dissociation, right? So what exactly we are doing right now? We are doing the Kp and Kc calculations. And right now, few minutes back, I showed you calculation of Kp and Kc with the help of mole method, right? Now, we are exactly going to see the calculation of Kp and Kc with the help of degree of dissociation method as well. So before going into that, let's get to know what this degree of dissociation is all about. My dear students, this degree of dissociation, it is represented by alpha. It is represented by alpha. Yeah. Now, dear students, degree of dissociation, it is defined as the fraction of reactant which gets dissociated into product. The fraction of reactant which gets dissociated into product is something which we call as degree of dissociation. Now, the point is, what is meant by that? What is that? Let's have a look. My dear students, for example, I'm writing a reaction. A gives B plus C. Let's assume this is one reaction which is at equilibrium, for example. First of all, I'm assuming degree of dissociation of this reaction is alpha, right? Degree of dissociation of this particular reaction is alpha. Now, my dear students, how do you define alpha basically? Alpha is defined something like this. Number of moles of reactant which gets dissociated into products. So those moles of reactants which get converted into products. Those moles of reactant which get dissociated basically. Divided by initial moles of reactants taken. Divided by initial moles of reactants taken. Those moles of reactants which get dissociated into products divided by initial moles of reactants taken. Now, for example, have a look. Let's assume at time t is equal to 0, we have got A moles of reactant. So this has to be 0, this has to be 0, right? Now, my dear students, alpha has to be equal to number of moles of reactant which got dissociated, for example. Let's say number of moles of reactant which got dissociated divided by initial moles of reactants are equal to A. So from this particular equation, can you let me know how many moles of reactants are getting dissociated? A alpha moles of reactants are getting dissociated into products. My dear students, I took A moles of reactants. Now at equilibrium, I can say out of A moles of reactants, A alpha moles of reactants are getting converted into products. So I'll be left with A minus A alpha moles of reactants, right? Simple. Now use the stoichiometry. 1 mole of A gives 1 mole of B. So from A alpha moles, you'll be getting A alpha moles of B. Similarly, 1 mole of A gives me 1 mole of C. From A alpha moles, you'll be getting A alpha moles of C. So over here, if I ask you what these terms are, if I ask you what these basically terms are, you will say these are the moles of reactants and products which are there in the container at equilibrium. As simple as that, right? And rest of the things you already know. If these are the moles, divide the moles by the volume, get the concentration at equilibrium, get the Kc value, right? Similarly, Kp also you can calculate. Let me give you one more example so that it becomes properly clear to you. One more example I'm going to give you. For example, you are given with a reaction like this. 2 times A is in equilibrium with 3 times B plus 5 times C. It is one reaction which is at equilibrium, for example. I'm assuming that the degree of dissociation of this particular reaction, the degree of dissociation alpha, right, is equal to number of moles of reactants which get dissociated into products, which get converted into products, divided by initial moles of reactants taken, right? Now you tell me one thing. At time t is equal to 0, I'm starting with A moles of reactants. This has to be 0. This has to be 0, right? So can I say alpha is nothing? It is number of moles of reactants which are getting dissociated divided by initial moles are A. So number of moles of reactant which got dissociated, that is A alpha, right? So I can say initially I took A moles of reactant. Now out of A moles, A alpha moles are getting converted into products. So I'll be left with A minus A alpha moles of reactant at equilibrium, right? Now 2 moles of A gives 3 moles of B. So 1 mole of A gives 3 by 2 moles of B. So A alpha moles of A are going to give me 3 by 2 multiplied by A alpha moles of B. Similarly, 2 moles of A gives 5 moles of C. So 1 mole of A gives 5 by 2 moles of C. So A alpha moles are going to give me 5 by 2 multiplied by A alpha moles of C. So what are these terms basically? These are the moles of reactants and products present in the container at equilibrium, right? Perfect. One last example so that we can start the questions directly. Let's say you have got the reaction like this. N2 gas plus 3 times H2 gas. For example, it's in equilibrium with 2 times NH3 gas. Correct? My dear students, imagine that you have got A moles of N2 in the container. You have got B moles of H2 in the container. And you have got 0 moles of NH3 at time t is equal to 0. Right? At time t is equal to 0. Perfect. Now, for example, if I ask you how many moles of N2 are left in the container at equilibrium, I'll say out of A moles of N2, A alpha moles would have reacted. So I'll be left with A minus A alpha moles of N2 in the container. So 1 mole of N2 reacts with 3 moles. So A alpha would have reacted with 3 times A alpha. So I'll be left with B minus 3 A alpha moles of H2 in the container. 1 mole of N2 gives 2 moles of NH3. So A alpha is going to give me 2 A alpha. So I got the moles of each reactant product in the container at equilibrium, right? Very simple and basic. Now, my dear students, if you got to know how to write, if you got to know exactly how to write the moles of reactant product at equilibrium in terms of alpha, then you should be able to solve these sort of basic questions. Let's try to understand what the question is. Calculate the Kp for dissociation of 1 mole of PCl5. So as per the question, you're dissociating PCl5. And do remember PCl5, it gets dissociated into PCl3 gas. And with this, you'll be writing Cl2 gas. Correct? Now, if I ask you at time t is equal to 0, we have got A moles of reactants. And it's mentioned that we are starting with 1 mole of reactant. So A value has to be 1. Correct? So this is going to be 0. Even this is going to be 0. Perfect. Before doing the question, do remember percentage dissociation. Percentage dissociation is always equal to degree of dissociation multiplied by 100. Percentage dissociation is always equal to degree of dissociation multiplied by 100. So as per the question, it's mentioned that 20% reactant is being dissociated. So 20% reactant is being dissociated, right? So what is the value of alpha from here? I'll say alpha is nothing, it will be 0.2. I'm given it percentage dissociation. I converted it into degree of dissociation. Now you already know out of A moles of reactants, how many moles of reactants got dissociated? Out of A moles, I must say, out of A moles, A alpha would have got dissociated. So I'll be left with A minus A alpha moles of reactant. Now 1 mole of PCl5 gives 1 mole of PCl3. From A alpha, you get A alpha. Even this is A alpha. Correct? Now my dear students, A value you know, alpha value you know. So get the moles of reactants and products present in the container at equilibrium. A is 1. 1 minus 0.2, that is 0.8. Right? 1 into 0.2, that is 0.2. So this is also 0.2. So what is the 0.2, 0.8, 0.8? These are the moles of reactants products present in the container at equilibrium. Right? What are we supposed to calculate? We are supposed to calculate Kp. If I ask you what Kp is basically, how do we write the expression for Kp? It's partial pressure of PCl3. It is partial pressure of PCl3 at equilibrium raised for stoichiometric coefficient 1. Partial pressure of Cl2 at equilibrium raised for stoichiometric coefficient 1 divided by partial pressure of PCl5 at equilibrium raised for stoichiometric coefficient 1. So in order to calculate Kp, what do I need? I need the partial pressure of each reactant product at equilibrium. What did I calculate? I calculated the moles of each reactant product at equilibrium. Now you tell me one thing. If I ask you how many total moles are there in the container at equilibrium? 0.8 plus 0.2 plus 0.2, which makes it 1.2. So I'm dividing here with total moles at equilibrium. So what did I get? Moles of PCl5 left in the container at equilibrium divided by total moles. So this is mole fraction of PCl5 at equilibrium. Mole fraction of PCl3 at equilibrium. Mole fraction of Cl2 at equilibrium. Now multiply these mole fractions by the total pressure. Total pressure is 1 atm. So multiplying them with 1, I'll be getting the partial pressure of each reactant product. So partial pressure of PCl3 at equilibrium will be 4 by 3. This will be 1 by 6. This will be 1 by 6. So I got partial pressure of each reactant product present in the container at equilibrium. Now, if you got the partial pressures of each reactant product at equilibrium, put all these values in this particular expression and you'll be getting the value of Kp. Done and dusted, right? Simple. Yeah. You can use the mole method as well. The choice is all yours. Right? The choice is all yours. So basically, the x which we used in the mole method, here instead of x, what are we using? Instead of x, we are using A alpha. So x is basically equal to A alpha in short. Yeah. There it used to be A minus x. Here it is going to be A minus A alpha. I hope you can relate it properly now. I hope you can do that. You can relate it properly. Now guys, one more question for example. Look at this particular question. The degree of dissociation of N2O4 at 1.5 atm and 25 degrees centigrade is 0.25. So basically as per the question, degree of dissociation is given to me as 0.25. Calculate Kp for the reaction. The reaction is N2O4 gas is in equilibrium with 2 times NO2 gas, right? The degree of dissociation is alpha. Now start the same procedure again. Let's assume that we have got A moles of N2O4 in the container at initial conditions. So this is going to be 0. Now tell me at equilibrium, out of A moles of reactant, I must say A alpha moles got converted into products. So I'll be left with A minus A alpha. 1 mole gives 2 moles. From A alpha, you get 2 times A alpha. So I would say 2 times A alpha moles of NO2 would have got formed in the container at equilibrium. What do we need to calculate? I basically need to calculate Kp value. What is Kp? Kp is nothing, it is partial pressure of NO2 at equilibrium, raised power stoichiometric coefficient, that's 2, divided by partial pressure of N2O4 at equilibrium, raised power stoichiometric coefficient 1. So I need what exactly? I need the partial pressure of NO2 and N2O4 at equilibrium. Now, my dear students, tell me one thing. How many total moles are there in the container at equilibrium? The total moles present in the container at equilibrium is A minus A alpha plus 2 times A alpha, which makes it A plus A alpha. These are the total moles present in the container at equilibrium. Now, if I divide this term by the total moles, A plus A alpha, if I divide this term by the total moles, A plus A alpha, can I say I got the mole fraction of each reactant product in the container at equilibrium? Absolutely. Multiply these mole fractions by the total pressure at equilibrium. Total pressure is 1.5. So multiplying here with 1.5 and multiplying here with 1.5. So what did I get? Mole fraction multiplied by total pressure. That gives me what? Partial pressure. So this is the partial pressure of N2O4 at equilibrium, partial pressure of NO2 at equilibrium. Right? Now put the values. So if you take A common in the numerator, A common in the denominator, the partial pressure of N2O4 at equilibrium, how much it comes out to be? It comes out to be 1 minus alpha multiplied by 1.5 divided by 1 plus alpha. Similarly, A common, it's going to be 2 into 1.5 is 3. So it's going to be 3 times alpha divided by 1 plus alpha. This is the partial pressure of NO2 in the container at equilibrium. Now, my dear students, if I ask you, do you know the value of alpha? Yes, you know the value of alpha. Put the value of alpha in both these expressions. You'll be getting the exact value of partial pressure of reactant product. And if you get the partial pressure of reactant product at equilibrium, put the values here in this expression, get the Kp value. Isn't it simple and basic, my dear students? Right? Isn't it simple? Nothing to do. It is just the matter of calculations. It is just the matter of calculations. Let me know in the chats quickly. One question I'm giving you as the homework. You can let me know its answer in the comment section afterwards. This is the similar type of question which you can solve, you are going to solve, and please do let me know its answer in the comment section of the video, because the question is based on the same parameters, right? Okay, perfect. Let's move on to one more topic. That's again simple only. Calculation of degree of dissociation through vapor density measurement. Before talking about the calculation of degree of dissociation using vapor density measurement, or let me directly go into this. Here we have got two expressions basically. Let me not derive those expressions because derivation is not needed. I'll be giving you the expressions and I'll show you how to use those expressions in the questions. Derivation right here, it's not needed, right? It's not needed. My dear students, try to understand one important thing which I'm going to say. Try to understand one important thing which I'm going to say. How do you define the vapor density of a gas? How do you define the vapor density of a gas? Vapor density of a gas, it is the ratio of density of the gas to that of density of hydrogen gas, provided the gas and H2 gas, they are present at same pressure and temperature. Right? That's something I assume you know. Even leave the definition aside. Have you ever heard this particular relation? Molar mass of a gas is equal to 2 times the vapor density of the gas. Have you ever come across this? I have discussed this in mole concept as well, if you remember. Whenever vapor density of a gas is given, you just have to multiply vapor density by 2. You'll be getting what? You'll be getting molar mass of the gas. Right? Perfect. Now try to understand. For example, I've got the reaction like this. AN in equilibrium with, or let me write it simply like this, just a second. A gives N times B. A gives N times B. Stoichiometric coefficient here is 1, here it is n. I'm assuming that n value is greater than 1. I'm assuming that n value is greater than 1, right? I'm assuming that n value is greater than 1. That means n can be 2, it can be 3, it can be 4. Imagine n is 2. Imagine n is 2. So at that point of time, can I say one particle of A is giving basically 2 particles? N can be 3. So one particle is giving 3 particles, one particle is giving 4 particles, one particle is giving 5 particles, 6 particles. So is this the case of dissociation or association? One particle is giving more than one particle. So this is the case of dissociation. This is the case of dissociation, right? My dear students, the degree of dissociation alpha can be calculated with the help of one result. What is that result? I'm directly giving you the result, right? No need of derivation over here. It is capital D minus small d divided by small d multiplied by n minus 1. Now, understand these terminologies. What are this capital D's? What are the small d's? Tell me one thing. Initially, at time t is equal to 0. Initially, at time t is equal to 0. Do we have only one gas in the container? That is gas A. Do we have only one gas in the container? Absolutely, that's gas A at time t is equal to 0. Right? Vapor density of gas A at time t is equal to 0. Vapor density of reactant at time t is equal to 0. That is denoted by capital D, which is something I call as theoretical vapor density. Theoretical vapor density, or just to remember, you can call it as vapor density of reactant at T is equal to 0, right? Perfect. Now tell me one thing. With time, when the reaction will start, what will happen? The moles of A will start to decrease. The moles of B will start to increase. Then equilibrium will get established. At equilibrium, will you find only one gas in the container or there'll be 2 gas? Tell me. Tell me. Quickly. Will there be only one gas in the container or there'll be 2 gases? At equilibrium, there'll be 2 gases in the container. So there will be a gaseous mixture present in the container at equilibrium. I'm assuming that the vapor density of that gaseous mixture is represented by small d. So small d is something which you call as experimental vapor density. Experimental vapor density, or you can call it as vapor density of the mixture at equilibrium. Vapor density of the mixture at equilibrium, right? Now, dear students, tell me one thing. Capital D stands for theoretical vapor density or vapor density of reactant. Vapor density of reactant. Vapor density is equal to molar mass divided by 2. So, vapor density of reactant, it actually has to be equal to molar mass of reactant by 2. Vapor density of reactant, it has to be equal to molar mass of reactant divided by 2. Similarly, D. D is the vapor density of the mixture of gas at equilibrium. Right? So at equilibrium, you have got a mixture of gas. Perfect. So vapor density of the gaseous mixture has to be equal to molar mass of the gaseous mixture divided by 2. And you already know molar mass of gaseous mixture is something which you call as average molar mass. So average molar mass of the mixture divided by 2. That is basically your small d. That is basically your small d. That is basically your small d. Do remember, in case of dissociation, capital D is greater than small d. In case of dissociation, capital D is greater than small d. What is alpha? Degree of dissociation. Capital D, what is it? It is theoretical vapor density. Vapor density of reactant at time t is equal to 0. Vapor density of equilibrium mixture. What is N? What is N basically here? N stands for the number of moles. The number of moles of product. The number of moles of product produced from 1 mole of reactant. Reduced from 1 mole of reactant. For example, let's say you go to the reaction like this. A gas, it gives 2 times B gas plus 3 times C gas. If I ask you what is the N value for this, tell me from 1 mole of reactant, how many moles of products you are getting? From 1 mole of reactant, you're getting 5 moles of product. So N value here is 5. N value here is 5. If I ask you, for example, you have got the reaction like this, PCl5 gas, it is an equilibrium with PCl3 gas plus Cl2 gas. So 1 mole of reactant is giving me 2 moles of product. So N value has to be equal to. N value has to be equal to. For example, you have got the reaction like this, 2 times A gas in equilibrium with 4 times B gas plus 5 times C gas. Can you let me know what is the N value for this reaction? N value? Can you let me know what is the N value for this reaction? Quickly. Quickly, guys. Say it's simple. I'll say 2 moles of A, 2 moles of reactant is giving us 4 plus 5, 9 moles of products. Right? So 1 mole of reactant has to give us 9 by 2, 4.5 moles of products. So can I say these are the moles of products which are produced from 1 mole of reactant? I would say N value is equal to 4.5. N value is equal to 4.5. Right? Simple. Now guys, here we have got a graph basically. Here we have to, in case of dissociation, let me show you one graph as well. Right? Let me show you one graph as well. The graph is between capital D divided by small d versus alpha. Capital D by small d versus alpha. Now you tell me one thing. What is the relation? We know alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Right? So I can say n minus 1 multiplied by alpha is equal to capital D divided by small d minus 1. Just doing simplification, cross multiplication, nothing else. Capital D divided by d is equal to 1 plus n minus 1 into alpha. This capital D by small d I'm plotting along y-axis. Alpha I'm plotting along x-axis. This term is something which you call a slope m. In between the sign is plus. And this is your intercept c. Y is equal to mx plus c. This is going to be a straight line. Y is equal to mx plus c. Now my dear students, if I ask you, what about the slope of this curve? You'll say slope of this curve is basically m. And m is nothing, it is n minus 1. Right? If I ask you what about the intercept, the distance from here to here, intercept is c and c value is nothing, that's 1. This is the graph which you have to remember. Right? You'll be getting a question from this graph as well. I'll let you know in some time. Okay? I'll let you know in some time. So in case of dissociation, how do we get the alpha? Alpha is capital D minus small d divided by small d multiplied by n minus 1. Capital D is basically molar mass of reactant by 2. Small d, experimental vapor density. Or you can call it as vapor density of the mixture at equilibrium, which is molar mass of the mixture divided by 2. Right? Now, there is one more case, which is the case of association. Till now, I was talking about dissociation only. Now, let's talk about the case of association. How do I represent the association? For example, you have got the reaction like this. N times A gas in equilibrium with B gas. I'm assuming N value is greater than 1. For example, N value is 2. N value is 2. What does that mean? For example, N value is greater than 2. Let's say N value is greater than 1. For example, N value is 2. That means 2 moles of A are giving me 1 mole of B. If N is 3, 3 particles of A are giving me 1 particle of B. 4 particles of A giving 1 particle of B. So more than one particle of A are associating to form what? More than one particle of A are associating to form 1 particle of B. Here, if I define N, what is N here? N over here is equal to number of moles of reactant particles, number of moles of reactant species, reactant particles associated to form 1 mole of product. Right? How many moles of reactants are associating to form 1 mole of product? That defines N here, right? So over here, alpha does not represent degree of dissociation. Alpha represents degree of association. It represents degree of association. It represents degree of association and it will be equal to, as per formula, capital D minus small d divided by small d multiplied by 1 divided by n minus 1 minus 1. 1 by n minus 1. It has a derivation as well. I'm not showing the derivation. That's of no need to you. You just need to remember this result. In case of association, alpha has to be equal to capital D minus small d divided by small d multiplied by 1 by n minus 1. Yeah? Right? Now, my dear students, already you know what is capital D. Heretical vapor density. Vapor density of reactant at time t is equal to 0, which is molar mass of reactant by 2. What is small d? Vapor density of mixture at equilibrium, right? Which is molar mass of the mixture divided by 2, right? What is alpha? Degree of association. What is n? N stands for the number of moles of reactants, the number of moles of reactants associating to form 1 mole of product, right? To form 1 mole of product. I hope this is clear to you. If this is clear to you, let me show you few questions so that you can understand it properly where it's utilized. Understand, guys. As far as the question is concerned, the reaction that's given to us, that's N2O4 gas. It is in equilibrium with 2 times NO2 gas. First of all, tell me whether this is the case of dissociation or association. Tell me that. Quickly. Is this the case of dissociation or association? See, one particle of A is giving you 2 particles of B, right? So one particle is dissociating into 2 particles. So I would say this is the case of dissociation and n value is equal to 2. You got the value of n. You got the value of n. So you got to know n value is equal to 2. So n value you got. Perfect. The vapor density of N2O4 and NO2 mixture at equilibrium. So vapor density of the mixture at equilibrium. Vapor density of mixture at equilibrium, that's represented by small d. That's given to me as 30, right? Calculate the percentage dissociation. Calculate the percentage dissociation. What is percentage dissociation all about? It is equal degree of dissociation multiplied by 100. So basically, how get the value of alpha? You need to get the value of alpha. Once we get the value of alpha, multiply with 100, get the percentage dissociation. Now, guys, try to understand. Then this is the case of dissociation. In case of dissociation, alpha is equal to capital D minus small d divided by small d multiplied by n minus 1, right? So alpha is equal. What is capital D basically? Capital D is theoretical vapor density of reactant, which is molar mass of reactant divided by 2. What is the molar mass of reactant? Molar mass of reactant, when you calculate, it's 92 divided by 2. So the value comes out to be 46. Do you see? It is 46, this is 30. I told you capital D is greater than small d in case of dissociation, right? So capital D is 46, small d is 30 divided by 30 multiplied by n minus 1. So 2 minus 1. When you solve it, the value approximately comes out to be 0.52. So what is this 0.52? This is the degree of dissociation. Am I supposed to calculate degree of dissociation or percentage dissociation? Percentage dissociation is 0.52 multiplied by 100, 52%. So what does this 52% mean? It means after the completion of 52% of the reaction, after the completion of 52% of the reaction, equilibrium would have got established in the reaction, right? Once 52% reactant gets converted into product, at that point of time, equilibrium got established in the reaction. Yeah? Clear? Is it clear? Let me know once in the chats. I can move on then to one more question. Okay, look at this question, guys. Perfect. Look at this question now. In the reaction, vapor density of the mixture means small d. Vapor density of mixture at equilibrium, that's small d. Vapor density of mixture is reduced to half. Half of what? Half of initial vapor density. Half of theoretical vapor density. It's mentioned that vapor density of the mixture has reduced to half. Half of what? Half of theoretical vapor density. Half of initial vapor density of reactant basically, which is capital D. So small d is equal to capital D by 2. When equilibrium is achieved. If the percentage dissociation is 25%, if percentage dissociation is 25, alpha is going to be 25 by 100, that's 1 by 4, right? Calculate how many moles of B will be formed at equilibrium on starting with 2 moles of A. on starting with 2 moles of A. So as per the question, at time t is equal to 0, we have got 2 moles of A. This will be 0. Let's say degree of dissociation is alpha, right? So at equilibrium, out of 2 moles, how many moles would have got converted? How many moles would have got dissociated? Out of 2, I'll say 2 alpha moles would have got dissociated. So I'll be left with 2 minus 2 alpha. These are the moles of A left in the container at equilibrium. Now 1 mole gives n moles. So from 2 alpha, you get 2 times alpha multiplied by n. Or let me make it simple for you. If this is confusing a bit, let me make it a bit simple for you. Let's say initially at time t is equal to 0, you have got A moles of reactant, which is 2. This is 0. Degree of dissociation is alpha. So at equilibrium, out of A moles, I'll be left with A minus A alpha moles of A. Now 1 mole of A gives n moles of B. So from A alpha, you get n times A alpha. What do I need to calculate basically? I need to calculate the number of moles of B formed at equilibrium. And you got to know number of moles of B formed at equilibrium, that has to be equal to n times A alpha. Alpha value we know, that's 1 by 4. A value we know, that is 2, right? But n we do not know. N we do not know. So we have to get the value of n first. So how you are going to get the value of n? You know, since this the, how do we get the value of n? Try to understand. Already we know alpha is equal to capital D minus small d divided by small d multiplied by n minus 1, right? Perfect. Now guys, try to understand. Alpha is 1 by 4 is equal to capital D, I'm writing as such. Small d is capital D by 2. So d minus d by 2 comes out to be d by 2. Small d, which is d by 2. N minus 1. So this term got cancelled. What do I get? I get 1 by 4 is equal to 1 divided by n minus 1. Or you can say n minus 1 is equal to 4. Or n value simply you got to know as 5. That's all. Right? Yeah? N value is equal to 5. If n value is equal to 5, if n is equal to 5, A value is already 2, alpha is equal to 1 by 4, the value comes out to be 2.5. So I would say 2.5 moles of B have got formed at equilibrium, which is something which we're supposed to calculate, right? Is it clear? Is it clear to everyone? Wassim, stop writing nonsense stuff in the chats, right? Students are concentrating, let them concentrate. Or else I have the option of blocking you as well, whosoever you are. Quickly guys, so let me know in the chats if this particular question is clear to you or not. So we got to know 2.5 moles of B have got formed at the end. Like, at the end means at equilibrium. All right. One more question for you. Can you give it a try? Can you give this question a try? Look at it. We are given the graph between capital D by D versus alpha. Capital D by D versus alpha. Okay. Now, my dear students, the graph is given like a straight line. Its slope is given. Slope is equal to 2. Already I told you slope is nothing, it's n minus 1. So basically, n minus 1 value is equal to 2. This is something which is given to me. N minus 1 value is equal to 2. Yeah, you can get the hell out of here. Yeah. Go wherever you want. Let me tell you, we do not appreciate this nonsense in the chats. This is something which happens on different channels. Right here, whosoever comes, they come here to study, right? We do not appreciate this nonsense content and all. Perfect? Like to make you laugh, etc., etc. I don't believe in that. I believe in content. Just if you want content, come here. Otherwise, don't. Okay? This is for everyone. Perfect. So capital D by D versus alpha. Its graph is given to us and its slope is given to us as 2. If slope is 2, that means n minus 1 value is 1. Now try to understand what is given in the equation. Calculate the percentage dissociation. So first of all, we have to calculate the percentage dissociation. Percentage dissociation is degree of dissociation multiplied by 100. Right? So basically, we need to get the value of alpha. Calculate the percentage dissociation when experimental vapor density is small d, becomes equal to half of theoretical vapor density when it becomes capital D by 2. Right? When it becomes capital D by 2. Now, my dear students, you know, alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Right? So, from here, alpha will be equal. Capital D, I'm writing as such. Small d is capital D by 2. So, d minus d by 2 makes it d by 2 divided by. Small d is d by 2. N minus 1 value is already equal to 2. Right? So, this term gets cancelled. The value comes out to be 1 by 2. So, alpha value you got to know is 1 by 2, 0.5. If alpha is equal to 0.5, get the percentage dissociation. So, I would say percentage dissociation of reactant at equilibrium will be equal to alpha is 1 by 2, multiply it with 100, the value comes out to be 50%, right? So I would say 50% of reactant would have got dissociated at equilibrium. Is this clear to everyone? Let me know once in the chats quickly. Everyone, guys, everyone, quickly in the chats. Let me know if all these things are super clear to you. Yeah? Perfect. So this was your degree of dissociation in terms of what? This was your degree of dissociation in terms of vapor density. Now, dear students, there is one more topic, one small topic. That's the reaction quotient. What is reaction quotient and where it is used? See, guys, it is a very simple topic. For example, you have got the reaction. The reaction is N1A plus N2B. It gives N3C plus N4D. Let's assume it's a balanced chemical equation, right? Do you remember how we used to write the equilibrium constant expression? For example, Kc. How do we write Kc expression? Concentration of C at equilibrium raised by stoichiometric coefficient. Concentration of D at equilibrium raised by stoichiometric coefficient divided by concentration of A at equilibrium raised by stoichiometric coefficient and concentration of B at equilibrium raised by stoichiometric coefficient. This is how we write the expression, the equilibrium constant expression. Correct? What is special here? When we write the equilibrium constant expression, we need the concentrations of reactants and products at equilibrium. First of all, we are supposed to calculate the concentrations of reactants and products at equilibrium, right? Then put it here, get the value of Kc. Now I'm going to write the similar expression. But I'm going to write it like this. Concentration of C raised by N3, concentration of D raised by N4, concentration of A raised by N1, and concentration of B raised by N2. My dear students, what is the difference between these two expressions? Here I'm using all the concentrations of reactants and products at equilibrium. Here I am using the concentrations of reactants and products at any stage apart from equilibrium. Here I am using the concentrations of all the reactants and products at any stage but apart from equilibrium. This expression I'll be calling as reaction quotient. Right? So what is the only difference between Kc and Qc? All the terms here, all the concentration terms here. These are the concentrations of reactants and products at equilibrium. And these are the concentrations of reactants and products at any stage apart from equilibrium. Correct? Now, my dear students, tell me one thing. Tell me one thing. If, for example, Qc is equal to Kc, if Qc of a reaction is equal to Kc, if Qc is equal to Kc, that means concentration of C is equal to concentration of C at equilibrium. Concentration of D is equal to concentration of D at equilibrium. What does that mean? That means the reaction is already at equilibrium. The reaction is already at equilibrium. If Qc is equal to Kc, the reaction is already at equilibrium. My dear students, do you remember when we started the chapter equilibrium, I told you, equilibrium is the most stable state of the system. It is the most stable state of the system. Every reaction, every reversible reaction wants to attain equilibrium as soon as possible. Right? As soon as possible. What does that mean? That means every reaction wants to have its QC. every reaction wants to have its QC to become equal to Kc as soon as possible. Because once Qc becomes equal to Kc, then only we can say reaction is at equilibrium, right? So every reaction wants to make its QC same as that of Kc. Perfect. That means if the QC value of the reaction is less than that of Kc, what will happen? What will happen? QC will try to increase its value such that it becomes equal to Kc. And once it becomes equal to Kc, the reaction is at equilibrium. Yeah? Okay. Again, I'm telling you, every reaction wants to be at equilibrium as quick as possible, because equilibrium is the most stable state of the system, right? So every reaction wants to have its QC to be equal to Kc. Once QC becomes equal to Kc, that means the reaction is at equilibrium, right? Now you tell me one thing. If by chance QC of a reaction is less than Kc, if QC is less than Kc, what QC will do? What QC will do? If QC is less than Kc, that means the reaction is not at equilibrium. So QC will try to increase its value. How QC will try to increase its value? How QC will try to increase its value? QC can increase its value if numerator increases, denominator decreases. What is the numerator? Numerator is basically concentration of products. So concentration of products should increase, concentration of reactant should decrease. How concentration of products will increase? When the reaction shifts forward, right? Yes? When the reaction shifts, when the equilibrium shifts forward. Yes? Is this clear? Perfect. So in this particular case, it's going to be forward shift, right? Now you tell me one thing. If by chance QC is greater than Kc, is the reaction at equilibrium? No. Reaction is only at equilibrium if QC is equal to Kc. If by chance QC is greater than Kc, QC will try to decrease its value. How QC will decrease its value? QC can decrease its value. QC can decrease its value if this term decreases, numerator decreases, denominator increases. Numerator decrease means concentration of products should decrease. Concentration of products, how it will decrease? How concentration of products will decrease? When the shift will be backward. When the shift will be backward. So do remember this particular point. This is important. This is important, my dear students. Do remember this particular point. Q greater than KEQ. Q greater than KC. Backward shift favors. Q less than Kc. Forward shift favors. And Q equal to KEQ. That means the reaction is at equilibrium. And why am I teaching you this? Because I have to teach you one last topic here, that is Chatelier principle. Chatelier principle, right, is explained by this reaction quotient. Perfect? But we are not going into the details on this. We'll just study the part which is required basically to solve the questions which are related to your NEET and JEE. Okay? So what is Chatelier principle all about? Try to read its statement first. The statement is very simple. According to this principle, if any change is imposed on the system at equilibrium, first of all, if you have got a system at equilibrium, that means it is the most stable state, right? It is the most stable state. For example, you have got a system which is at equilibrium. So that means the system is present at its most stable state, right? Now, as far as this particular principle is concerned, if any change is imposed on the system at equilibrium, equilibrium will shift in such a way in which the effect of change is nullified. What does that mean? In simpler words, it means whatever you do to a system which is at equilibrium exactly does opposite of what we do to the system. See, for example, you have got the reaction which is at equilibrium, right? So maximum stable, correct? Now I'm doing some change. I'm changing the pressure. I'm changing the concentration, right? That means equilibrium will get disturbed. Stability will get disturbed, right? Will the system let that happen? the system is going to oppose what we do to the system, because the system wouldn't want to change its stability. It wouldn't want to affect its stability, right? Yeah. So in short, according to this principle, if any change is imposed on the system which is at equilibrium, equilibrium exactly does opposite of what we do, right? Whatever you do to the system at equilibrium, equilibrium is going to do opposite of what you do, so that the effect of change is nullified. So do remember this. Do remember this. According to this principle, if any change is imposed on the system at equilibrium, then the equilibrium will shift in such a direction in which the effect of change is nullified. Yes, Sadhika, this is a live class. Now, my dear students, one by one, we are going to have a look on few things. Effect of addition of reactant or product. For example, what that means. Let's say you've got a reaction at equilibrium. A in equilibrium with B. This is the reaction, for example, which is at equilibrium. Now try to understand. If the reaction is at equilibrium, I would say its QC will be equal to KEQ, which is going to be concentration of B at equilibrium divided by concentration of A at equilibrium raised for stoichiometric coefficient. Correct? Now, my dear students, since the reaction is at equilibrium, so it's at maximum stable state. For example, if I increase the amount of B, if I try to increase the amount of B, that means I'm trying to increase the numerator. That means QC value will be increasing. QC will become more than that of KC. If QC becomes more than KC, that means the system is not at equilibrium at that point of time. QC will try to bring back its value. And how QC will try to bring back its value? When numerator will decrease and denominator will increase. Numerator decreases means concentration of B should decrease. It will decrease only when the reaction moves in the backward direction. So equilibrium shifts backward. Right? So backward reaction favors. Perfect. There'll be a backward shift. Now, if you decrease the amount of A, if you decrease the amount of A, when you decrease the amount of A, QC value will increase. If QC will increase, QC will become more than KC. Then QC will try to bring back its value. QC will try to decrease its value. How will it decrease its value? If this decreases and this increases. How will this decrease? How will B decrease? Concentration of B will decrease only if backward shift happens. Right? Perfect. Similarly, on decreasing the amount of B or increasing the amount of A. When you decrease the amount of B, what happens? My dear students, when you try to decrease the amount of B, QC value will start to decrease. So QC is becoming less than that of EQ. Right? So equilibrium is disturbed. Now QC will try to bring up its value. When QC tries to bring up its value, how it will bring up its value? How will it increase its value? If B increases, how will B increase? How will concentration of B increase? When forward shift favors. So forward shift favors here also. And forward shift favors here also. Do remove these particular things, right? I hope you're getting exactly why it's happening, right? There's actual logic why on changing the amount of reactant and product. How, like, on changing the amount of reactant and product, which shift favors. I hope you got it. Perfect. So if more reactant is added or product is removed, reaction shifts forward. If reactant is removed or product is added, backward shift proceeds. There is no effect of adding a solid at equilibrium. Okay, this is one more important point. Right? When you add, since, for example, look at this particular reaction. Okay? Look at this particular reaction. My dear students, here you have got solid, here you have got solid. So if you try to increase the amount or decrease the amount of solid, what will happen to the shift? Will the shift be forward, backward, or there'll be no shift? There'll be no shift. Because this is solid. Its ectomass is unity. If its ectomass is unity, it's not in the expression of QC only. If it is not in the expression of QC, if you change its amount, QC will not change. If QC is not changing, that means nothing will happen. Yeah? I hope this point is clear. No shift. Point number 1. Now point number 2. Effect of change in pressure. Effect of change in pressure. For example, this is the reaction. Effect of change in pressure. This is the reaction. Let's assume that this reaction is happening at constant volume and temperature. Right? PV is equal to nRT. Volume and temperature is constant. Can I say at that point of time, pressure is directly proportional to moles? Absolutely. If you decrease the moles, pressure decreases. If moles are increased, pressure increases. Correct? Very simple. Now tell me one thing. On reactant side, how many moles we have? 1 plus 3. 4 gaseous moles. On product side, we have got 2 gaseous moles. So in the forward direction, are moles increasing or decreasing? Moles are decreasing in the forward direction. That means pressure is decreasing. In the backward direction, moles are increasing. That means pressure is increasing. That means pressure is increasing. So over here in this particular example, in the forward direction, pressure decreases. In the backward direction, pressure increases. Now you tell me one thing. If I increase the pressure of the system, I am increasing the pressure of the system. Equilibrium will try to decrease it. Equilibrium will try to decrease it. Equilibrium will try to decrease the pressure of the system. So it will make sure equilibrium shifts forward. It will make sure the reaction shifts forward, because in the forward direction only, the pressure is decreasing. Because it has to nullify the effect of change. See, in the forward direction, pressure is decreasing. In the backward direction, pressure is increasing. Now, if I increase the pressure, equilibrium will try to decrease it. So it will make sure the reaction shifts forward. Because in the forward direction only, pressure is decreasing. Perfect? Due to which the effect of change will be nullified. Look at the forward direction. In the forward direction, are the gaseous moles increasing or decreasing? In the forward direction, gaseous moles are decreasing. So can I say something in short? On increasing the pressure, reaction will shift in such a direction in which the total gaseous moles decreases. When you try to increase the pressure, reaction will shift in such a direction in which the total gaseous moles decreases, right? Now, there is a separate debate for that. If gaseous moles are decreasing in forward direction, the reaction goes forward. If the gaseous moles are decreasing in backward direction, the reaction goes backward. As simple as that. Perfect. Now look at this particular reaction. 1 plus 1, 2. 1, here it is 2. So in the forward direction or backward direction, are the moles changing? No. If the moles are not changing, pressure is not changing. Right? Neither in forward direction nor in backward direction. Now you change the pressure, you increase or decrease the pressure, nothing will happen. There will be no shift. So any such reaction whose delta Ng is 0, if you change the pressure, nothing will happen. There will be no shift at all. Right? There will be no shift at all. This is one more important point. Now comes to the most important point. That is effect of temperature. Try to understand, because this is very important. What happens to a reaction when you change the temperature? First of all, this is one important equation. I would want you guys to remember it directly. Log of K2 divided by K1 is equal to delta H divided by 2.303 R, 1 by T2 minus 1 by T1. My dear students, imagine that you have got a reaction at equilibrium, right? I'm assuming that when the temperature was T1, at that point of time, equilibrium constant of the reaction was K1, right? Let's assume when the temperature of the reaction, when the reaction was carried out at temperature T1, at that point of time, its equilibrium constant was K1. Now, for example, I'm changing the temperature of the reaction from T1 to T2. Let's assume the equilibrium constant changes from K1 to K2. Let's assume that. At the same time, I'm assuming that the reaction is endothermic. For example, the given reaction is endothermic. If the given reaction is endothermic, what about its delta H? For endothermic reactions, delta H value will be positive. For endothermic reactions, delta H value is positive. So this term is positive. Delta H is positive, right? Now, for example, initial temperature was T1, final temperature of the reaction is T2. Let's assume that you have increased the temperature. Let's assume that we have increased the temperature. What does that mean? That means T2 is greater than T1. Let's assume that we have increased the temperature. If we are increasing the temperature, if T2 is greater than T1, what will happen to T2 minus T1? Will T2 minus T1 come out to be positive or negative? T2 minus T1 will come out to be positive, right? And over here it is T2 minus T1. So this term is also coming out to be positive. So for the endothermic reaction, if you increase the temperature, see delta H for endothermic is already positive. Now this term, T2 minus T1, this term is also positive. So positive makes the whole term positive. So I can say log of K2 divided by K1. This term has to be positive, right? When is log of X positive? Log of X is positive only when X is greater than 1, which clearly tells me K2 has to be greater than, K1. What is K2? K2 is the equilibrium constant at temperature T2, right? So what did we do? We increase the temperature and equilibrium constant is also increasing. So do remember, my dear students, in case of endothermic reactions, when you increase the temperature, equilibrium constant increases. That means equilibrium constant is directly proportional to temperature in case of which particular reaction? In case of endothermic reaction, right? One mistake which you can do here, which I think you can do, try to understand, try to rectify that. See, my dear students, you know, equilibrium constant is actually basically the ratio of rate constant of forward to that of rate constant of backward reaction. This is the actual equilibrium constant. Rate constant of forward to that of rate constant of backward. Now we know on increasing the temperature of endothermic reaction, equilibrium constant increases. If equilibrium constant increases, does that mean Kf increases and Kb decreases? Does that mean Kf increases and Kb decreases? No, the case is not that. The case is not that. Do remember one simple thing. When you increase the temperature of the reaction, on increasing the temperature, rate constant of forward as well as rate constant of backward, both the terms increase. Rate constant of forward as well as backward reaction increases on increasing the temperature. Now what exactly are we doing? We are increasing the temperature of the reaction, of the endothermic reaction. When you increase the temperature, equilibrium constant will increase because directly proportional. Now, we know on increasing the temperature, Kf increases as well as Kb increases. Correct? If Kf also increases, Kb also increases. This term also has to increase. That means increase in the value of Kf will be more than that of increase in the value of Kb. If the increase in the value of Kf is more than that of increase in the value of Kb, then only this whole term will increase. Then only Keq will increase. So my dear students, try to remember one particular statement. On increasing the temperature, equilibrium constant of the endothermic reaction increases. And at the same time, increase in the value of Kf is more than that of increase in the value of Kb. That is the reason why overall Keq increases, right? Do remember this particular statement. This is important. Yeah, this is important. Now, same goes for exothermic. You can check for exothermic as well, right? You can check for exothermic as well. For example, I'm taking one exothermic reaction. Let's say I've got the exothermic reaction. In case of exothermic reactions, what about the delta H value? Delta H value is negative. What about the equation which we have? It is the log of K2 divided by K1 is equal to delta H divided by 2.303 R. 2.303 R, and it's T2 minus T1 divided by T1 T2. This is the equation. Perfect. Let's say we have got the exothermic reaction A gives B. Right? At temperature T1, the equilibrium constant is K1. At temperature T2, the equilibrium constant is K2. Perfect. For example, you are increasing the temperature of the reaction. If you increase the temperature of the reaction, what will happen to T2 minus T1? T2 minus T1 will be positive. So, on increasing the temperature, T2 minus T1 is coming out to be positive. Delta H is already negative. Positive, negative makes it negative. That means this whole term is negative. So, log of K2 divided by K1 value will come out to be negative. It is only possible when K2 divided by K1 is less than 1. That means K2 has to be less than K1. What was K2? What was K1? K2 was equilibrium constant at temperature T2. K1 was equilibrium constant at temperature T1. So on increasing the temperature, is the equilibrium constant increasing or decreasing? On increasing the temperature, the equilibrium constant of the exothermic reaction that decreases. That means your equilibrium constant, it is inversely proportional to temperature for which reaction? For an exothermic reaction. For an exothermic reaction. Perfect. For endo, it is directly. For exo, it is inversely. Now, again the same thing. You know, equilibrium constant is basically the ratio of rate constant of forward to that of rate constant of backward. Correct? Now you got to know, on increasing the temperature, equilibrium constant decreases. Does that mean Kf increase? Does that mean Kf decreases and Kb increases? If Keq has to increase, that means Kf should decrease, Kb should increase. But that's not the case, because I told you already, on increasing the temperature, rate constant of forward as well as backward reaction increases. Rate constant of forward as well as backward reaction increases. If the rate constant of forward is increasing, backward is increasing, then how come equilibrium constant will decrease? Equilibrium constant will decrease only. Equilibrium constant will decrease only if increase in the value of Kb will be greater than that of increase in the value of Kf. If increase in the value of Kb is more, if the denominator is increasing by more amount, then only the whole term will decrease. So this is one more important statement which I would want you guys to take a note of. Is this clear? Is this clear, guys? So this was your effect of temperature on equilibrium constant. For endothermic reactions, on increasing the temperature, equilibrium constant increases. For exo, on increasing the temperature, equilibrium constant decreases. Right? Perfect. Now, effect of addition of inert gas at constant pressure. When you add an inert gas at constant pressure, when you add an inert gas at constant pressure, what will happen due to that? Try to understand. See, guys. Just a second. Okay. So first of all, imagine that this particular reaction, the reaction which we have, just an example, the reaction which we have, assume that this reaction is taking place at constant pressure and temperature. R value is already constant, so volume is directly proportional to moles. You already know it, right? So if moles are increasing, volume is increasing. If moles are decreasing, volume will be decreasing, correct? Imagine that this particular reaction is carried out at constant pressure and temperature, right? At constant pressure and temperature. Now, for example, if this particular reaction which we have, this is the reaction which we have. I'm assuming that this reaction is at equilibrium, and this reaction is at constant pressure and temperature, right? It's carried out at constant pressure and temperature. Now, my dear students, imagine that this is the concentration of reactant at equilibrium. Imagine this is the concentration of product at equilibrium. Assume that the reaction is at equilibrium, and these are the concentrations of reactants and products at equilibrium. Now, if the reaction is at equilibrium, that means QC value has to be equal to Kc, which will be equal to concentration of this divided by concentration of this. So, in the numerator, it's B square by V square. In the denominator, it's A by V. So, the value has to be B square divided by A multiplied by 1 by V. Correct? I'm assuming that the reaction is at equilibrium. If the reaction is at equilibrium, then QC has to be equal to Kc. Correct? And this is the value exact. Now, tell me one thing. The reaction is taking place at constant pressure and temperature. Let's assume that I'm adding an inert gas in the container. Let's assume that I'm adding the inert gas in the container. If I add the inert gas in the container, are the total moles in the container increasing or decreasing? If I'm adding inert gas, that means total moles in the container are increasing. If total moles in the container are increasing, that means the volume of the system, will it increase or decrease? Volume of the system will increase. If volume of the system is increasing, what will happen to QC? QC will decrease. QC will decrease. QC will become less than Kc. If QC becomes less than Kc, equilibrium is disturbed. Can I say QC will again start to increase its value? And how QC will increase its value? When the reaction will shift in the forward direction. And the reaction will shift in the forward direction. In the forward direction are the gaseous moles increasing or decreasing. In the forward direction, gaseous moles are increasing. That means on adding inert gas at constant pressure, reaction shifts in such a direction in which the total gaseous moles increases. Right? If the gaseous moles are increasing in forward direction, it will go forward. If the gaseous moles are increasing in backward direction, it will go backward. Right? I hope this is also clear to you. Now, similarly, effect of inert gas addition at constant volume. Effect of inert gas addition at constant volume. Try to understand what exactly I'm going to say. Try to understand. Effect of inert gas addition at constant volume. So I'm assuming that this particular reaction is taking place at constant volume and temperature. Let's say volume and temperature is constant. PV is equal to nRT. Volume and temperature constant. So pressure is directly proportional to moles, right? Pressure directly proportional to moles. Yeah? Pressure directly proportional to moles. That means if moles are increasing, pressure will be increasing. If moles are decreasing, pressure will be decreasing, right? Now, try to understand what I'm going to say. Let's say at equilibrium, you have got A moles of PCl5, B moles of this, and B moles of this. These are, for example, the moles of reactants and products at equilibrium. Let's say the total moles at equilibrium is equal to NT. NT stands for total moles present in the mixture at equilibrium. Moles of A at equilibrium divided by total moles at equilibrium. This gives me the mole fraction of reactant. Mole fraction multiplied by total pressure of the mixture. It gives me the partial pressure of PCl5 at equilibrium. This gives me partial pressure of PCl3 at equilibrium, partial pressure of Cl2 at equilibrium, right? Moles of PCl5 at equilibrium divided by total moles present in the container at equilibrium multiplied by total pressure of the mixture. It gives me the partial pressure of PCl5. So basically, I have got the partial pressure of each reactant product, just to make you understand, right? And if the reaction is at equilibrium, that means QP has to be equal to KP. And how do you write the expression for KP? This into this divided by this. So it's going to be B square divided by NT square multiplied by PT square whole divided by. This is A divided by NT multiplied by PT. See what all terms will get cancelled out. See, one of the PT cancelled out. NT cancelled out. So the expression is going to be B square divided by A. It's going to be PT divided by NT. This is the final expression. Now try to understand what I'm going to say. Try to understand what I'm going to say. My dear students, this particular reaction is happening at constant volume and temperature. And at constant volume and temperature, pressure is directly proportional to moles. If moles are increasing in the container, pressure will increase. If moles are decreasing in the container, pressure will decrease. Right? For example, imagine that you are adding an inert gas in this container. If you add an inert gas in this container, are the total moles present in the container increasing or decreasing? Total moles in the container are increasing. Total moles in the container are increasing. That means the total pressure of the system will be also increasing. Since pressure is directly proportional to temperature, the ratio in which moles will be increasing in the container, in the same ratio, pressure will be increasing. In the same proportion, pressure will be increasing. So moles are increasing in the container by the addition of inert gas, due to which total pressure of the system is also increasing. So numerator increasing, denominator increasing, and both are increasing by same amount. If both are increasing by same amount, will there be any change in QP? There will be no change in reaction quotient. If the reaction quotient is not changing, will there be any shift? There will be no shift, right? There will be no shift. I hope this is clear. Yeah, I hope this is clear to everyone. Perfect. Now, one last thing here. Catalyst. What does a catalyst do? If I talk about the positive catalyst, it increases the rate of forward reaction and rate of backward reaction. Positive catalyst, it increases the rate of forward reaction and backward reaction by equal amounts. So, due to the addition of positive catalyst, rate of forward and rate of backward reaction increase by equal amounts. If the rate of forward and backward reaction is increasing, I would say equilibrium in the reaction is established a bit early, in lesser time. right? No matter what, whether the equilibrium is established in the reaction early or it takes more time, will it affect the equilibrium concentrations? It won't affect the equilibrium concentrations, right? No doubt, by the addition of positive catalyst, equilibrium comes in the reaction early. In absence of catalyst, it takes long to attain equilibrium in the reaction, right? Will that affect the equilibrium concentrations? It won't affect the equilibrium concentrations, right? No matter whether it comes early or it takes long. If equilibrium concentrations are not getting affected, that means will the equilibrium constant get affected? Equilibrium constant does not get affected. So by the addition of catalyst, equilibrium constant does not change at all. There is no effect of catalyst on equilibrium state. Equilibrium state is attained early due to the presence of positive catalyst, but nothing happens to the equilibrium concentrations. They're still the same, right? Equilibrium constant is still the same. I hope this is clear, right? So no effect of catalyst on equilibrium. One question, and with that, we'll be ending this session. And after this one question, I'll give you as a homework. Imagine that this is the reaction. Imagine that this is the reaction. As per the question, predict the direction of shift of equilibrium if more H2 is added. If you are adding more H2, in short, you are adding more H2, equilibrium will try to decrease it. It will decrease it when the reaction shifts forward. So here, shift is favored in forward direction, right? If more NH3 is added, if you add more NH3, equilibrium will in short try to decrease it. How NH3 amount will get decreased? When the reaction moves backward, right? If the temperature is increased, the reaction is endothermic. It is absorbed, endothermic, right? Endothermic. Equilibrium constant is directly proportional to temperature for endothermic reactions. If you increase the temperature, equilibrium constant increases. Equilibrium constant increases. That means equilibrium constant will increase only if the concentration of products will increase, concentration of reactants will decrease, right? So the reaction will shift forward. Equilibrium constant increases. That means forward shift, right? Inert gas is added at constant volume. Nothing will happen. When inert gas is added at constant volume, nothing happens. No shift. Inert gas is added at constant pressure. When inert gas is added at constant pressure, the reaction shifts in the direction in which the total gaseous moles increases. A few minutes back, I told you. In which the total gaseous moles increases. On the reactant side, we have got 4 gaseous moles. On the product side, 2 gaseous moles. It's going to be backward shift. Right? It's going to be backward shift. I hope all these things are clear to you. One question I'm giving you as the homework. Do let me know its answer. Okay, tell me the answer right here only. The reaction is at equilibrium at 25 degrees centigrade in a closed container. Wow, closed container means volume of the system is constant. Volume of the system is constant. So at constant volume, an inert gas, helium, is introduced. Inert gas addition at constant volume. No shift. No shift. Nothing will happen to the concentrations of reactants products. Right? No shift. Nothing will happen to the concentration of reactants. Okay. Okay, this is your homework question. Do let me know its answer in the comment section of this particular video. Right? So, my dear students, this was your chemical equilibrium, which is done and dusted. I hope you got all the concepts. Right? So, as I told you, I'll be starting this chapter from exact basics. So, the first topic, the first and the basic topic with which I shall be starting this chapter, that is going to be electrolyte. Right? You must have come across this term, electrolytes. Let's get to know what electrolytes exactly are all about. How do we classify these electrolytes? Because in this particular chapter, we have to deal only with the electrolytes. So let's get to know exactly what the electrolytes are all about. My dear students, it's very simple and basic. Try to understand the definition, then slowly we'll go towards the complex things as well. Yeah? So first of all, electrolytes are those substances which on dissolving in water dissociates into their ions. Electrolytes are basically those substances which, on dissolving in water, they dissociate into their respective ions. Any such substance which, on dissolving in water, dissociates into its respective ions, we call that substance as the electrolyte. So what is electrolyte in short? It is that substance which, on dissolving in water, dissociates into its respective ions. Right? Very simple and basic definition. Now, dear students, we classify these electrolytes basically into two types. One is strong electrolyte, one is weak electrolyte. Let's exactly get to know what strong electrolytes are and what weak electrolytes are. This is complete basics which I'm telling you. My dear students, strong electrolytes are those substances which are completely ionized, which are completely dissociated in their aqueous solution. Any such substance which dissociates completely into its respective ions, that's something which you call a strong electrolyte. For example, let's say you've got AB solid. Let's say you've got AB solid. Now you're introducing this AB solid into water, for example. I'm assuming that this AB solid, when introduced into water, let's assume that it got dissociated completely. It got 100% dissociated into its ions. So I'll be calling this particular electrolyte over here as strong electrolyte. So what is a strong electrolyte? That substance which undergoes 100% dissociation on dissolving in water, right? At the same time, if you ask me, what about degree of dissociation? What about degree of ionization for these strong electrolytes? You'll say the degree of ionization for the strong electrolytes, it's always equal to 1, right? It's always equal to 1 because the electrolyte, it gets completely dissociated into its ions. If you remember, in the chemical equilibrium, we used to call this alpha as degree of dissociation. But in this particular chapter, I'll be calling this alpha as degree of ionization. It is just the terminologies are different, but the meaning is actually same. Terminologies are different, but the meaning is same. In chemical equilibrium, we used to call it as degree of dissociation, and here I'll be calling it as degree of ionization, right? Rest, every single thing is same. Perfect. If you remember, I told you one more thing. I told you percentage dissociation. Here I'll be writing percentage ionization. Percentage ionization is equal to degree of ionization multiplied by 100, right? Now, I'm telling you a strong electrolyte, it gets 100% ionized. That means percentage ionization of the strong electrolyte is 100, which is equal to alpha multiplied by 100, right? So the value of alpha is coming out to be directly 1. As I told you, in case of strong electrolytes, the degree of ionization, it's always equal to 1, right? Again, simple and basic. Now, my dear students, you must be thinking, what are the examples of these strong electrolytes? My dear students, all the strong acids, all the strong bases, and all the water-soluble salts, they are the examples of the strong electrolyte. So whenever you see a strong acid, whenever you see a strong base, whenever you see a water-soluble salt, when you introduce them into water, they'll get 100% ionized. They'll get 100% dissociated into their ions. And any such substance which gets 100% dissociated into its ions, we call that as the strong electrolyte. So do remember, all your strong acids, all your strong bases, and all your water-soluble salts, these are the examples of the strong electrolytes, whose alpha, degree of ionization, that's equal to 1, right? At the same time, let me tell you, the general salts of alkali metals. General salts of alkali metals. For example, alkali metals, all of you must be familiar with, right? Lithium, sodium, potassium, rubidium, cesium. When you take any salt of these alkali metals, for example, you're taking the salt NaCl. It is the salt of alkali metal, right? It is the salt of alkali metal. So all the salts of alkali metals, even all the salts of NH4 positive. For example, you have got NH4Cl as the salt. Should I be calling this salt as the salt of NH4 positive? Absolutely, this is the salt of NH4 positive. And all the salts of NO3 negative, right? For example, you have got NH4NO3, NH4NO3. For example, you have got KNO3, Perfect. So these are what I'll be calling as the salts of NO3 negatives. Let me tell you, all the salts of alkali metals, all the salts of NH4 positive ions, all the salts of NO3 negative ions, these are considered to be water soluble salts, and water soluble salts are always the examples of what? These are always the examples of strong electrolytes. So these are some basic things which I would want all of you to remember. Any such substance which gets 100% ionized, which gets 100% dissociated on dissolving in water, that's something which I'll be calling a strong electrolyte. All the strong acids, all the strong bases, all the water-soluble salts, these are the examples of the strong electrolytes, right? General salts of alkali metals, general salts of NH4 positive, general salts of NO3 negative, these are all the examples of the water-soluble salts, and you know, water-soluble salts are the examples of the strong electrolytes. So I hope you guys are going to remember this from now onwards. My dear students, what about weak electrolytes? Weak electrolytes, they are not 100% dissociated on dissolving in water, right? I would say they are partially ionized. When you put a weak electrolyte in water, it does not get 100% ionized. It does not get 100% dissociated upon dissolving in water. It is partially ionized in its aqueous solution. Now you must be thinking, if it is partially ionized, its alpha value, its alpha value, will it be equal to 1? No. It will be greater than 0 and less than 1. It will be greater than 0 and less than 1. Right? And at the same time, you must be thinking, what are the examples of these weak electrolytes? My dear students, all the weak acids, all the weak bases, all the weak acids, all the weak bases, they are examples of weak electrolytes. All the weak acids, all the weak bases, they are the examples of the weak electrolytes which do not get completely ionized when we introduce them into water. What are the other examples of weak electrolytes? All the sparingly soluble salts. What are sparingly soluble salts? You'll get to know in this chapter only, but afterwards, right? All the sparingly soluble salts, these are the examples of weak electrolytes, and these are the examples of your sparingly soluble salts, right? Which are again considered to be weak electrolytes. So few things which I would want you to remember. Any substance which do not get 100% ionized in their aqueous solution, you call that as weak electrolyte. Weak acids, weak bases, sparingly soluble salts, these are all examples of weak electrolytes, right? These are all examples of weak electrolytes which do not get 100% dissociated into their ions. And these are some examples of the weak electrolytes, right? My dear students, there is one important point which I would want to mention here, right? Which I'll be using everywhere in ionic equilibrium. Let me tell you, all the weak electrolytes are considered to be, just a second. See, I'm writing a weak electrolyte. A weak electrolyte will be always in equilibrium with its ions. In this complete chapter, this is a particular statement will be following throughout. Whenever you see a weak electrolyte, weak electrolyte will be always in equilibrium with its ions. For example, if I take a weak acid, CH3COH, right? This is a weak acid, acidic acid. It's an example of weak acid. Since it's a weak electrolyte, so it's going to remain in equilibrium with its ions, and its ions are going to be CH3CO negative aqueous plus H positive aqueous, right? For example, you have got NH4OH. This is a weak base. It's a weak base. When you put it into water, right, it gets dissociated into its ions, and its ions are NH4 positive aqueous plus OH negative aqueous. Now what I'm telling you is, this NH4OH, it's a weak base. If it is a weak base, it's going to remain in equilibrium with its ions. So in short, whenever you see a weak electrolyte, you'll be always considering that the weak electrolyte is in equilibrium with its ions. This is one important point which I would want you guys to remember from now on, right? Strong electrolyte, it gets completely ionized. It is not going to remain in equilibrium with its ions. Whereas when I'll be talking about the weak electrolyte, in its aqueous solution, do remember, it will be always in equilibrium with its ions. I hope this is super clear to everyone, right? So this was just the basics, right? Now we are going to understand the actual stuff over here. Now we are going to enter into the chapter. Till now, whatever I was telling you till now, that was complete basics, right? Now, my dear students, we are going to enter into the chapter. Now it is the time to start the chapter. Okay? So the first topic which we have to discuss here, that is ionization constant of a weak electrolyte. Ionization constant of a weak electrolyte. Try to understand what I'm going to say. My dear students, for example, I have got a weak electrolyte AB. Let's say AB is a weak electrolyte. You are going to introduce it into water. Since it's a weak electrolyte, so it is going to remain in equilibrium with its ions, and its ions are going to be A positive aqueous plus B negative aqueous, right? It's going to be A positive aqueous plus B negative aqueous. Now, my dear students, let's assume the degree of ionization of this weak electrolyte. Let's assume that is alpha. And at the same time, let's assume initially at time t is equal to 0, the concentration of this weak electrolyte is C, for example. It is C molar, the concentration of weak electrolyte. So initially, the concentration of weak electrolyte is C. Time t is equal to 0 means that the dissociation has not started yet. If the dissociation has not started yet, I must say the container in which this reaction will be taking place, in that container, the concentration of A positive and B negative initially will be 0. Because the dissociation has not started yet. AB has not got dissociated into ions yet, right? So concentration of A positive and B negative at time t is equal to 0 will be absolutely 0, right? Now, my dear students, at equilibrium, when equilibrium is established in the reaction, if I ask you, what is the concentration of reactant left in the container? You'll be using the same procedure as we used to do in chemical equilibrium. You are going to treat this concentration in the similar way as you used to treat moles. Do you remember in equilibrium, chemical equilibrium, it used to be A00. Then it used to be A minus A alpha. This used to be A alpha. This used to be A alpha. So the way we used to treat the moles, in the similar way, you guys are going to treat the concentration as well. Now try to understand. The initial concentration of AB was C. Now, from C, how much will get dissociated? From C, C alpha will get dissociated. So how much will be left? C minus C alpha will be left. As simple as that. Now, 1 mole of AB gives 1 mole of A positive. From C alpha, you get C alpha exactly. 1 mole of AB gives 1 mole of B negative. From C alpha, you exactly get C alpha. So what did I calculate? Try to understand these things. What are these things exactly? These are the concentrations of reactants and products present in the container at equilibrium. When equilibrium got established in the reaction, I got the concentration of each reactant and product at equilibrium. Correct? Now, my dear students, the way we used to write Kc, do you remember how we used to write the expression for Kc? Well, let me tell you, in ionic equilibrium, Kc is represented by Ki. Kc is represented by Ki. That's all. What this Ki is called? Ki is something which you call as ionization constant. It is something which you call as ionization constant of what? Of a weak electrolyte. Of a weak electrolyte. Which weak electrolyte? AB. Perfect. The way you used to write the expression for Kc, in the similar way, you guys are going to write the expression for Ki. You'll be starting from the product. Concentration of A positive at equilibrium raised power stoichiometric coefficient. Concentration of B negative at equilibrium raised power stoichiometric coefficient divided by concentration of AB at equilibrium raised power stoichiometric coefficient. As simple as that. Now try to understand few important things. I'm teaching you the complete basics. If this is clear, then only the chapter will get clear to you. Now, my dear students, try to write the Ki expression in detail. Ki is equal to concentration of A positive at equilibrium, C alpha. Concentration of B negative at equilibrium, C alpha. So C alpha and C alpha makes it C square alpha square divided by concentration of AB at equilibrium, that is C minus C alpha, right? So it is C minus C alpha. So my dear students, just write it like this. It is C square alpha square, take C common, it's going to be 1 minus alpha in the denominator. So 1 of C and 1 of C gets cancelled out. So Ki comes out to be equal to C alpha square divided by 1 minus alpha. So first of all, this is how you write the expression for This is how you write the expression for the ionization constant of a weak electrolyte which undergoes the dissociation 1:1:1, right? Which undergoes the dissociation under the stoichiometry 1:1:1, right? I hope this is clear. Now, my dear students, after reaching till here, we'll be assuming certain things. Try to understand what I'm going to say. Till now, we got the Ki value, which is C alpha square divided by 1 minus. After reaching here, what we shall be doing, we shall be assuming certain things. I shall be assuming let alpha value is less than 0.05. I'm assuming that alpha is less than 0.05. I'm assuming that the percentage ionization of this electrolyte, at equilibrium, that is less than 50%. I'm assuming less than 50, that is less than 5%. I'm assuming less than 5% of electrolyte got dissociated when equilibrium was established. I'm assuming when 5% of electrolyte got dissociated, at that point of time only equilibrium is established. For example, I'm assuming that when 5% reaction was completed, at that point of time equilibrium is established. So what I'm assuming is, if I'm saying let alpha is less than 0.05, that means less than 5% reactant has got converted into product at equilibrium, right? As simple as that. So let alpha is less than 0.05. My dear students, if you assume that alpha is less than 0.05, at that point of time, you can neglect alpha in comparison to 1. And when you neglect alpha in comparison to 1, you can write Ki as C alpha square, and you can get the value of alpha from here. Just remember this procedure. You'll get its exact idea in some time when I'll be solving the questions. So first of all, you need to get the value of alpha. Let me tell you, this Ki will be given to us, C will be given to us. Can't we calculate alpha from there? Absolutely, we'll be calculating alpha from here. Absolutely, we shall be calculating alpha from here. I'm assuming less than 5% of reaction got completed. When less than 5% of reaction got completed, equilibrium got established. I'm assuming the degree of ionization of this weak electrolyte is less than 0.05. Right? So, my dear students, when I let alpha be less than 0.05, so 1 minus alpha will be taken as 1. So, Ki will be taken as C alpha square. Alpha will be taken as under root of Ki by C. And let me tell you, Ki value will be given to us as per the question. C value will be given to us as per the question. We just have to put the values. After putting the values, we'll be getting the value of alpha. We will be getting the value of alpha. And if the alpha value, after putting the terms in this equation, if the value of alpha actually comes out to be less than 0.05, that means whatever assumption we have done, that's absolutely correct. That's absolutely correct. If alpha does not come out to be less than 0.05, after solving this equation, if alpha does not come out to be less than 0.05, that means our assumption is absolutely wrong. You'll be getting its clear-cut idea in some time. But I hope my point here was to let you know how to write the ionization constant expression. If this ionization constant expression is clear, then I'm going to do one question based on the same so that you'll get the idea of what exactly I was talking about till now. Try to understand what I'm saying. Calculate the concentration of each ion at equilibrium for 0.1 molar solution of a weak electrolyte AB. So as per the question, you are given with a weak electrolyte AB. If it is a weak electrolyte, it's going to remain in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. Absolutely correct. Yeah. Now, dear students, at time t is equal to 0, let the concentration of AB aqueous is C, right? And this concentration of AB aqueous is given to me as 0.1 molar as per the equation. So initially, when the reaction has not started, this will be 0, this will be 0. Now you tell me at equilibrium, what is the concentration of reactant left? Let's assume the degree of ionization is alpha. So it is supposed to be C minus C alpha. 1 mole of AB gives 1 mole of A positive. So from C alpha, you get C alpha. From C alpha, you get C alpha, right? Now, my dear students, if I write the expression for Ki expression, ionization constant of weak electrolyte, Ki, how exactly you are going to write it? Concentration of A positive at equilibrium, multiplied by concentration of B negative at equilibrium divided by concentration of AB, which I told you a few minutes back only, that is C alpha square divided by 1 minus alpha. Correct till here? I hope every single thing is clear till here, right? Now, dear students, these are basically two questions. In the first question, we have to assume that ionization constant is equal to 10 raised power minus 5. In the first question, it's mentioned that ionization constant is equal to 10 raised power minus 5. Okay. Till here, everything is done. After this, I told you to follow certain assumptions. What I'll be doing after this? I'll be assuming let alpha value is less than 0.05. If alpha is less than 0.05, at that point of time, I can say 1 minus alpha is equal to 1. And if 1 minus alpha is equal to 1, that means I can say Ki is nothing, that is C alpha square. And from here, you'll be getting the value of alpha, which is under root of Ki divided by C. Now you tell me, what is the value of Ki? That's 10 raised power minus 5. What is the value of C? 10 raised power minus 1. So it comes out to be 10 raised power minus 4. Its root is 0.01. Now, my dear students, try to analyze the things. Whatever alpha value you have calculated from here, is the alpha actually coming out to be less than 0.05 or not? Absolutely, the value of alpha is coming out to be less than 0.05. That means whatever assumption you have done over here, the assumption is all perfect. Right? So you got the value of alpha. If you got the value of alpha, what was I supposed to calculate? Calculate the concentration of each ion at equilibrium. Now you tell me, concentration of each ion at equilibrium. Concentration of A positive and B negative at equilibrium. I'll say concentration of A positive at equilibrium is equal to the concentration of B negative at equilibrium, and both the values exactly are equal to C times alpha. Now people, are you given with the C value? Absolutely, you're given with the C value. That is 0.1 molar, which is 10 raised power minus 1. Alpha value, which is 10 raised power minus 2. So the value comes out to be 10 raised power minus 3 molar. So this is the concentration of A positive as well as B negative when equilibrium is established in the reaction. Is this point clear to every single guy? Say yes or no in the charts quickly. Say yes or no in the charts quickly, my dear students. Everyone, quickly. So the first part of the question is done and dusted. Right? The first part of the question is done and dusted. Perfect. Now, my dear students, since the first part of the question is done, let's try to do the second part of the question. In the second part of the question, we have to assume that the ionization constant of the weak electrolyte is 10 raised power minus 2. Now, let's see what change will occur over here. See, guys, the second part of the question. You have got an electrolyte AB aqueous. Right? Since it's a weak electrolyte, so it's going to remain in equilibrium with its ions, and its ions are A positive aqueous and B negative aqueous. I think all the procedure you already know. At time t is equal to 0, the concentration of this one is 0.1 molar. So this has to be 0, this has to be 0. Degree of ionization is alpha. So at equilibrium, what will be the concentration of AB aqueous? It is C minus C alpha. Sorry. So this is going to be C alpha and this is going to be C alpha, right? Now, as per the question, we have to consider the Ki value, ionization constant value, as 10 raised power minus 2. So it is 10 raised power minus 2, correct? Perfect. Now, my dear students, I would want you guys to write the Ki expression. Ki expression you already know, concentration of A positive, concentration of B negative, divided by concentration of AB. So final expression will be C alpha square divided by 1 minus. Now, again, the same thing. Let alpha value is less than 0.05. At that point of time, instead of 1 minus alpha, I can write 1. Therefore, Ki value will be just equal to C alpha square, and alpha will be equal to under root of Ki divided by C. Yeah? Right? Now, people, alpha is equal to under root of Ki by C. Now, you tell me, alpha is equal to under root of, what is Ki? 10 raised power minus 2. What is C? C is 0.1 molar. That means 10 raised power minus 1. Correct? That means 10 raised power minus 1. Which is going to be equal to under root of 10 raised power minus 1. Under root of 10 raised power minus 1 is 1 divided by root 10. 1 by root 10 is approximately 3 point something. Right? And approximate value will be 0.3. This is the approximate value of what? This is the approximate value of alpha. I had assumed that alpha value is less than 0.05. But have a look. Is alpha coming out to be less than 0.05? Alpha is not coming out to be less than 0.05. That means whatever assumption we have done over here, you cannot assume it. This is wrong. You cannot neglect alpha in comparison to 1. If you cannot neglect alpha in comparison to 1, that means how you are going to calculate Ki. In the Ki expression, you have to keep all the terms. C alpha square divided by 1 minus alpha. You cannot neglect alpha now. You cannot neglect alpha at this point of time, because alpha is not coming out to be less than 0.05. Yeah? What are we supposed to calculate? We are supposed to calculate the concentration of A positive and concentration of B negative at equilibrium, correct? Now, how we are going to solve it? Now, have a look. Now, we got to know that this is the actual Ki expression. You cannot neglect alpha. So, what you'll be doing? Put the value of Ki in this expression, which is 10 raised power minus 2. And 10 raised power minus 2, you can write it like this. You can write it as 1 divided by 10 raised power 2 is equal to C. C is the concentration of this electrolyte. 10 raised power minus 1. 10 raised power minus 1 can be written as 1 by 10. Alpha square multiplied by 1 minus alpha. So 10 and 10 got cancelled. So over here, if you have a look exactly what you'll be getting. You'll be getting 10 alpha square. 10 alpha square is equal to 1 minus alpha. So it's going to be 10 alpha square is equal to 1 minus alpha, or you can say 10 alpha square plus alpha minus 1 is equal to 0. So do you see over here one quadratic equation got developed? You got a quadratic equation, my dear student. You got a quadratic equation. Now you know exactly how to solve the quadratic equation. Alpha is equal to minus b plus minus root of b square minus 4ac divided by 2a. So after solving this quadratic, can't you get the value of alpha? Exactly, you'll be getting the value of alpha. And the value of alpha, which you'll be getting from here, just put the value of alpha here. C value, you know, alpha you'll be calculating. So C alpha will give you the concentration of A positive at equilibrium. Similarly, C alpha will give you the concentration of B negative at equilibrium, right? I hope you understood both the scenarios. When to neglect alpha and when not to neglect alpha. Say yes or no in the chats quickly. Say yes or no in the chats quickly, my dear students. Every one of you. Every one of you. This is the most important point here. This is the most important point here. To understand when to neglect alpha and when not. I hope this is super clear, yeah? All right. Now let's have a look. Look at this particular topic. Topic by topic, we'll be doing the questions. And I'm 100% sure you'll find this ionic equilibrium very, very, very easy. My dear students, still your NEET level. When it comes to NEET level or JEE mains level, this chapter is considered to be easy only, provided you know the basics. But from the advanced point of view, this chapter is considered to be tough. Yeah? But for your level or mains level, this is damn easy, provided you know the basics of it. Right? So we'll be studying a topic followed by question, topic followed by question, so that you get to know the application of the concept as well. Yeah? Now guys, few minutes back, I told you, all the weak acids, all the weak bases, they are the examples of weak electrolytes. For example, the weak electrolyte, which I am going to take into consideration, let's assume that is weak acid. Let's assume that is weak acid. Let's say I've got a weak acid HA over here. It's a weak acid. If it's a weak acid, it's going to be considered as a weak electrolyte and it's going to remain in equilibrium with its ions. And its ions are H positive aqueous plus A negative aqueous. Right? Now the same procedure. Let's assume the degree of ionization of this weak acid is alpha. So at time t is equal to 0. Its concentration is C. This is 0. This is 0. At equilibrium, this is going to be C minus C alpha. This is going to be C alpha. This is going to be C alpha. Right? Now, how do we write the ionization constant of the weak electrolyte? It is represented by Ki. But when your weak electrolyte is weak acid, you are not going to write Ki. Instead of Ki, you'll be writing Ka. And what is this Ka called as? It is called as ionization constant of a weak acid. Basically, this ionization constant of weak acid, what is it? It is ionization constant of weak electrolyte only. It is just the terminologies are different. Meaning is same. If your weak electrolyte is weak acid, then instead of Ki, you will be writing Ka. Rest everything is same. It is going to be equal to concentration of H positive at equilibrium raised per stoichiometric coefficient, concentration of A negative at equilibrium raised per stoichiometric coefficient, concentration of HA at equilibrium raised per stoichiometric coefficient, which will finally again come out to be C alpha square divided by 1 minus alpha. And after this, I'm damn sure you exactly know what to do. What do we do after this? Assumption. Let alpha value be less than 0.05. Let alpha value be less than 0.05. Then get the value of alpha. If the alpha value comes out to be less than 0.05, that means your assumption is correct. If not, then you have to solve the quadratic equation to get the actual value of alpha. Similarly, my dear students, if your weak electrolyte is your weak base, let's say you're taking a weak base, BOH. It's a weak base. If it's a weak base, it's a weak electrolyte. If it's a weak electrolyte, it's going to remain in equilibrium with its ions. Its ions are B positive aqueous plus OH negative aqueous. Right? Now you know each and everything. At time t is equal to 0, this is C. This is 0, this is 0. Degree of ionization, that's alpha. So this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. Now, dear students, particularly when your weak electrolyte is a weak base, at that point of time, Ki is replaced by the term Kb. Kb is something which I'll be calling as ionization constant of a weak base. Ionization constant of a weak base. How do I write this expression? You know how to write the expression. The same way as you used to write the expression for Kc, right? Concentration of B positive at equilibrium raised per stoichiometric coefficient. Concentration of OH negative at equilibrium raised per stoichiometric coefficient divided by concentration of BOH. As simple as that. So finally it comes out to be C alpha square divided by 1 minus alpha. And after this, you exactly know what to do. So from now onwards, try to remember one thing directly. If the electrolyte undergoes dissociation under the stoichiometry 1:1:1, its Ki will be always C alpha square divided by 1 minus alpha. If the electrolyte follows the dissociation under the category 1:1:1 stoichiometry, its Ki value will be always C alpha square divided by 1 minus alpha. Perfect. But if you change the stoichiometry, for example, this was 2 times. Let's say it was 2 times H positive. Here it will be 2 times C alpha. Here you have to introduce 2 as well. Perfect. I hope that thing is something which you already know. Yeah. Now, people, try to understand few important things. If, for example, alpha value is less than 0.05, at that point of time, your alpha will come out to be, if alpha is less than 0.05, then 1 minus alpha can be written as 1, and alpha you'll be getting as Ka divided by C. And over here, alpha you'll be getting as under root of Kb divided by C. Correct? Now, my dear students, try to understand one simple conclusion. Alpha and Ka directly or inversely proportional? They are directly proportional. So, more the value of Ka for an acid, more the value of ionization constant of an acid, I'll say more will be the value of alpha. More will be the value of alpha. More the value of alpha means more the percentage of acid that got dissociated. And more acid getting dissociated means more will be the H positive concentration in the solution. More the H positive concentration in the solution, lesser is going to be the pH. Right? Lesser is going to be the pH. Are you relating all these things? More the value of Ka means more is the value of alpha. More value of alpha. That means more is the dissociation, more is the ionization, more the H positive concentration, and lesser is going to be the pH. Right? Or you can say stronger is going to be the acid. Simple. Right? Look at this particular scenario. Alpha and Kb, they are again directly proportional. So more the value of alpha. More the value of Kb. If Kb value for the weak base is more, that means alpha value is more. If alpha for the weak base is more, that means this weak base has got dissociated more into its ions. So in the container, more will be the OH negative concentration, and more the OH negative concentration means more the basic strength. More the basic strength. More the basic strength means more is going to be the pH. More is going to be the pH. Right? Over here you can say more will be the acidic strength, right? Lesser the pH means more the acidic strength. All these things you already use in organic chemistry, right? I hope all these things are clear to you. So say yes or no in the chats if every single thing seems clear till here. And my dear students, if all these things are clear, let's try to solve certain questions. Weak acid, this is Ka, this is alpha. When you assume alpha is less than 0.05. This is alpha. When you assume alpha is less than 0.05. Perfect. And you got to know more Ka, Kb means more acidic basic strength for the same concentration. Yeah. Let's try to solve few questions so that you can completely analyze the things. See, learn the concept and try to utilize it in the question. That's how you actually learn the things, right? And if you learn together a lot of questions, if you learn together a lot of concepts, and at the end you'll be solving the questions, it won't make a difference. You are not going to learn in a better way then. One concept, one question. One concept, one question. That has to be the strategy always, right? That's how you remember the approach to solve the questions as well. Okay? Keep this thing in mind as well. All right. Calculate the H positive concentration of a 0.05 molar CH3COH. Now, if I talk about CH3COH, acidic acid, it's a weak acid. Weak acid, weak electrolyte. Weak electrolyte remains in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous. Agreed? Absolutely agreed. Yeah. Now, at time t is equal to 0, its concentration is C. This is 0. This is 0. Degree of ionization is alpha. At equilibrium, this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. Now write the expression for Ka. That has to be equal to C alpha square divided by 1 minus alpha. Yeah. Now let's assume that alpha value is less than 0.05. At that point of time, instead of 1 minus alpha, you can write 1. Right? And eventually, Ka comes out to be equal to C alpha square. Therefore, alpha value will be equal to under root of Ka divided by C. Yes? Agree till here? Now, my dear students, tell me the value of Ka. Ka value as per the question, that's 1.25 into 10 raised power minus 6. What about the C value? C is the concentration of the weak acid, and concentration of weak acid is given to me as 0.05 molar. So this is 0.05. So this is 1, this is 25 times. So this is root of 25 into 10 raised power minus 6, which comes out to be 5 into 10 raised power minus 3. 5 into 10 raised power minus 3 means 0.005. Alpha value is coming out to be 0.005, which is actually less than 0.05, which is actually less than what I had assumed. I had assumed the alpha to be less than 0.05, which is coming out to be actually 0.005. So whatever assumption we have done, absolutely correct. So we got the value of alpha, that is 0.005, or you can say 5 into 10 raised power minus 3. So alpha we calculated. What are we actually supposed to calculate? The concentration of H positive. Tell me the concentration of H positive in the container at equilibrium. Finally, what is the concentration of H positive in the container? That's C alpha. So this is C multiplied by alpha. What is C value? That is 0.05. 0.05, which means 5 into 10 raised power minus 2. What about alpha? Alpha is 5 into 10 raised power minus 3. Alpha is 5 into 10 raised power minus 3. So the value comes out to be 25 into 10 raised power minus 5 molar. This is the concentration of H positive in the container, which we were supposed to calculate. Is this clear to everyone? Say yes or no in the chats quickly. Everyone, people. Everyone means everyone. Quickly. I hope it's absolutely clear. So I do understand one more question. One more question which will make this concept a little more stronger. Have a look. Calculate the ionization constant of a weak base. So as per the question, we have taken a weak base, NH4OH. If it is a weak base, it's going to remain in equilibrium with its ions. Its ions are NH4 positive aqueous plus OH negative aqueous. That's how it would have got dissociated. Now, all the things you already know. Initially at time t is equal to 0, the concentration of NH4OH is C, right? And how much it is? How much it is? 0.1 molar. This is 0, this is 0. Let's assume the degree of ionization is alpha. So at equilibrium, I must say the concentration of this NH4OH left in the container is C minus C alpha. So this is going to be C times alpha. Even this is going to be C times alpha. Right? Clear till here? Now, my dear students, if I ask you to write the expression for Kb, since it's a weak base, so ionization constant of a weak base, it undergoes the dissociation. It undergoes dissociation under the stoichiometry 1:1:1. So it directly has to be C alpha square divided by 1 minus alpha. No need to do lot. Now tell me one thing. Tell me one thing. It is mentioned in the question that the concentration of OH negative in the 0.1 molar aqueous solution is 0.05 molar. So concentration of OH negative in the aqueous solution at the end, that means concentration of OH negative at equilibrium, that's basically given to me as 0.05 molar. Now if I ask you what is the concentration of OH negative at equilibrium, you'll say that is C alpha. So C alpha is equal to basically 0.05. Can I say alpha is nothing? That is 0.05 divided by C, and C is 0.1. So the value will be 0.5. Alpha is coming out to be 0.5. Alpha is coming out to be 0.5. Now you tell me, if alpha is coming out to be 0.5, that means instead of 1 minus alpha, can you write 1? You cannot do that. Alpha value, it did not come out to be less than 0.05. So you cannot do the neglection. So this is the expression which you have to write now. You cannot neglect alpha here. You have to take this alpha in the denominator as well, right? So what are we supposed to calculate? We were supposed to calculate the ionization constant of the weak base. So Kb we were supposed to calculate. C value is 0.1. 10 raised power minus 1. Alpha square. Alpha is 0.5. 0.5 ka square divided by 1 minus 0.5. So 1 minus 0.5 is 0.5, 0.5, 0.5 cancel. So it comes out to be 0.05. So this is the value of ionization constant of the weak base which we were supposed to calculate. So let me know in the chats if every single thing is clear to you. Quickly guys. Quickly in the chats. Quickly in the chats. Yes? Perfect, guys. Now, there is one more important concept which is used in the entire equilibrium. That is common ion effect. One of the most important concepts, right? Let's try to understand what this concept exactly is and where do we exactly utilize this concept. Let's get to know one by one, right? Let's try to read its definition first. The suppression of degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added to it. I'm damn sure you did not get it, right? So let's try to understand it. See guys, for example, you have got a weak electrolyte. Let's say I'm taking weak acid. This is the weak acid which we have. This is the weak acid. That means we have got a weak electrolyte. If we have got a weak electrolyte, that means it's going to remain in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous. Perfect. So I've taken a container in which CH3COH is in equilibrium with its ions. Agreed? Let's assume its degree of ionization is alpha. So initially at time t is equal to 0. This is C. This has to be 0. This has to be 0. Now when equilibrium is established in the reaction, so this has to be C minus C alpha. This is going to be C alpha. This is going to be C alpha. Right? Now dear students, try to understand one thing. I've taken a container. In which this weak electrolyte is in equilibrium with its ions. Now, in the same container, I am going to introduce a strong electrolyte. In the same container, I'm going to introduce a strong electrolyte. Right? Strong electrolyte HCl, I'm going to introduce in the same container. So it's going to get dissociated completely into its ions. It's going to get dissociated completely into its ions. Right? Now, let's assume that its initial concentration was C1, this was 0, this was 0. Now it's going to get completely dissociated into its ions. So its concentration will be 0 at the end. 1 mole gives 1 mole, C1 gives C1. This is C1. Now, my dear students, try to understand one simple thing. I had a weak electrolyte in the container, which was in equilibrium with its ions. In the same container, I introduced a strong electrolyte. But you'll be introducing such a strong electrolyte. Which will be satisfying one condition. And the condition is that there should be one ion common in both. Is there any ion common in both? H positive, H positive. So you are going to add such a strong electrolyte which will satisfy the condition that one of the ion should be common in both, right? So whenever you see such kind of the thing, you have got a weak electrolyte, you are introducing a strong electrolyte into it, having a common ion. Now do remember, at that point of time, common ion effect is going to operate. Now what this common ion effect does? Before telling you that, tell me one thing. If I ask you, what is the total concentration of the common ion? Common ion is H positive. Concentration of H positive coming from this acid is C alpha. Concentration of H positive coming from this acid is C1. So total H positive concentration is C1 plus C alpha. C1 plus C alpha, right? Initially, if you try to observe one thing, initially, there was only weak acid in the container, which was in equilibrium with its ions. Now you are introducing a strong acid, right? By the introduction of strong acid, can I say you are increasing the H positive concentration in the container? Absolutely, you are increasing the H positive concentration. Now, you are increasing the H positive concentration in the container. Since this reaction was in equilibrium, now you are adding a strong acid. Due to the addition of strong acid, you are increasing the concentration of H positive. Which effect is going to operate? Chatelier principle, you are going to operate. Whatever you do to a reaction at equilibrium exactly does opposite of what you do. I am trying to increase the H positive concentration by the addition of strong acid. Now equilibrium will try to decrease it. How equilibrium is going to decrease it? It will make sure the reaction shifts in the backward direction. And when this particular reaction shifts in the backward direction, that means the value of alpha for this weak electrolyte, is it increasing or decreasing? I must say the value of alpha for the weak electrolyte will be decreasing. Right? So my dear students, this decrease in the value of alpha, the suppression in the degree of ionization, the decrease in the degree of ionization when a strong electrolyte is added to a weak electrolyte having a common ion in between. This effect is what you call as common ion effect. The suppression, the decrease in the value of degree of ionization of a weak electrolyte when a strong electrolyte having a common ion is added to it. Right? For example, this particular alpha, when there was only weak electrolyte present in the container, which was in equilibrium with the ions, let's assume that alpha was already less than 0.05. Now, by the addition of this strong acid, the alpha value would have further suppressed. So, wherever you see alpha, you can neglect the alpha. So, if I ask you the total H positive concentration, which is C1 plus C alpha, instead of this whole, you are only going to write C1. Because alpha has further suppressed, it has further decreased. Already it was less than 0.05. Now it has further decreased. Yeah? Right? Right, people? Now, I'm going to ask you one thing. Write the expression of Ka for this weak acid. It's going to be concentration of CH3CO negative, which is C alpha. Concentration of H positive at equilibrium, which is just C1 divided by concentration of CH3COH, which is C minus C alpha. Take C common, state 1 minus alpha, so CC cancel. So Ka value will be equal C1 alpha divided by 1 minus alpha. Already, due to the addition of strong acid, alpha value has further suppressed. So wherever you want to neglect alpha, you can do that. So instead of 1 minus alpha, you can write 1. So from here, you can say Ka is equal to C1 alpha, or alpha value you got to know as Ka divided by C1. Tell me, is this the old alpha or new alpha? Is this the alpha before the addition of strong electrolyte, or this is the alpha after the addition of strong electrolyte? Tell me, is this the alpha before operation of common ion or after operation of common ion? This is the value of alpha after the operation of common ion. Before the operation of common ion, when there was only weak acid in equilibrium with its ions, alpha at that point of time would have been under root of Ka by C. But now it's going to be Ka divided by C1. Ka is the ionization constant of the weak acid. And what is C1? C1 is basically the concentration of common ion. The concentration of common ion coming from the strong electrolyte. Concentration of common ion coming from the strong electrolyte. One more thing. If they ask you, what is the concentration of common ion in the container? What is the concentration of common ion in the container? The concentration of common ion in the container net is C1. And what is C1? C1 is the concentration of H positive which you are getting from strong electrolyte. So from this particular thing, can I say the common ion concentration is entirely decided by the strong electrolyte? Right? See, the concentration of common ion is coming out to be C1 finally. Right? What was the C1? It was basically the concentration of common ion coming from strong electrolyte. So strong electrolyte is the one which decides the entire common ion concentration. So take a note of this particular thing. It's important. Concentration of common ion. Concentration of common ion is entirely decided by the strong electrolyte. So strong electrolyte is the one which governs, which decides the concentration of the common ion. I hope this is absolutely clear to you. Let's try to solve a question on the same concept. So before doing the question, tell me one thing. When a strong electrolyte is added to a weak electrolyte, both having one ion in common, what will happen to alpha value of a weak electrolyte? The degree of ionization of the weak electrolyte decreases. And this decrease in the value of alpha due to the addition of strong electrolyte to the weak electrolyte, both having one ion in common, right? That effect is what you call as common ion effect. Yeah? Perfectly here? Perfect, people? All right. Now let's try to solve certain questions. Look at the first question. The first question is calculate the concentration of each species at equilibrium in an aqueous solution. These are two questions basically. The first question is you have got 0.1 molar NH4OH. So you have got 0.1 molar NH4OH. NH4OH is a weak base. If it is a weak base, it's going to remain in equilibrium with its ions. Its ions are NH4 positive aqueous plus OH negative aqueous. This question will solve all your doubts if you have any. Okay. Or imagine that you have got 0.1 molar NH4 only in the container. So at time t is equal to 0, its concentration is C, which is 0.1 molar. So this is 0, this is 0. Degree of ionization, assume that alpha. So at equilibrium, it's going to be C minus C alpha. This is going to be C alpha. This is going to be C alpha. Now try to write the Kb value. Try to write the Kb value, which has to be equal to C alpha square divided by 1 minus alpha. It's a weak base, that's why Kb, right? Now what we are going to do, we are going to assume certain things. Let alpha is less than 0.05. Therefore 1 minus alpha can be taken as 1. If 1 minus alpha is taken as 1, therefore alpha is going to be under root of Kb divided by C. Therefore alpha is going to be under root of Kb. What is Kb? Kb is given 1.8 into 10 raised to the power minus 5. What about C value? C is the concentration of weak electrolyte, which is 0.1 molar, right? Now, do remember from now onwards, you'll be frequently using this. Root of 1.8 is equal to 1.34. Root of 1.8 is equal to 1.34. You'll be frequently using it. Yeah? Now, my dear students, try to understand a few more things. So, get the value of alpha from here. I would say alpha will be equal to under root of 1.8 is 1.34 multiplied by 10 raised power minus 1 will go up. It's 10 raised power minus 4. Root of 10 raised power minus 4 is 10 raised power minus 2. So this is the value of alpha, which came out to be 0.00134. Now check the value of alpha. Is that actually coming out to be less than 0.05? Yes, it's coming out to be less than 0.05. So whatever is the alpha value, which you have got from here, absolutely correct. Whatever assumption you have taken, that's absolutely correct. Now, what I was supposed to calculate? I was supposed to calculate the concentration of all the ions at equilibrium. Concentration of NH4 positive at equilibrium is exactly equal to concentration of OH negative at equilibrium, and both are equal to C alpha. Look at this. This is C alpha. This is C alpha, right? C is given, alpha is given. C is 0.1. Alpha is 1.34 into 10 raised power minus 2. So the final answer is 1.34 into 10 raised power minus 3 molar. This is the concentration of all the ions in the container if there was only 0.1 molar NH4OH present in the container. That's all. Yeah? Let me know quickly in the chats if all the things are absolutely clear to you. Quickly, people. Everyone. Everyone. So the first part of the question is done. So if there was only NH4OH in equilibrium with its ions, its alpha is less than 0.05. Alpha is less than 0.05. And you got the concentration of each ion present in the container at equilibrium. Yeah? Perfect. Perfect, people. Let me know once in the chats. Now it's time to solve the second question. Now the second question will make you understand the common ion effect properly. The second question says, if 0.1 molar NH4Cl is added with, along with 0.1 molar NH4OH. Now see exactly what you'll be doing. Now the question says, already there was NH4OH in the container, which was in equilibrium with its ions, and its ions were NH4 positive aqueous plus OH negative aqueous, right? Its degree of ionization was alpha. At time t is equal to 0, its concentration was 0.1 molar. This was 0, this was 0. And at equilibrium, it was C minus C alpha. This was C alpha, this was C alpha. And when NH4OH was there in the container, which was in equilibrium with its ions, its alpha at that point of time was 0.00134, right? Which we already saw. Now, what exactly is going to happen? You are going to introduce NH4Cl in the same container. Tell me one thing. When I say NH4Cl, it is the salt of NH4 positive. And the salts of NH4 positives, they are water soluble, if you remember. And all the water soluble salts, they are strong electrolytes. So this NH4Cl, it is absolutely a strong electrolyte here. So it will undergo complete dissociation. NH4 positive aqueous plus Cl negative aqueous. Correct? Let's assume its concentration is C1, which is given to us as 0.1 molar as per the question. You can check it if 0.1 molar NH4Cl is added. Right? So this is 0 in the beginning, this is 0. Now 100% dissociation. This will be 0, this will be C1, this will be C1. Now tell me one thing. Do you see one simple thing over here? Do you see a weak electrolyte, a strong electrolyte, both having one ion in common? Absolutely. I'm seeing a strong electrolyte, weak electrolyte. Both are having one ion in common. Which effect you are going to operate? You are going to operate the common ion effect. Due to common ion effect, what will happen to the value of alpha? It was already less than 0.05. Now it will further decrease. So wherever you want to neglect alpha, you can neglect that. Yes, you can neglect that. Now, dear students, if I ask you, what is the total concentration of common ion? From here it is C alpha, from here it is C1. So it is going to be C1 plus C alpha. Now, due to common ion effect, you can neglect alpha. So instead of C1 plus C alpha, you can only write C1. Yes, you can only write C1. Now, if I want to write the Ka expression, how you are going to write it? Few minutes back only, or let's not write Ka directly. What is the new alpha? New alpha is directly going to be Ka divided by C1. Sorry, Kb by C1 in this case. Because it's a weak base, right? Kb divided by C1. If it was a weak acid, then Ka by C1. Right? So Kb value, as per the equation, 1.8 into 10 raised power minus 4. C1 value is given 0.1. Right? So alpha value is equal to 1.8 into 10 raised power minus 3. Which comes out to be equal to 0.00, right? 0.00018. Perfect. 0.0018 it will come. Right? Perfect. Is there some mistake? I think yes. It is 10 raised per minus 5 here. Sorry, this is not 10 raised per minus 4. This is 10 raised per minus 5. If this is 10 raised per minus 5, it's going to be 10 raised per minus 4 here. It's going to be 10 raised per minus 4 here. Now it's going to be 0. Now it's going to be 0.0018. Perfect. Now you are going to tell me one thing, whether this is new alpha or old alpha. Compare the old alpha and new alpha. Old alpha was 0.00134. New alpha is 0.00018. So has the alpha actually increased or decreased? Alpha has actually decreased. That's what I'm telling you. Alpha decreases due to common ion effect. What am I supposed to calculate? I'm supposed to calculate the concentration of each ion in the container. First of all, the common ion is NH4 positive. So tell me the net common ion concentration finally in the container. It was supposed to be C1 plus C alpha, which is coming out to be C1 only, right? And C1 value, that's already 0.1 molar. Absolutely correct. Now second, concentration of OH negative in the container. Concentration of OH negative is going to be C times alpha. But this alpha is not old alpha, it's the new alpha. C value is equal to 0.1. Alpha is 1.8 in 10 raised power minus 4. So the final value comes out to be at the end 1.8 in 10 raised power minus 5 into 10 raised power minus 5 molar. So this is the concentration of OH negative in the container at the end. I hope you got the concept of the common ion effect. If you actually got it, let me know once in the chats. Then only I'll be solving one more question with you. Quickly. Quickly, my dear students, everyone in the chats. Is every single thing clear till here? Look at this question now. Look at one more question. Calculate the concentration of H positive and CH3CO negative at equilibrium. If 0.5 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. Similar pattern of question. Let's give it a try. Let's try to understand this common ion effect a bit more in detail now. Right? By solving this question, absolutely everything will be clear. Now, as per the question, you have got CH3COH aqueous in the container. Since it's a weak acid, so it's going to remain in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous. Right? Now, at time t is equal to 0, the concentration of CH3COH is C. How much is that? That's 0.1 molar as per the question. So this will be 0, this will be 0. Degree of ionization alpha. So at equilibrium, it's going to be C minus C alpha. This is C alpha, this is C alpha. Right? Right, people? Now, my dear students, in the same container, what you are doing? You are adding HCl in the same container. HCl is an example of a strong electrolyte. So it will undergo complete dissociation as H positive aqueous plus Cl negative aqueous. Now, the concentration of HCl in the beginning has been kept as 0.5 molar. So this will be initially 0, this will be 0. Now 100% dissociation. This will be 0, this will be C1, this will be C1. Now try to understand the concept. Do you see? Weak electrolyte and a strong electrolyte. Weak electrolyte, strong electrolyte. Both having one ion in common. That's H positive. So which effect is going to operate here? Again the common ion effect is going to operate. Due to common ion effect, this alpha value will further decrease. Already it was less than 0.05. Now it will further decrease, right? So wherever you want to neglect alpha, you can do that. So tell me first of all, what is the concentration of the common ion? H positive concentration from here is C1, from here is C alpha. So it has to be C1 plus C alpha. But which finally you have to write as C1 only. Right? What is the new alpha? New alpha is going to be Ka divided by C1. Ka value as per the question, 1.8 into 10 raised power minus 5 divided by C1 value, that's 0.5. Right? Which comes out to be 3.6 into 10 raised power minus 5. This is the value of new alpha. Now, what is the concentration of the common ion? Common ion is H positive. The net common ion concentration is C1 basically, and C1 is equal to 0.5 molar. If I ask you, what is the concentration of CH3CO negative in the container at the end? That is C times alpha. So C times alpha. P value is 0.1 and alpha is how much? Alpha is 3.6 into 10 raised power minus 5 now. So the value comes out to be 3.6 into 10 raised power minus 6 molar. So these were the two things which you were supposed to calculate, I believe, right? Yeah? Is it clear, people? Quickly. Is it clear to everyone? Without using pen and paper, tell me the answer of this question. Without using pen and paper, tell me the answer of this question. Without using pen and paper. Calculate the concentration of H positive at equilibrium if 0.1 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. Without using pen and paper. Strong electrolyte, weak electrolyte. Both are having one ion in common. That one ion is H positive. Concentration of common ion is decided by the strong electrolyte. Strong electrolyte HCl undergoes dissociation as H positive plus Cl negative. Right? So, concentration of H positive is decided by strong electrolyte HCl, which undergoes dissociation as H positive plus Cl negative. Its concentration was 0.1. So, its concentration will be 0.1 molar. The question is done here only. Right? Agreed to this? Agreed, people? Yeah, or you can have a detailed approach the way I have been solving the questions. In the similar way, you can try this question as well, writing both the reactions, etc., etc. Gautam, just watch the video which I've taken for the test series, right? Just watch that video. I've given the entire syllabus for the first 7 tests. Just watch that video. I don't remember what is the syllabus of the upcoming test. Just watch that video and see. Okay? Perfecto. Moving ahead. There is something called as Ostwald's dilution law. What is Ostwald's dilution law all about? It's again very simple, right? Let me try to make you understand what is Ostwald's dilution law. As per this law, on dilution, degree of ionization. Upon dilution, degree of ionization of a weak electrolyte increases. With the dilution, the degree of ionization of a weak electrolyte increases. What does that mean? Try to understand. For example, you have got a weak electrolyte as AB. This is a weak electrolyte. If it is weak, it's going to remain in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. Let's assume the degree of ionization is alpha. Let's assume initially its concentration is C. This is 0, this is 0. So at equilibrium, it's supposed to be C minus C alpha. This is supposed to be C alpha. This is supposed to be C alpha, right? Let's assume that the ionization constant of this weak acid, of this weak electrolyte is Ki, which will be for sure C alpha square divided by 1 minus alpha. Now again, let's assume that alpha is less than 0.05. Therefore, 1 minus alpha will be taken as 1 from here, and alpha value will be equal to under root of Ka by C. Alpha value will be equal to under root of Ka by C. Right? Now what exactly we are going to do? Try to understand. So first of all, I had a container in which the weak electrolyte was in equilibrium with its ions. This is the container in which the weak electrolyte is in equilibrium with its ions, right? Now, if I ask you what is concentration, basically, concentration is number of moles per unit volume of the system. Number of moles per unit volume of the system in liters. Now, dear students, for example, if you are adding more solvent here is water, for example, right? If you are adding water into the container, so what you are doing? You are doing dilution. By the addition of water, what will happen to the volume of system? Volume of system will increase. If volume of system increases, concentration will decrease. Both are inversely proportional. If concentration decreases, that means alpha value will increase. Alpha value will increase. That's something which I wrote over here. Upon dilution, degree of ionization of a weak electrolyte, what happens to it? It increases, right? Upon dilution, degree of ionization of a weak electrolyte, that increases. So upon dilution, upon the addition of water here in this particular scenario, this weak electrolyte, gets more and more ionized into its ions. It gets more and more ionized into its ions. Right? Can I say upon continuous dilution, this weak electrolyte will be continuously getting dissociated into its ions. Can I say a scenario will come when 100% of this electrolyte would have got dissociated into its ions? That particular dilution is something which we call as infinite dilution. So at infinite dilution, I must say this weak electrolyte would have got completely dissociated. So at infinite dilution, the weak electrolyte will be behaving like the strong electrolyte. So I can say at infinite dilution, the degree of ionization of the weak electrolyte, that becomes 1. So it now behaves like the strong electrolyte. Right? I hope this is clear. I hope this is clear to everyone. Right? This is the scenario which I gave you. At infinite dilution, the weak electrolyte behaves as a strong electrolyte. Perfect, people? Is this super duper clear to you? Quickly. Let me know quickly in the chats, every one of you. Quickly. Yes, Anish, it is in electrochemistry only. I mean, in electrochemistry, you learn the same concept, right? Effect of dilution on molar conductivity and equivalent conductivity for strong as well as weak electrolytes. Perfect. Now, ionic product of water. Again, one important topic. Ionic product is represented by Kw first of all. Now, what is ionic product of water? Try to understand what exactly I'm going to say. This is again some complete basic thing. Try to understand. My dear students, for example, you have got water, pure water you have, right? You have taken pure water in the container. Let me tell you, pure water, it's again considered as a weak electrolyte. Pure water, it is again considered as a weak electrolyte. If pure water is considered as the weak electrolyte, so it will also remain in equilibrium with its ions. Its ions are H positive aqueous and OH negative aqueous. Or you can write H3O positive aqueous, OH negative aqueous. By solvers, right? Yeah. So I'm talking about pure water. Pure water is again the example of a weak electrolyte, which is going to remain in equilibrium with the ions. Now, if this pure water is the example of weak electrolyte, can you write its ionization constant expression? Absolutely. Concentration of H positive at equilibrium raised power 1, concentration of OH negative at equilibrium raised power 1 divided by concentration of H2O liquid. Right? Now you can write it like this. Ki multiplied by concentration of H2 is equal to concentration of H positive multiplied by concentration of OH negative. Now, my dear students, this particular term, it's constant, right? This particular term, it's constant. So constant multiplied by constant makes it a new constant, that's Kw. So Kw is nothing. It is the product of concentration of H positive and OH negative, right? This particular expression is valid at all temperatures. It is valid at all temperatures. It is valid at all temperatures, this particular expression. Kw, which is what you call as ionic product of water. It is defined as the product of H positive concentration and OH negative concentration in the container. That's all. Yeah? But try to understand one thing. My dear students, at 25 degrees centigrade, do remember a few things now. At 25 degrees centigrade, the concentration of H positive is equal to the concentration of OH negative in the container at 25 degrees centigrade. Concentration of H positive and OH negative, both are equal to 10 raised power minus 7 mole in the container. But at 25 degrees centigrade, if concentration of H positive OH negative at 25 degrees centigrade is 1 molar, then what's going to happen? I must say, Kw will be written as, ionic product of water will be written as concentration of H positive multiplied by concentration of OH negative, 10 power minus 7, 10 power minus 7, which makes it 10 raised power minus 40. But this equation is only valid at 25 degrees centigrade, when water is kept at 25 degrees centigrade, right? Perfect. Now, guys, try to understand a few things now. Have you ever heard of pH? Okay, leave pH aside. Let me tell you what this P stands for. What is P? This small p. It is just a mathematical operator. It is just a mathematical operator which stands for minus log. Minus log is represented by P basically. In short, minus log is represented by P. For example, you're writing pH. What does it mean? P stands for minus log. So that means I'm talking about minus log of H positive concentration. For example, if I write POH, P stands for minus log. That means I'm talking about minus log of OH negative concentration. If I'm writing P of Ka, that means I'm talking about minus log of Ka. So what is P basically? P is nothing. It is just the mathematical operator which stands for minus log, right? Now, what exactly I'm going to do? I'm going to multiply this equation throughout by minus log. Multiplying throughout by minus log. It becomes minus log of Kw is equal to minus log of H positive concentration, OH negative concentration, which is equal to minus log of 10 raised power minus 14. Now minus log of Kw is simply called as P of Kw is equal to, when you split it, log of m into n makes it log of m plus log of n. It finally becomes pH plus POH, right? And this term minus log of 10 raised power minus 14, it comes out to be 14. It becomes 14 because log of m raised power n is n log m. But this particular equation, again I'm telling you, it's valid only when water is kept at 25 degrees centigrade, right? So at 25 degrees centigrade, this particular equation is valid. P of Kw is equal to pH plus POH. That's equal to 14, right? Perfect. Perfect, guys. Now tell me one thing. Tell me one simple thing, which I'm going to tell you here. Since Kw is equal to concentration of H positive multiplied by concentration of OH negative, do remember, on increasing the temperature, the value of Kw increases. When you increase the temperature, on increasing the temperature, the value of Kw, it increases. Do remember it, okay? Do remember it. So let me know once in the chat if it is clear, quickly. Quickly, guys. Yes? Perfect. Perfect. Try to understand few more things. I'm going to tell you one important thing now, okay? One important thing. I'm going to tell you now. Try to understand that carefully. What is that important thing? Have a look. I'm writing a statement. The statement is, upon increasing the temperature, pH scale shrinks. pH scale shrinks. This is one important concept. Why is it important? There is a logic for that. Why is it important? For example, I'm asking you a question like this. You have got two glasses, right? Both containing water. This is H2O liquid. This is H2O liquid, right? Now this H2O liquid is at 25 degrees centigrade. This H2O liquid is at, for example, 35 degrees centigrade. Can you let me know whose pH will be more, whose pH will be less? Just say it. What do you think? Both the containers will be containing water, right? One is at 25 degrees centigrade, one is at 35 degrees centigrade. So where do you see the pH of water more, at 25 or 35? Quickly, guys. With this, I should have some water as well. Where do you see pH of water more? So a lot of people are saying pH at 25 degrees centigrade will be more and pH at 35 degrees centigrade will be less. pH more, what does that mean? Basic. pH less, does that mean acidic? So does that mean when I'm drinking hot water, does that mean I'm drinking acid? Are you trying to say that? Okay, just kidding. Try to understand what I'm going to say. Try to understand what I'm going to say. How written a statement or increasing the temperature, pH scale shrinks. So basically, at 25 degrees centigrade, pH scale varies from 0 to 14. And in the middle, the 0.7 is here, which represents neutral, Before this, it represents acidic part. And after this, it represents basic part. Correct? At 25 degrees centigrade. Now, for example, the same water is at 35 degrees centigrade. For example, the same water is at, 35 degrees centigrade. Right? So, have I increased the temperature? Absolutely, I have increased the temperature. Upon increasing the temperature, pH scale shrinks. pH scale was initially from 0 to 14. Now, for example, imagine that the pH scale will now be from 0 to 13 only. The pH scale has shrinked a bit. Now, the middle point over here is 6.5 only. Middle point is 6.5. So, in this particular scale, on this particular scale, this 6.5 represents neutral. Before this, this part represents the acidic part and this part represents the basic part. Right? Right, people? Now, what was I doing? I was increasing the temperature of water. When you increase the temperature of water, Kw value increases. Kw value increases. Kw increases, that means H positive as well as OH negatives increase. On increasing the temperature, H positives as well as OH negatives increase. My dear people, the stoichiometric coefficient is 1:1. On increasing the temperature, H positives as well as OH negatives increase. What does that mean? That over here means the concentration of H positive and OH negatives are increasing by equal amounts. Right? The concentration of H positive and OH negative upon increasing the temperature are increasing by equal amounts. Right? If the concentration of H positives and OH negatives are increasing by equal amounts, what will happen to neutrality? Neutrality will remain the same. Because the concentration of H positives and OH negatives, they are increasing by equal amounts on increasing temperature. So, neutrality is going to remain the same. But at 25 degrees centigrade, 7 used to represent the neutral solution. At 35, for example, 6.5 represents the neutral. Upon increasing the temperature, neutrality has to remain the same. Right? So, that means to have the same neutrality, the pH has to decrease from 7 to 6. Because 7 was used to represent neutral at 25. But at 35, 6.5 represents neutral. Neutrality remains the same. So, in order to show the same neutrality, pH will decrease. Right? So, what should be the answer? Upon increasing the temperature, pH scale shrinks. Let me tell you, pH scale shrinks. Upon increasing the water, on increase the temperature, pH of water decreases. But does that affect the neutrality? But neutrality of water remains the same. Right? But the neutrality of water remains the same. I hope this point is clear to you. Yeah? Let me know once in the chats if it is super clear. One more thing. If the concentration of H positives and OH negatives in the solution is equal, the solution is going to be neutral. If H positive concentration is greater than OH negative concentration, it's going to be acidic. If it is less, it's going to be basic. This is something which you all must be knowing already, right? I'm not going to discuss about this one. I hope all these things are absolutely clear to you, right? Now, my dear students, we are going to discuss one of the most, I would say the most important topic of the chapter, that is calculation of pH. How do we calculate pH of different solutions? So one by one, we are going to discuss all the categories in it, right? And again, we'll be starting from the basics itself, from the zero itself. So my dear students, the first category here in order to calculate the pH. The first category which I'm going to discuss with you, what is that? That is calculation of pH of a strong monoprotic acid or a base. First of all, whenever you are supposed to calculate pH of a solution, whenever you are supposed to calculate pH of the solution, what does first of all that mean? You know, P stands for minus log. Minus log of what? Minus log of net H positive ion concentration. So whenever you are supposed to calculate pH of any solution, your first point always will be to calculate the net H positive ion concentration in the solution. Once you get the total H positive ion concentration in the solution, take minus log of it. Whatever the value you'll be getting, that's going to be the pH of the solution. Right? So dear students, in order to calculate the pH of the solution, what do you need? You need the H positive ion concentration in the solution. Once you get the H positive ion concentration in the solution, take minus log of it, get the value, that's going to give you the pH. That's all. Right? Now dear students, the first category is calculate the pH of strong monoprotic acids and bases. What does it mean? See, these are 6 questions over here. These are 6 questions over here. By solving these questions, you'll exactly get the idea of how do we calculate pH of strong monoprotic acids or bases. So dear students, have a look on the first case. We are given with 0.1 molar HCl aqueous solution. We are given with 0.1 molar HCl aqueous solution. We are supposed to calculate pH of this particular solution. Right? Now, first thing, if I ask you, HCl, is it a strong acid or weak acid? It's absolutely a strong acid. Strong acid means it's a strong electrolyte. If it is a strong electrolyte, it would have got completely dissociated into its ions. So basically, when you will introduce HCl in water, it will completely get dissociated into its ions, right? Because it's a strong electrolyte. Now, dear students, if I ask you, at time t is equal to 0, what was the concentration of HCl that was given to us? 0.1 molar. So this was 0, this was 0. Now it's a strong electrolyte, it will get completely dissociated, right? So I'll be left with nothing of this HCl. Now 1 mole of HCl gives 1 mole of H positive. So 0.1 molar is going to give me 0.1 molar of HCl. H positive. Similarly, 0.1 molar of Cl negative. So can I say I got the concentration of H positive in the solution? The concentration of H positive in the solution came out to be 0.1 molar. That means 10 raised power minus 1 molar. And since you got the H positive ion concentration in the solution, you can directly calculate pH. P stands for minus log. So minus log of what? Minus log of H positive concentration, which comes out to be minus log of 10 raised power minus 1. Log of m raised power n is n log m. So minus 1 comes to the front. Minus becomes plus. So the value comes out to be 1. And log of 10 is 1 itself. So I would say pH of the solution over here that was given to us, that's absolutely 1. Right? Perfect. Very simple. Now look at the second one. 10 raised power minus 3 molar HCl. So I'm given with 10 raised power minus 3 molar HCl aqueous solution. Get its pH. Get the pH of this solution. Now if I talk about HCl, it's again a strong electrolyte. When you introduce it into water, it will get completely dissociated. It will get completely ionized. Right? The initial concentration of HCl was 10 raised power minus 3 molar. So this was 0. Even this was 0. Now it will be getting 100% ionized. This will be 0. 1 mole of HCl gives 1 mole of H positive. So 10 power minus 3 molar will give 10 power minus 3. Even this will be 10 raised power minus 3 molar. Now my dear students, you got to know the H positive concentration in the solution. That's 10 raised power minus 3 molar. Now calculate the pH. P stands for minus log. Minus log of H positive concentration. So the final answer will come out to be 3. So pH of this particular solution is simply 3. That's all. Right? Similarly, you can calculate for this one. Easy. Now look at this particular case. 10 raised power minus 7 molar HCl. Now try to understand. Here's a trick. Next case is 10 raised power minus 7 molar HCl aqueous solution. Try to understand. First of all, when I introduce HCl into water, I would say this HCl will dissociate into H positive and Cl negative. When you introduce HCl into water, you will get H positive aqueous and Cl negative aqueous. Correct? Now, my dear students, at time t is equal to 0, what was the concentration of HCl? That was 10 raised power minus 7 molar. This was 0, this was 0. Now it's a strong acid, complete dissociation. This will be 0, this will be 10 raised power minus 7, this will be 10 raised power minus 7. Right? So what is the H positive concentration which you got over here? H positive concentration is coming out to be 10 raised power minus 7 molar. Right? In the solution, we got to know H positive concentration is 10 raised power minus 7 molar. So if I ask you to calculate pH, P stands for minus log of H positive. The value comes out to be 7. Right? So pH of this solution has to be 7. But if you think logically, are we given with acidic? Is this acidic solution or basic solution? It is 10 raised power minus 7 molar HCl aqueous solution. So it is acidic solution. Its pH is supposed to be less than 7, but it's coming out to be 7. So that means there's a mistake which we'll be doing. There's a mistake which we are doing here. See, following the general procedure, the pH of this particular solution is coming out to be 7, but it should be less than 7. Whenever by following this particular procedure, the pH of acidic solution comes out to be 7 or greater than 7. At that point of time, what exactly we need to do? Try to understand. See guys. See. HCl you are introducing in water basically. Right? HCl you are introducing in water. Since water is already a weak electrolyte, which is in equilibrium with its ions, H positive, H negative. So can you let me know already in the water, what was the H positive concentration which was already there in the water? That was already 10 raised power minus 7 molar at 25 degrees centigrade. And this is the H positive concentration which is coming from acid. Already in the container, the concentration of H positive was 10 raised power minus 7 molar. Now, in the water, you are introducing the HCl, right? So concentration of H positive coming from HCl, that's 10 raised power minus 7. Concentration of H positive, which was already coming from water, was 10 raised power minus 7 molar. If I ask you, what is the net H positive ion concentration in the container? Net H positive ion concentration, total H positive ion concentration in the container will be this plus this, which is 2 times 10 raised power minus 7 molar. This is the total H positive ion concentration in the container. Now calculate the pH of the solution. P stands for minus log of net H positive ion concentration in the container, which is minus log. This is 2 into 10 raised power minus 7. Now a bit of maths is used here. Minus log of m into n. It is log m plus log of n. So minus, I'm writing as such. This is 0.3. Log of 2 is 0.3. Log of m raised power n. And log m. So minus 7 comes to the front. So the final answer comes out to be 6.7. So 6.7 is the actual pH of this particular solution which we have taken over here. Right? So whenever this sort of a question comes, do not make a mistake. Right? And when do you have to use this kind of the procedure? If the pH of the acid comes out to be 7 or greater than 7, at that point of time, you have to take into consideration the H positives which were already coming from water. You have to consider those H positives as well, which were already there in the water. Perfect. I hope this is clear. Moving on to one more. 10 raised power minus 4 molar NaOH. 10 raised power minus 4 molar NaOH. 10 raised power minus 4 molar NaOH aqueous solution. How do we get its pH? First of all, my dear students, NaOH, how will it undergo dissociation? NaOH will undergo dissociation as Na positive plus what? Plus OH negative. This is how it will undergo dissociation. Now at time t is equal to 0, what is the concentration of NaOH? 10 raised power minus 4 molar. This is 0, this is 0. Now tell me, is NaOH strong base or weak base? It's a strong base. It will get completely ionized. This will be 0. 1 mole gives 1 mole, 10 power minus 4 gives 10 power minus 4 molar. Similarly, this will be 10 raised power minus 4 molar. Can you let me know what is the OH negative concentration which you are getting here? It is 10 raised power minus 4 molar. My dear students, if you got the OH negative concentration, can't we calculate POH? Absolutely, we can calculate POH of the solution. P is minus log. So minus log of OH negative concentration. So it becomes minus log of OH negative concentration is 10 raised power minus 4. The value comes out to be 4. So this is POH. But was I supposed to calculate POH? No. I was supposed to calculate pH. Already you know, pH plus POH at 25 degrees centigrade. That's 14. So pH will come out to be 14 minus POH. So 14 minus 4 comes out to be 10. So 10 is going to be the pH of this resulting solution. I hope this is clear. Right? Let's have a look on one more example in which you can do a mistake. 10 raised power minus 8 molar NaOH. 10 raised power minus 8 molar NaOH. 10 raised power minus 8 molar NaOH aqueous solution. Calculate its pH. How exactly you're going to do it? Again, my dear students, a similar procedure. So first of all, you know, your NaOH, when you introduce it into water, how it's going to get dissociated. It will undergo dissociation as Na positive aqueous plus OH negative aqueous. This is how it will undergo dissociation. Now tell me one thing. Initially, at time t is equal to 0, what is the concentration of NaOH? 10 raised power minus 8 molar. So this has to be 0. This has to be 0. Now, it is a strong base. It will get completely dissociated. This will be 0. This will be 10 raised power minus 8 molar. This is again 10 raised power minus 8 molar. Right? Now, you can do a mistake here. And what is the mistake? Let's wait for it. See guys, if I ask you, what is the OH negative concentration which is coming from the base? 10 raised power minus 8 molar. If you got OH negative concentration, can't we calculate POH, which is minus log of OH negative concentration? The value comes out to be 8. So if POH is coming out to be 8, that means pH will be 14 minus 8. That means pH should be 6. pH should be 6. pH is equal to 6. Does it represent acidic or basic solution at 25 degrees centigrade? It represents acidic solution, right? But is NaOH aqueous? Is it acidic or basic? It is actually basic. But from here, it's coming out to be acidic. That means some mistake we are doing. What is that mistake? Try to rectify it. Try to rectify it, dear students. Basically, when you are introducing NaOH in water, already water is a weak electrolyte. So from water, already there will be some OH negatives, which will be in equilibrium with H2O, right? So already there were OH negatives present in the container, which have come from water. How much was that? 10 raised power minus 7 molar at 25 degrees centigrade. Already these many OH negatives were there in the container. Now you are adding NaOH into that water. So OH negative concentration which is coming from NaOH, that is 10 raised power minus 8 molar. Already in the container there were 10 raised power minus 7 molar OH negatives due to water. Now this much molar concentration of OH negative is coming from NaOH. Now if I simply ask you, what is the net OH negative concentration in the container? You will say this plus this, right? 10 raised power minus 8 plus 10 raised power minus 7. This is the total, this is the net OH negative concentration which is present in the container. Now my dear students, try to understand one thing. If I take 10 raised power minus 8 common, it's going to be 10 raised power minus 8 divided by 10 raised power minus 8 plus 10 raised power minus 7 divided by 10 raised power minus 8. Correct? This is the net OH negative concentration. So I can say net OH negative concentration is equal to 10 raised power minus 8. This value is 1 plus 10 raised power minus 8 goes up, it comes out to be 10. So 10 plus 1 is 11. So it's 11 into 10 raised power minus 8 molar. This is the net OH negative concentration which is present in the container. Once you get the net OH negative concentration, you can easily calculate POH. P stands for minus log. P stands for minus log. Minus log of net OH negative concentration, which is minus log of 11 into 10 raised power minus 8. You can write it like this, minus log of 11 plus log of 10 raised to the power minus 8. Now A bit of calculation is needed. A bit of calculation is needed. I'm calculating it over here. So it's going to be minus log 11. Do remember it's 1.05. Log of m raised power n. N log m. So minus 8 comes to the front. So the value will be 6.95. So this 6.95, what is it? It is the pOH basically. It is the pOH. Now calculate the pH. It's going to be 14 minus pOH. The value has to be 7.05. So 7.05 is the actual pH of the solution which we were supposed to calculate. So whenever you see this sort of equation, do not commit a mistake, right? Do not commit a mistake. So in short, whenever by following the general procedure, pH of the basic solution comes out to be 7 or less than 7, at that point of time, take the OH negatives coming from water into consideration as well. And then calculate the net OH negative concentration, get the pOH, and finally get the pH. That's all. Yeah? Perfect. I hope these sort of things you can easily do. You can easily solve. Now, there are a few more mistakes you might do in the basic things. For example, you have got 0.1 molar H2SO4 aqueous solution. Just tell me one thing. How H2SO4 undergoes dissociation when you introduce it into water? It will get dissociated as 2 times H positive aqueous plus SO4 di negative aqueous. Right? That's how it will undergo dissociation. Tell me one thing. At time t is equal to 0. What is the concentration of H2SO4 that's given to me? 0.1 molar. This is 0. This is 0. Now H2SO4, strong acid, strong electrolyte, completely dissociated. So this will be 0. 1 mole gives 2 moles. 0.1 molar will give 0.2 molar. 1 mole gives 1 mole. 0.1 will give 0.1 molar. So if I ask you, what is the concentration of H positive which we are getting here? Concentration of H positive which we are getting here, that is 0.2 molar. That means 2 into 10 raised power minus 1 molar. What are we supposed to calculate? We are supposed to calculate pH. P stands for minus log. Minus log of what? Minus log of H positive concentration. So minus log of H positive concentration is 2 into 10 raised power minus 1. Now a bit of maths is needed. That's all. A bit of maths is needed. So I would say pH has to be equal. Minus you're writing as such. Log of m into n. It becomes log of m plus log of n like this. So pH will come out to be minus. Log of 2 is 0.3. Log of m raised power n. And log m. So the value comes out to be 0.7. So 0.7 is going to be the pH of this particular solution. Yes? Yes, these lectures are enough. Is it clear, guys? Is it clear? Say yes or no in the chats quickly. All right, one more thing. Look at the second question. Look at the second question. BaOH whole twice. How will it undergo dissociation? Ba di positive plus 2 times OH negative. So if I ask you directly, what will be the OH negative concentration? It will be 2 times 10 raised power minus 3. This is the OH negative concentration. If I ask you what is pOH, minus log of 2 into 10 raised power minus 3, which is minus log 2 is 0.3 and log of m raised power n. It will be minus 3 at the end. The value is 2.7. So pOH is 2.7. So pH is going to be 14 minus pOH. The value has to be 11.3. Right? Done and dusted. Nothing to worry about these questions. Perfect? Perfect, people? Is that clear? So these sort of mistakes you can do. Right? So whenever you solve these basic questions, try to dissociate your electrolyte in a proper way. Do not just write H positive and OH negative. Do not just write H positive SO4 di negative. No. Yeah? Perfect. Is that clear till here? Say yes or no in the chats. Say yes or no in the chats. Say yes or no in the chats quickly. Now comes one more case. Calculation of a pH of a mixture of strong acids or strong bases. This particular topic I'm going to break in 3 parts. I'm going to break in 3 parts. Case 1. For example, you are mixing two acidic solutions, strong acid 1 plus strong acid 2. Let's say in the container you have got two acidic solutions. After mixing these acidic solutions, I will be getting a resulting solution. And for example, I'm supposed to calculate the pH of this particular resulting solution. Let's say I'm supposed to calculate pH of this resulting solution. This is one more case. This is the first case over here. For example, you have got a mixture of two strong acids. After mixing two strong acids, we'll be getting a resulting final solution. How do we calculate pH of that final resulting solution? That's important. How do we do it? Try to understand how exactly we are going to do it. Yeah? Try to understand how exactly we are going to do it. Before showing you the procedure of solving the question, let me teach you a few more things. My dear students, let me tell you. Since you know molarity is equal to number of moles of solute divided by volume of solution in liters. I assume everyone would be knowing this. Molarity of the solution is equal to number of moles of solute divided by volume of solution in liters, right? So from this particular equation, can't we calculate number of moles of solute? Molarity of the solution multiplied by volume of solution in liters. Agreed? Let's say you are given with a solution whose molarity you know, whose volume in liters you know. You just have to multiply these two. You'll be getting the moles of solute in the solution. In the similar way, in the same equation, if you use volume of the solution in ml, then you'll be calling it as number of millimoles of solute. You'll be calling it as number of millimoles of solute. So these are the two things which I would want all of you to remember right now. Why is that? Why is that? You'll get the idea in some time. So first, let me know in the chats if all the things are clear till here. Yeah? Okay. Now guys, understand what exactly I'm going to do. I'm going to start with a question so that you can understand it properly. Calculate the pH of the following mixture. Try to understand what exactly you are mixing. This is the acidic solution. This is the acidic solution. So basically, you're mixing two strong acids, H2SO4, HCl. You're mixing two strong acids, right? After mixing these two strong acidic solutions, you'll be getting a resulting solution. You'll be getting a final solution whose pH you have to calculate. Now, how exactly? How exactly? Try to understand. Try to understand properly. First of all, the first solution is your H2SO4 aqueous solution. The first solution is your H2SO4 aqueous solution. Can you let me know how this H2SO4 aqueous solution would have undergone dissociation? How this H2SO4 would have undergone dissociation? It is a strong acid, this is the strong acid. I'm talking about the first acid. This H2SO4 would have undergone dissociation as 2 times H positive aqueous plus SO4 di-negative aqueous. This is how it would have undergone dissociation. In the similar way, how this HCl would have undergone dissociation? HCl would have undergone dissociation as H positive aqueous plus Cl negative aqueous. Correct? Now, my dear students, try to understand. Time t is equal to 0. The first solution which we have, I know its molarity, I know its volume in ml as well. Molarity of the solution multiplied by volume of solution in ml. What does it give me? It gives me number of millimoles of solute. Number of millimoles of solute. So if I ask you, how many millimoles of H2SO4 do we have? This multiplied by this, the value comes out to be 200. So we have got 200 millimoles of H2SO4 in the beginning, right? This will be 0. This will be 0. Correct? Now, dear students, H2SO4, it's a strong acid. It will undergo dissociation, complete dissociation. So I'll be left with 0 millimoles of H2SO4 in the solution. 1 mole of H2SO4 gives 2 moles of H positive. So 200 millimoles will give 400 millimoles of H positive. Right? Similarly, 1 mole gives 1 mole. So 200 will give 200. So my dear students, tell me one thing. How many millimoles of H positive? How many millimoles of H positive we are getting from H2SO4? How many millimoles of H positive we are getting from H2SO4? We are getting 400 millimoles of H positive from H2SO4. Right? Similarly, tell me how many millimoles of HC, how many millimoles of H positive will be getting from HCl? You can do that as well. Say, initially at time t is equal to 0. See, the molarity of HCl is given, volume of HCl in ml is given. So this multiplied by this, molarity multiplied by volume in ml, that gives me the millimoles of solute. So we have got 200 millimoles of HCl in the beginning, right? So this has to be 0, this has to be 0. Now HCl, complete dissociation, 0. 1 mole gives 1 mole. So from 200 millimoles, you will be getting 200 millimoles of H positive. Similarly, this will be 200 millimoles of Cl negative. So if I ask you, how many millimoles of H positive you are getting from HCl, you are getting 200 millimoles of H positive from HCl. Now, my dear students, if I ask you how many total millimoles of H positive are there, how many total millimoles of H positive are there in the final solution? 400 plus 200 makes it 600. So in total, in the final solution, there are 600 millimoles of H positive, right? There are 600 millimoles of H positive. Can I say millimoles divided by volume, that gives me the molarity? Millimoles divided by volume, that gives me the molarity. So if I ask you, what is the molarity of H positive in the final solution? Molarity means concentration. Molarity means concentration. If I ask you, what is the net H positive concentration? Total H positive concentration in the final solution. It's going to be millimoles, total millimoles of H positive divided by total volume of the resulting solution. 400 plus 400 makes it 800. So it's going to be 3 by 4. So 3 by 4, what is it? It is the net H positive ion concentration. It is the total H positive ion concentration, right? Since you got the total H positive ion concentration, how do you calculate pH? pH stands for minus log of net H positive ion concentration, which is minus log of P divided by 4, which is minus times log of M by N is a log of M minus log of N, right? So it is minus. Log of 3 is, how much is log of 3? 0.47. Log of 4 is 0.6. The final value comes out to be 0.13. So 0.13 is the pH of the final solution. 0.13 is the pH of the resulting solution. I hope this sort of a question you can easily solve from now onwards. So do remember, get the millimoles of H positive from first acid, get the millimoles of H positive from the second acid, get the total millimoles of H positive in the resulting solution, divide that by the total volume in ml, you'll be getting the concentration, net H positive ion concentration. And then you can easily get the pH of the resulting solution, minus log of net H positive ion concentration. That's all. Agreed? Is this clear to every single guy? Quickly in the chats. Quickly in the chats, people. One more type of the question. A 50 ml solution of strong acid of pH 1. So we have got a strong acid whose pH is 1. Whose pH is 1. Volume is equal to 50 ml. Right? Is mixed with 50 ml solution of strong acid. We have got one more strong acid whose pH is 2 and whose volume is how much? Whose volume is 50 ml. Now you are mixing them. After mixing them, you'll be getting a resulting solution and you have to calculate pH of this particular resulting solution. It's an easy question. It is an easy question, guys. Try to understand. pH of the first acidic solution is 1. Does that mean H positive concentration is equal to 10 raised per minus 1 molar? Right? pH of the second acidic solution is 2. So does that mean H positive ion concentration from this particular solution is going to be 10 raised per minus 2 molar? Agreed? Right? Simple. Molarity multiplied by volume in ml, it gives me millimoles. So what about the millimoles of H positive coming from first strong acid? This multiplied by this value is 5. What about the millimoles of H positive? Millimoles of H positive coming from second solution. This multiplied by this, it is 0.5. If I ask you, how many total millimoles of H positive are there in the resulting solution? This is 5 plus 0.5, which makes it 5.5. These are the total millimoles of H positive. These are the total millimoles of H positive in the resulting solution. Tell me what is going to be the net H positive ion concentration in the final solution. Total millimoles of H positive divided by total volume. Total volume is 50 plus 50 makes it 100. right? If you got the net H positive ion concentration, calculate the pH of the resulting solution, which is minus log of net H positive ion concentration. So pH has to be equal to minus log of net H positive concentration is 5.5 divided by 100 molar. So pH has to be equal to minus times log of m by n, which is log of m minus log of n. Now, as per the question, it's mentioned that log of 5.5, that is 0.74, minus log of 100. Log of 100 can be written as log of 10 raised power 2, which is 2 log 10. So it's going to be final 2. So the final answer is going to be 1.2x. 1.26. 1.26 is going to be the pH of the final resulting solution. I hope you can solve this sort of equation from now on, right? Is it clear to everyone? Is it clear to everyone, people, quickly? Yes. So what was this part? This was the pH of a mixture containing two strong acids. This was the pH of a mixture containing two strong acids. In the similar way, let's say you have got two strong bases. So let me mark the heading as case 2. Two strong bases. Strong base 1 plus strong base 2. Right? You're mixing them. You have got a mixture of two strong bases. How do you calculate pH of the mixture? How do you calculate the pH of the mixture? Right? Which is formed when two strong bases react. When two strong bases basically are present in the same container. How do we do it? Similar type of scenario this is. Similar type of scenario. Try to understand what exactly I'm going to say. Just try to understand what exactly I'm going to say. For example, my dear students, you have got a strong base as BOH. BOH. Or let me call it as B1OH. It's a strong base. Or if not like this, let me frame a question over here. Let me frame a question over here. Just a second. Let me frame a question over here. $400 ml of 0.5 molar B1OH, it is a strong base, plus just a second, plus let me write it as plus 400 ml of 0.5 molar B2OH whole twice. B2OH whole twice. Right? So this is the question. This is the question. We are supposed to calculate the pH of the resulting solution. We are supposed to calculate pH of the resulting solution. You have got two strong bases. You are adding the two strong bases. You are getting a mixture of two strong bases. Get the pH of the final solution. How you are going to do it? How you are going to do it? First of all, this B1OH, just tell me how it would have undergone dissociation. B1 positive plus OH negative, right? This is how it would have undergone dissociation. Similarly, you have got B2OH whole twice aqueous. How it would have undergone dissociation? It's going to be B2 positive plus 2 times OH negative. This is how these two strong bases would have undergone dissociation. Correct? Now guys, tell me one thing. At time t is equal to 0, can you let me know how many millimoles of B1OH do we have? Can you let me know that? Quickly. Quickly, people. Quickly. Can you let me know how many millimoles of B1OH do we have? See, you know its molarity, you know its volume. Molarity multiplied by volume gives me the millimoles. So we have got 200 millimoles of this particular thing in the beginning. So this has to be 0. This has to be 0. Now this will be 0. 1 mole gives 1 mole. From 200 millimoles, you are going to get 200 millimoles of B positive. 1 mole gives 1 mole. From 200 millimoles, you get 200 millimoles of OH negative. Similarly, how many millimoles of this particular substance we have? How many millimoles of this particular substance we have at time t is equal to 0? Molarity multiplied by volume in ml. So we have got 200 millimoles of B2OH whole twice in the beginning, right? So this will be 0, this will be 0. Now this will be 0. 1 mole gives 1 mole. So from 200 millimoles, you are going to get 200 millimoles. Now 1 mole gives 2 moles. From 200 millimoles, you guys are going to get 400 millimoles, right? Now, if I ask you, how many millimoles of OH negative you are getting from this particular base? 200. How many millimoles of OH negative you are getting from this particular base? 400. If I ask you, how many total millimoles? How many total millimoles of OH negative do we have? Total millimoles. 200 plus 400 makes it 600. So total millimoles of OH negative in the resulting solution is equal to 600. So if I ask you, what about the total net OH negative concentration? Total millimoles of OH negative in the final solution divided by total volume in ml. That's 800. The value is 3 by 4. This is the net OH negative ion concentration. Right, dear students, if you got the net OH negative concentration, calculate POH. P stands for minus log of net OH negative concentration. The value will be 0.27. Will it come out to be 0.27? Just a second. How much will be the value? We have solved a similar type of question before. The value comes out to be 0.13, sorry. The value will be 0.13, right? The value over here will be 0.13. So this is the POH of the final solution. If you got the POH, calculate pH, which is 14 minus POH. The value will be 13.87. This is the pH of the resulting solution. I hope this is clear to everyone. Yes, is it clear? Is it clear, guys? Quickly. So we talked about pH of the mixture containing two strong acids, pH of the mixture containing two strong bases. Now, what is the third case? Tell me what is the third case? Third case is pH of the mixture containing a strong acid and a strong base. pH of a mixture containing a strong acid and a strong base. Strong acid and a strong base. Let's try to understand. This is slightly different, but it's simple at the same time. For example, I'm writing 100 ml of 0.1 molar H2SO4 aqueous plus 100 ml of 0.1 molar NaOH aqueous. Look at this particular scenario. This is a strong acid. Look at this particular scenario. This is a strong base. Now, you know, when acid reacts with a base, it leads to the formation of salt and water. If you have got a strong acid on one side, strong base on another side. When you put them in the same container, they'll show a reaction. Acid will react with the base. So basically, when a strong acid is to be treated with a strong base, a reaction will happen. A reaction will happen. So I would say H2SO4 will react with NaOH and it will lead to the formation of Na2SO4, and for example, you are getting water as well. Right? Clear till here? Now tell me whether this particular reaction is balanced or not. This is the reaction which is happening, correct? Tell me whether the reaction is balanced or not. The reaction is not yet balanced. So this has to be 2 times. This has to be 2 times. Now the reaction is balanced, I believe. Right? Now tell me one thing. At time t is equal to 0. Do you know the molarity of this particular solution? Yes, we know it. Do you know its volume? Yes, we know it. So molarity multiplied by volume. It will give me the millimoles of H2SO4 in the first solution. Similarly, how many millimoles of NaOH in the second solution we have? Molarity multiplied by volume. So we have got 10 millimoles of NaOH in the final solution. Correct? Now this will be 0, this will be 0. Now, my dear students, if you remember the mole concept, I had told you whenever you are given with the amounts of all the reactants, at that point of time, you will be using the concept of limiting reagent. Right? Now, the first step for the limiting reagent concept is to balance the reaction. The reaction is already balanced. After balancing the reaction, identify the limiting reagent. How do you identify the limiting reagent? Given millimoles, divided by stoichiometric coefficient. Given millimoles, divided by stoichiometric coefficient. The one which gets the lesser value, that's going to be the limiting reagent. So 10 by 1, that's 10. 10 by 2, that's 5. This one is getting the lesser value, so it has to be the limiting reagent. My dear students, if NaOH is the limiting reagent, that means it would have got completely consumed in the reaction. So I will be left with 0 millimoles of NaOH at the end. When the reaction would have stopped, when the reaction stops at that point of time, there will be 0 millimoles of NaOH in the container. Now, this H2SO4, is it going to be limiting or excess? It's going to be excess reagent. What does that mean? That means out of its 10 millimoles, there will be some millimoles of NaOH left in the container as such. Now, how do we get that? See, I will say, use the stoichiometry. Use the stoichiometry. Can I say 2 moles of NaOH reacts with 1 mole H2SO4. As per stoichiometry, absolutely clear. So 1 mole NaOH reacts with 1 by 2 moles H2SO4. So 10 millimoles of NaOH. 10 millimoles of NaOH will react with 1 by 2 into 10. The value is 5 millimoles of H2SO4. Right? So I got to know with the 10 moles of NaOH, 5 moles of H2SO4 are reacting. With 10 moles of NaOH, with 10 millimoles of NaOH, 5 millimoles of H2SO4 are reacting. How many I had taken? I had taken 10. Out of 10, how many are reacting? 5. So I would say 5 millimoles of H2SO4 will be still left in the container as such at the end of the reaction. Right? 5 millimoles of acid, H2SO4, 5 millimoles of strong acid are still left in the container as such. So tell me, will the resulting solution be acidic or basic in nature? Absolutely, it's going to be acidic. Right? Because in the final solution, we are having a strong acid. Strong acid H2SO4. Now this strong acid H2SO4, which is left in the final solution, how do you think it would have undergone dissociation? It would have undergone dissociation as 2 times H positive aqueous plus SO4 dinegative aqueous. How many millimoles of H2SO4 are left? 5 millimoles of H2SO4 are left. So this will be 0, this will be 0. Now this will be 0. 1 mole gives 2 moles. From 5 you get 10 millimoles. So I got to know the total H positive millimoles which are left in the container at the end of the reaction. So at the end of the reaction, if I ask you, how many millimoles of H positive are left in the container at the end? You'll say 10 millimoles of H positive are left in the container at the end. Right? If 10 millimoles of H positive are left in the container at the end, if I ask you, what is the net H positive concentration? It is total millimoles of H positive left in the container divided by total volume. Total volume is 100 plus 100 makes it 200. So it's 1 by 20. If you got the net H positive ion concentration, can't you calculate pH? pH of the resulting solution, final solution, minus log of net H positive ion concentration, which is minus log of 1 by 20. You just have to solve this term. Get the pH of the resulting solution. I hope this is super duper clear to everyone. Right? Clear? Is it clear, guys? Quickly. Yes? So all the cases of strong acids, strong bases, I'm damn sure is clear. This is one question which I'm giving you as the homework. Will you be able to solve this question? Just try to understand. Just tell me which kind of question is it? Is it the mixture of two strong acids? Is it the mixture of two strong bases? Is it the mixture of strong acid and strong base? Just tell me that. Just tell me that. Just tell me that quickly. Just tell me that quickly. You just need to identify what kind of mixture this is. Is it the mixture of strong acid, strong base? Is it the mixture of two strong acids, two strong bases? What is it? Once you identify what kind of mixture this is, then only you can use the concept which I gave you. Right? Right, people? So this is your homework question. And let's move on to the calculation of pH of weak acids. Calculation of pH of weak acids, weak bases, and their mixtures. Let's get to know about that. Right? Let's get to know about that. Try to understand one simple thing. Till now, we were talking about only strong acids, strong bases, and their mixtures, right? Now it's time to calculate the pH of weak acids, weak bases, and their mixtures. Let's try to understand. My dear students, for example, you have got a weak acid, HA. This is a weak acid, HA, for example, right? Now this HA, since it's a weak acid, so it will be in equilibrium with its ions. Its ions are H positive aqueous plus A negative aqueous, right? For example, the ionization constant of this weak acid is Ka. Let's assume its degree of ionization is alpha. So what exactly I have done? Try to understand. I have taken a weak acid HA. I'm introducing it into water. When I introduce it into water, it will get dissociated. Now, this acid and its ions, they are going to remain in equilibrium with each other. I'm going to get the pH of the final solution which I got. How do I get the pH of the final solution? In order to get the pH of the final solution, what do I need? I need the total H positive ion concentration in the final solution. Then take its minus log and get the answer. Right? Now, the point is like this. At time t is equal to 0, its concentration is C, this is 0, this is 0. When equilibrium is established in this reaction, it will be C minus C alpha, this will be C alpha, even this is C alpha. Now, dear students, try to write the expression for Ka, which you already know, which is C alpha square divided by 1 minus alpha, right? I am assuming that alpha is less than 0.05. Therefore, 1 minus alpha value, that will be only equal to 1, right? So from there, you can get the value of alpha, under root of Ka by C. This is something which we have discussed in the beginning. Alpha value is equal to under root of Ka by C. Now, if alpha is equal to under root of Ka by C, if I ask you, what about the H positive concentration in the container? You will say it is C alpha. So H positive concentration in the container is C times. Alpha is under root of Ka by C, right? So I would say H positive ion concentration is equal to under root of. Take this C inside. So Ka as such, this is C square divided by C. C got cancelled. So I would say H positive ion concentration here is coming out to be under root of Ka multiplied by C, or you can write Ka multiplied by C whole raised power 1 by 2. This is the H positive concentration in the solution. When you introduce weak acid into water, right? Whatever happened, happened. So the total H positive ion concentration in the container is this much, right? Now, how do we get the pH? P is equal to minus log of H positive concentration, which is KaC raised power 1 by 2. So pH of the solution comes out to be minus log of m raised power n log m. So minus 1 by 2 comes to the front. Then it's going to be log of Ka plus log of C. Correct? So what you need to do is 1 by 2 I'm writing as such, minus log of Ka stands for P of Ka, and it's going to be minus log of C. So this is one direct result. This is one direct result by means of which you can calculate the pH. You can calculate the pH of this acidic solution, which which undergoes dissociation under the stoichiometry 1:1:1, right? And I'm assuming this particular formula is valid only when alpha is less than 0.05. And in your NEET, they only ask you these sort of questions. Whose alpha is less than 0.05. They won't give you more than 0.05 case, right? So this is the expression which you have to remember. This is the expression which you have to remember to calculate the pH of weak acids, right? Which undergoes the dissociation 1:1:1. Yeah? Perfect. Is this clear? And do remember this particular result is only valid when acid's alpha is less than 0.05. I hope this is clear. My dear students, similarly, if you will be having a weak base, for example, pH of a weak base, BOH. When you introduce this weak base into water, it will undergo dissociation. B positive aqueous plus OH negative aqueous. Correct? Let's assume its ionization constant is Kb, degree of dissociation is alpha. Right? Every single thing is same. This is C, this is 0, this is 0. This is C minus C alpha, this is C alpha, this is C alpha. Correct? Now Kb expression, it's similar C alpha square divided by 1 minus alpha. Now assumption, let alpha value is less than 0.05. Therefore, Kb will be equal to C alpha square, or alpha will be equal to under root of Kb by C. If you got the alpha, under root of Kb by C. If you got alpha, under root of Kb by C, we calculate OH negative concentration, which is going to be C times alpha. So C as such, alpha is going to be under root of Kb by C. Finally, it is going to be Kb multiplied by C whole raised power 1/2. If you got the OH negative concentration, get the POH of the resulting solution minus log of OH negative net, which is Kb multiplied by C whole raised power 1/2. So it's going to be minus 1/2 as such. Then it's going to be log of Kb plus log of C. Now use a bit of calculation. You'll say POH is equal to 1/2 as such. Minus log of Kb is basically P of Kb. And then it's going to be minus log of C. This particular result is used to calculate pH of a weak base. pH of a weak base whose alpha will be less than 0.05 and which will undergo dissociation under the stoichiometry 1:1:1. I hope this is again super clear to everyone. So quickly let me know in the chats. Yes? Is it clear, people? Quickly in the chats. Is it clear? If it is clear, try to solve these questions. Try to solve this question. Calculate the pH of. It's a weak acid. It's a weak acid. Right? It's a weak acid which undergoes dissociation as CH3COH. How will it undergo dissociation? CH3CO negative plus H positive. How do we get its pH? Its pH will be equal to half of P of Ka minus log of C. Right? Minus log of C. First of all, you have to calculate, actually you have to calculate first its value, its alpha value. If alpha is less than 0.05, then you'll be using this formula. Right? And I'm sure you can calculate alpha. Alpha is equal to under root of Ka by C. Under root of Ka by C. Let me calculate alpha over here first. So alpha is equal to under root of Ka is 1.8 in 10 raised power minus 5 divided by C is 10 raised power minus 1. Root of 1.8 is 1.34 into 10 raised power minus 2. So 0.00134, which is actually less than 0.05, right? So we can use this formula. We can use this formula, right? So now, so pH is equal to half of. Now, let me tell you one thing. In majority, do remember Ka value for acetic acid. Ka for acetic acid is equal to 1.8 into 10 raised power minus 5. And acetic acid is used in majority of the cases. Do remember for once and all, minus log of 1.8 into 10 raised power minus 5. Do remember its value directly. That is 4.74. Always 4.74. Right? Now, half of P of K. P is minus log of K. Minus log of this value. That's 4.74. Minus log of C. C is the concentration of acid. It's 10 raised power minus 1. So pH has to be equal. Half of it is 4.74 log of m raised power n. It's n log m. So it's 5.74 divided by 2. That's going to be the pH of the resulting solution. That's all. Right? Similarly, this is one more acidic solution. A weak acid basically. First of all, calculate its alpha. Then get to know whether alpha is less than 0.05 or not. If it is less than 0.05, use this particular result and solve the question. And same goes for the last one as well. Yes? Is this concept clear to you quickly? Is this concept clear to everyone? Let's try to solve the second part of the question. Third part you can do on your own. It is 10 raised by minus 3 molar CH3COH. First of all, I'll try to calculate its alpha. Under root of Ka divided by C, which is under root of. Ka is 1.8 into 10 raised by minus 5. C value is 10 raised by minus 3. Root of 1.8 is 1.34. This is 10 raised by minus 1. The value is 0.134. Is 0.134 less than 0.05? No, it's not less than 0.05. Now what to do? How to solve this question? How to solve this question now? How to solve this question now? Do you have any idea of how to do this sort of a question now? In order to solve this question, you have to use the general approach. General approach, my dear student. And what is the See, you won't be using this formula for the second part of the question. You won't be using this formula for the second part of the question. This formula is only valid when alpha is less than 0.05. Here, alpha is not less than 0.05. Right? So, you'll be using the general procedure. And let's try to understand what the general procedure here is. General procedure is very simple. See, CH3COH, when gone into water, it will give CH3CO negative aqueous plus H positive aqueous. Right? Its concentration is C, which is 10 raised by minus 3 molar. This is 0, this is 0. Degree of dissociation alpha. So C minus C alpha. This is C alpha. This is C alpha. This is C alpha. Correct? Clear till here? Clear till here? Now, write the Ka expression. It's going to be C alpha square divided by 1 minus alpha. Anyways, this sort of a question won't come in your NEET examination, by the way. In NEET, they'll always give less than 0.05 case. Right? So K is given, C is given. From here you can get the alpha. So basically you'll be getting a quadratic here. You will have to solve the quadratic, get the value of alpha. Yeah? You'll be getting the value of alpha. Once you get the value of alpha, you can get the concentration of H positive. Concentration of H positive in the solution is C alpha. Alpha you'll be calculating from here. C value already you know. So H positive concentration you'll be getting. So pH will come out to be minus log of that H positive concentration. I'm understood, right? Yeah? Clear? Clear? So basically it is the concentrations which play here the role. So be careful with all this. Be careful with all these things, my dear students, right? Can you solve this particular question? Calculate the pH of 0.01 molar RNH2 solution. Kb is given. Can you give this equation a try? It's again a simpler one. See, this is water, right? I do not have to consider it. It's in liquid state. Its ectomass is unity. Nothing to do with this. Its concentration of this particular base is C, which is 0.01. So this will be 0. This will be 0. Same procedure. C minus C alpha. This is C alpha. This is C alpha. Or let's not do like this. Let's directly calculate the value of alpha first of all. Alpha is equal to under root of Kb by C. Right? Under root of. Kb is Kb is 2 into 10 raised power minus 6. C value is 10 raised power minus 2. Root of 2 is 1.4 into 10 raised power minus 2. The value is 0.014. It is actually less than 0.05. So whatever neglection we have done, that's absolutely correct. Right? So we can use the formula directly. Formula is POH is equal to, what was the formula? 1 by 2 P of Kb minus log of C, right? So POH you can calculate from here, which is half of P of Kb. So minus log of 2 into 10 raised power minus 6 minus what? Minus log of C. C is 10 raised power minus 2. Now a bit of calculation is needed. So 1 by 2. 1 by 2. It's going to be minus log of 2 plus log of 10 raised power minus 6. So it's going to be log of 2. Take minus in between. So it's log of 10 raised power minus 6. And already there is a log of 10 raised power minus 2. Perfect. Now, method of calculation. So it's going to be 1 by 2 minus times. Log 2 is 0.3. This will be 6. This will be 2. So 6 plus 2 is 8. 8 minus 0.3 is 7.7. 7.7 divided by 2. 7.7 divided by 2. So 3.75 approximately. So this is POH basically, which is 3.75. Since you got POH, now get pH, which is 14 minus POH. So which is 14 minus 3.75. The value is 10.25. This is the pH of the resulting solution. That's all. That's all, right? Simple and basic again. I hope you can solve these sort of questions, right? You should be able to solve. You should be able to solve. Okay, let me just see whether you remember the concepts which you discussed earlier in the today's session or not. Calculate the pH of this particular solution. Let me exactly see whether you remember the concepts or not. 0.1 molar HCl is mixed with 0.1 molar CH3COH. Try to understand. Weak acid, strong acid, one ion in common ion effect. Concentration of common ion is decided by the strong electrolyte. So concentration of common ion will be directly 0.1. So net H positive ion concentration is directly 0.1. So pH of the resulting solution will be directly minus log of 10 raised power minus 1. Value coming out to be 1. So 1 is the pH. No solve, nothing. Don't solve. Right? Use the common ion effect. Weak acid, strong acid, both having one ion in common. And which is the common ion? H positive. So concentration of H positive will be directly equal to the concentration of H positive coming from strong acid, which will be 0.1 only. So net H positive concentration is 0.1. Therefore, pH of the resulting solution will be 1 itself. Right? This sort of equation, you should not need pen and paper now. You should not need pen and paper now. Right? First of all, the first topic which we are going to discuss in today's session, what is that going to be? That is going to be a pH of mixtures of two weak acids. Whenever you will have a mixture of two weak acids, how do we get the pH of that particular mixture which contains two weak acids basically? So let's get to know exactly how to do this sort of a topic. Have a look, people. For example, I'm taking a weak acid HA1. Let's say this is one of the weak acid which I have, right? Similarly, I've got, for example, one more weak acid, that is HA2, right? These are two weak acids which I have, right? My dear students, this weak acid HA1, since it's a weak acid, means it's a weak electrolyte. When you put it into water, it will be in equilibrium with its ions. And its ions are H positive aqueous plus A1 negative aqueous, right? Similarly, the second weak acid which we have, when you put it into water, it's going to dissociate into its ions. And its ions are going to be H positive aqueous plus A2 negative aqueous. This is something which I hope every one of you know already, right? So dear students, imagine that these two weak acids are present in the same container. Imagine that these two weak acids, they are present in the same container. So can I say, in the container, I have got a mixture of two weak acids? Absolutely, I can say that. How do you calculate the pH of a mixture containing two weak acids, right? So imagine that these two weak acids are present in the same container. This weak acid is in equilibrium with its ions. Even this weak acid, it is in equilibrium with its ions. What I need to calculate? I need to calculate the pH of the mixture that contains these two weak acids, right? Now, assume certain things. Let's assume that at time t is equal to 0, its concentration is C1. This will be 0, this will be 0, right? Let's assume degree of ionization of this weak acid is alpha 1. So I would say at equilibrium, the concentration of HA1 present in the container is going to be C1 minus C1 alpha 1, correct? The concentration of H positive from this weak acid, it is C1 alpha 1. This will be also C1 alpha 1, right? In the similar way, my dear students, let's assume that its concentration is C2. This is 0, this is 0. Let's assume the degree of ionization of this second weak acid is alpha 2. So at equilibrium, I'll be left with C2 minus C2 alpha 2. This is going to be C2 alpha 2. And this is also going to be C2 alpha 2, right? Now, my dear students, these two weak acids, they are present in the same container basically. From this weak acids, you are getting H positives in the container. From this weak acids, you are also getting H positives in the container. Can you just let me know what is the total H positive ion concentration? Can you let me know what is the total H positive ion concentration coming from this acid as well as coming from this acid? So the total H positive ion concentration in the container is just going to be C1 alpha 1 plus C2 alpha 2. Correct? This is the total H positive ion concentration present in the container. Now, my dear students, if this is the total H positive ion concentration present in the container, can't you calculate pH of the final solution, which is just going to be minus log of H positive net, right? Imagine C1 value is given to you, alpha 1 is given to you. Imagine C2 is given to you, alpha 2 is given to you. If all these parameters are given to you, you can calculate the total H positive ion concentration present in the container. And once you get the total H positive ion concentration in the container, you can just multiply that with minus log. You'll be getting the pH of the resulting solution. As simple as that. Number one. Number two, my dear students. Number two. Imagine that alpha 1 and alpha 2, it is not given to us. Imagine there will be some questions in which alpha 1, alpha 2 won't be given to you. You will be given with Ka1 and you will be given with Ka2. What is this Ka1 and Ka2? Ka1 is something which I call as dissociation constant, ionization constant of this weak acid. Ka2 is something which you call as dissociation constant or ionization constant of this second weak acid. Now, in some questions, you won't be given with alpha 1, alpha 2. You will be given with Ka1, Ka2 values. Remember, directly from now onwards, you can calculate the total H positive concentration in one more way as well. It is going to be Ka1C1 plus Ka2C2 ka root. This is one more way of calculating the total H positive ion concentration present in the final solution, right? And my dear students, whenever a question is asked related to this particular topic, in your NEET examination, they'll be always giving the stoichiometry 1:1:1 only. Similarly, 1:1:1 only. They are not going to change the stoichiometry coefficients for the NEET examination particularly, right? So do remember there are two ways to calculate the total H positive ion concentration. One is this way, if alpha values are given to us. One is this way, if Ka1, Ka2 are given to us, right? Either ways you can calculate. Either ways you can calculate the total H positive ion concentration in the container. Just multiply that with minus log and get the pH of the final solution. As simple as that, right? I hope this particular point is absolutely clear to you. The important point here is, which I'm going to underline so that you can remember it, that is how do we calculate the total H positive ion concentration. And this is how you calculate exactly the total H positive ion concentration, either by this particular result or by this particular result, right? Similarly, my dear students, there can be one more scenario. There can be one more scenario. Just try to understand what exactly I'm going to say. I'm writing pH of a mixture. I'm going to write pH of a mixture containing two weak bases. pH of a mixture containing two weak bases. This can be one more question which can be asked, right? And I'm going to write it in the form of the heading, pH of the mixture containing two weak bases. Imagine that in the same container, we have got two weak bases. Imagine that in the same container, we have got two weak bases. The first weak base is, for example, B1OH. This is the first weak base. The second weak base, for example, is B2OH. This is the second weak base. Imagine both these weak bases are present in the same container. Since this is the weak base, so in the container, it is going to remain in equilibrium with its ions. And its ions are B1 positive aqueous plus OH negative aqueous. Similarly, this particular weak base in the container, it's going to remain in equilibrium with its ions, and its ions are B2 positive aqueous plus OH negative aqueous. Right? Both these weak bases, they are present in the same container. This weak base is in equilibrium with its ions. This particular weak base, it is in equilibrium with its ions. Right? Now, the same procedure which will be following. Let's assume its concentration initially is C1. This is 0. This is 0. Let's assume degree of ionization is alpha 1. So I would say at equilibrium, the concentration of this particular weak base is C1 minus C1 alpha 1. This is going to be C1 alpha 1. This is again going to be C1 alpha 1. Right? In the similar way, let's assume that at T is equal to 0. This is C2, for example. This is 0. This is 0. Degree of ionization, for example, is alpha 2. So I would say at equilibrium, I'll be left with C2 minus C2 alpha 2. This is going to be C2 alpha 2. Even this is going to be C2 alpha 2. Right? Now I can say, since both the weak bases, they are present in the same container. From this weak base, OH negatives are liberated in the solution. From this weak base, also OH negatives are generated in the container, in the solution. If I ask you, my dear students, what is the total net OH negative concentration present in the final resulting mixture? OH negatives coming from first base, that is C1 alpha 1. OH negatives coming from the second base, it is C2 alpha 2. So if I ask you, what is the net OH negative concentration present in the final resulting mixture? It is just going to be C1 alpha 1 plus C2 alpha 2. This is one of the way by means of which you can calculate the total OH negative concentration present in the resulting mixture. Or there is one more way. I'm not deriving the result, I'm just giving you the result. Imagine that alpha 1, alpha 2 is not given. Imagine that KB1 value and KB2 value is given to us. What is KB1? It is the ionization constant of the first weak base. KB2 is the ionization constant of the second weak base. There is one more way. It's going to be under root of KB1C1 plus KB2, and it's going to be C2, right? So these are basically the two ways by means of which you can calculate the total net OH negative ion concentration present in the resulting solution. And once you get the total OH negative ion concentration in the resulting solution, you can easily calculate POH, which stands for minus log of OH negative net concentration. And once you get POH, you can use the result pH plus POH is equal to 14 at 25 degrees centigrade. From this particular result, you can easily calculate pH. So this is the general way of solving the questions which are based on the pH of a mixture containing either two weak acids or two weak bases. I hope this is clear to everyone. Just let me know once in the chats quickly. Just let me know once in the chats quickly, every one of you. Just let me know once in the chats quickly. Yes? Perfect. All right, let's try to solve certain questions so that you can understand how these concepts are exactly used. Okay, let's try to solve certain questions. For example, this is the question. From one particular question, you'll understand the topic properly. I'm sure about that. See guys, calculate the pH of 0.1 molar formic acid, which is mixed with 0.1 molar acetic acid. So basically, you are given with two weak acids. One is your formic acid, HCOOH. One is your acetic acid, CH3COOH. So first of all, both are the weak acids. Both are the weak acids, right? Now, both these weak acids are present in the same container. So we have got a mixture of two weak acids. And few minutes back only, I told you, whenever you have got a mixture of two weak acids, right? Like formic acid and acetic acid, how they are going to undergo dissociation. HCOH will be in equilibrium with H positive plus HCO negative. Similarly, CH3COH, that will be in equilibrium with CH3CO, negative plus H positive. So, as you can see, assume 40% of both the acids getting ionized. So, assume 40% of both the acids getting ionized. So, alpha 1 is 0.4, even alpha 2 is 0.4. The concentration of both these acids is same. The concentration of both these acids is same. C1 value is 0.4, even C1 value is 0.1. Even C2 value is also 0.1, right? Concentration of both these weak acids is same. Now, few minutes back only I told you, how do we get the net H positive ion concentration? So I would say the net H positive ion concentration is simply going to be C1 alpha 1 plus C2 alpha 2, right? C1 value is given, alpha 1 is given, C2 is given, alpha 2 is given. Put all the values, you'll be getting the net H positive ion concentration in the final solution. Once you get the net H positive ion concentration, you can easily calculate pH, which stands for minus log of H positive net. That's all. Isn't it simple, my dear students? Say once in the chats if this particular question you can easily solve from now onwards, right? So basically, this acid is giving the H positive ion concentration as C1 alpha 1. This particular acid is also giving the H positive ion concentration in the same container, and that will be C2 alpha 2. I would say the total H positive ion concentration is going to be C1 alpha 1 plus C2 alpha 2. Now C1, C2, alpha 1, alpha 2, it's given to us, right? You'll be getting the net H positive concentration, and eventually you'll be getting the pH of the resulting pH of the final solution. Is this clear? Is this clear to everyone? Say yes or no in the chats. Say yes or no in the chats quickly. Quickly, my dear students, quickly. Right? Let me know in the chats quickly if this is clear. Perfect. Or if you want me to solve this, I can do that too. C1 alpha 1, 0.4 into 0.01 makes it 0.04 plus C2 alpha 2, this into this, it's also going to be 0.04. So the value is 0.08, which can be written as 8 into 10 raised power minus 2, right? 8 into 10 raised power minus 2. Perfect. 8 into 10 raised power minus 2. Yeah. Now, minus log of net H positive concentration, minus log of 8 into 10 raised power minus 2. You should be able to solve this. It's going to be minus log of m into n. It's going to be log of m plus log of n. Simply like this. So minus you are going to write as such. It's going to be log of 2 raised power 3 plus log of 10 raised power minus 2. Log of m raised power n. N log m. So minus 2 comes to the front. Right? Log 10 eventually is 1. Now this is minus of. This is going to be 3 log 2. 3 log 2 is 0.3 and this is going to be minus 2. So it's going to be 3 into 0.3. How much that will be? 0.9. So 2 minus 0.9 is just going to be 1.1. So 1.1 is basically going to be the pH of the final solution. 1.1 is going to be the pH of the resulting solution. I hope this is clear to everyone. Right? Right? So net H positive ion concentration you got. You just multiplied that with minus log and you got the pH of the final resulting solution. I hope you can solve these sort of questions from now onwards. Now imagine if alpha 1, alpha 2 was not given to us. If we were given with Ka1 and Ka2 value, then how would you calculate H positive concentration net? Then it's going to be under root of Ka1 C1 plus Ka2 C2. From there you can calculate the H positive net concentration, multiply that with minus log, get the pH of the resulting solution. Yeah? Clear till here? All right. Now, guys, there is one more simple topic, that is a relative strength of two weak acids. What does this exactly mean? A relative strength of two weak acids. See, imagine that you have got a weak acid in one container. You have got one more weak acid in one more container. So imagine you have got two containers. First container contains first weak acid. Second container contains second weak acid. Now, among these two weak acids, which one is comparatively strong? Among these two weak acids, which one is comparatively strong? How do we check that? How do we check that? Try to understand one thing. For example, I have got a weak acid HA1 present in the container. So this weak acid HA1 in the container, it's going to remain in equilibrium with its ions. Its ions are H positive aqueous plus A1 negative aqueous, right? I'm assuming that initially concentration of this weak acid is C1, degree of dissociation is alpha 1, and its dissociation constant is Ka1. These are the things which I'm assuming, right? Now similarly, we have got one more container that contains weak acid HA2, and this HA2 is going to remain in equilibrium, that is H positive aqueous plus A2 negative aqueous. These are going to be its ions with which it's going to be in equilibrium with. Yeah. Now same procedure. Time t is equal to 0. Let's assume its concentration is C2. Degree of ionization is alpha 2. And let's assume the ionization constant of this weak acid is Ka2, for example. Right? Use the same procedure. So initially this has to be 0. This has to be 0. Now at equilibrium, the concentration of HA1 is going to be C1 minus C1 alpha 1. This is going to be C1 alpha 1. This is also going to be C1 alpha 1. Now, this is C2, this is 0, this is 0. At equilibrium, this is going to be C2 minus C2 alpha 2. This is going to be C2 alpha 2. Even this is going to be C2 alpha 2, right? Agree till here? Now, my dear students, how many containers we have? We have got basically 2 containers, right? Let me represent it in the same manner. So, this is the first container, right? Similarly, this is the second container. So we have got basically 2 containers containing 2 weak acids which are in equilibrium with their ions, right? Now, my dear students, if I ask you, what is the concentration of H positive which we are getting from this particular weak acid? I would say the concentration of H positive from weak acid number 1. That is coming out to be how much? That's coming out to be C1 alpha 1. Similarly, what is the concentration of H positive in the second container? Concentration of H positive which you are getting from this particular acid, right? In the second container, that is C2 alpha 2. Now, let me clearly tell you, when you talk about strength of an acid, strength of an acid, it is directly proportional to H positive ion concentration in the container. It is directly proportional to H positive ion concentration in the container. More the H positives in the container, more the concentration of H positives in the container, stronger is going to be the acid. As simple as that. So strength of acid, it depends on the H positive ions which you are getting from the acid. More the H positive ions you are getting from the acid, stronger is going to be the acid, right? So do remember, strength of acid, that is directly proportional to the concentration of H positive. So can I say something like this? Can I say strength of acid 1 divided by strength of acid 2 will be equal to concentration of H positive coming from acid 1 divided by concentration of H positive coming from acid 2. So what is the concentration of acid H positive coming from acid 1? C1 alpha 1, and this is C2 alpha 2. You already know it, right? Now, my dear students, again one more thing. C1. What is alpha 1 basically? How do we calculate alpha 1? Alpha 1 can be written as under root of Ka1 divided by C1. I hope you remember in the last session we have discussed. If alpha is less than 0.05, then alpha has to be under root of Ka1 divided by C1, right? Similarly, denominator C2 and alpha 2 is just going to be under root of Ka2 C2. Now, dear students, the final expression will be something like this. Under root of Ka1 C1 divided by Ka2 C2. So, my dear students, whenever you want to compare the acidic strengths of 2 weak acids, these are the 2 results by means of which you can compare the acidic strengths of the 2 weak acids. Imagine that we are given with alpha 1, alpha 2, C1, C2. Imagine that we are given with all the parameters. When you put all the parameters here in this particular equation, you'll be getting a value. Let's say the value of this particular term. Let's imagine that the value of the whole term is equal to 3. What does that mean? That means strength of acid 1 divided by strength of acid 2. That came out to be 3. What does that mean? That means acid 1 is 3 times stronger than that of acid 2. As simple as that. That's what we were supposed to compare, right? We were given 2 weak acids present in 2 different containers. We were supposed to check which weak acid is comparatively strong. We got to know the H positive coming from the first weak acid. Then we got to know the H positives coming from the second weak acid. More the H positives coming from the acid, stronger is going to be the acid. As simple as that, right? So do remember this particular scenario as well, right? So this is how you compare the strengths of two weak acids. Strength of acid 1 divided by strength of acid 2 is equal to C1 alpha 1 by C2 alpha 2, or under root of Ka1 C1 divided by Ka2 C2, right? I hope this is perfectly clear to everyone, right, people? So my dear students, with this, we are basically done with the pH, right? Now we are going to move into some different topics. We are going to discuss salt hydrolysis, we are going to discuss buffer, and we are going to discuss solubility. These are the three important topics which students find difficult basically. But again, I'm telling you, I'm going to start these topics exactly from the scratch itself. So before doing the salt hydrolysis, I need to teach you one simple concept so that there'll be no issues in understanding the salt hydrolysis concept. Yeah? Try to understand what I'm going to say. I'm marking the heading as a relation between Ka and Kb. A relation between Ka and Kb for a conjugate acid-base pair. For a conjugate acid-base pair. Try to understand what exactly I'm going to say. Relation between a conjugate acid-base pair. Imagine that I've got an acid Ha. Imagine that I've got a weak acid Ha. Now imagine that I'm going to introduce this weak acid into water. I'm going to introduce it into water. If it is a weak acid, that means it's a weak electrolyte. So it has to remain in equilibrium with its ions. Its ions are H positive aqueous and A negative aqueous. Right? As simple as that. Now, dear students, understand one thing. This acid, after losing H positive, it is getting converted into A negative. This particular acid, after losing H positive, it is getting converted into A negative. So I would say this acid, after losing H positive, is getting converted into A negative. So this A negative I'll be calling it as the conjugate base of this particular acid. Acid, after donating H positive, it gets converted into A negative, for example. So A negative I'll be calling as the conjugate base of the acid. For example, you have got the acid Hi, right? When you put it in water, it gets converted into H positive plus I negative. So after the liberation of H positive, it got converted into I negative. So if this was the acid, then after the donation of H positive, I'll be calling this I negative as the conjugate base of the same acid. Right? I'll be calling it as the conjugate base of the same acid. I hope this is something which you already know, right? Now, my dear students, try to understand. Since I told you the acid, after the liberation of H positive, it got converted into A negative. A negative I'm calling as conjugate base of the same acid, right? So Ha and A negative. Ha and A negative. These are the conjugate acid-base pairs. These are the conjugate acid-base pairs, right? Now, since you have introduced this acid into water, since it's a weak acid, so it's remaining in equilibrium with its ions, correct? Let's assume that the ionization constant of this weak acid is, for example, Ka. Let's assume that the ionization constant of the weak acid is Ka. If the ionization constant of the weak acid is Ka, how do I write the expression of Ka? It is going to be concentration of H positive raised power 1, concentration of A negative raised power 1 divided by concentration of Ha raised power 1. This is how you are going to write the expression of Ka, right? Now, my dear students, try to understand one thing. When you introduce this acid into water, it gave away H positive and it gave A negative. This conjugate base A negative, which is liberated, which is produced, this conjugate base is further going to interact with water. Since you are introducing acid into water, so already in the container there was water, and in that water you are introducing acid. Now the acid is remaining in equilibrium with its ions. This A negative, which is the conjugate base of the same acid, the conjugate base is further going to interact with the rest of the water in the container. It is going to interact with the rest of the water in the container. Now what's going to happen? This conjugate base is going to interact with the rest of the water. Now water already has two types of ions in it, H positives and OH negatives. Can you let me know with which ion, H positive or OH negative, with which ion this A negative is going to interact? I would say this A negative will interact with H positive, right? And when A negative interacts with H positive, it's going to lead to the formation of HA aqueous and you'll be left with OH negative. You will be left with OH negative. Perfect. My dear students, let's assume that the ionization constant of this conjugate base, A negative, that's Kb. Kb is the ionization constant of this conjugate base, A negative, which interacted with the water. Can you write the expression for Kb over here? Absolutely, you can do that. Start with the product. It is concentration of HA raised power 1, concentration of OH negative raised power 1 divided by concentration of A negative. Right? That's how you are going to write the Kb expression. You got the Ka expression, you got the Kb expression. Now, dear students, if I just want you to multiply Ka with Kb, see what you'll be getting exactly. What is the Ka value? Ka value is concentration of H positive, concentration of A negative divided by concentration of HA multiplied by Kb. Kb expression is concentration of HA multiplied by concentration of OH negative divided by concentration of A negative. Now see which all terms will get cancelled out. So I would say HA will get cancelled out. A negative will get cancelled out. So I'll be left with only concentration of H positive multiplied by concentration of OH negative. Do you remember this H positive concentration multiplied by OH negative concentration? What we used to call it? We used to call it as ionic product Kw. I hope you remember that. I hope you remember that. So I am getting one simple result over here. That is ionization constant of the weak acid multiplied by ionization constant of the conjugate base of the same weak acid. It will always be equal to ionic product of water. And if you remember, at 25 degrees centigrade, your Kw value, that is equal to 10 raised power minus 14. That's something which we have discussed already in the last session. So this is one result which I would want you guys to remember from now onwards. Right? Perfectly done. But do remember, this is the ionization constant of the weak acid. And this is the ionization constant of the conjugate base of the same weak acid. Right? If you got it exactly, can you let me know the answer of this particular thing? Just let me know in the chats. For example, I've got the weak acid CH3COH. Its ionization constant is Ka. For example, I have got one more base, NH3. Its ionization constant is Kb. Can I write Ka multiplied by Kb as Kw? Is this correct? Is this correct? Just let me know once. Is this correct? What do you think? Is this correct, my dear students? Quickly. I'm just asking you, is it correct? It's not correct, right? You know it. Ka is the ionization constant of this weak acid. And Kb has to be the ionization constant of the conjugate base of the same weak acid. Right? And if you see here, conjugate base of CH3COH will be CH3CO negative. If this is the Kb for it, then this statement makes a sense. Then this particular statement makes sense. Otherwise, it doesn't. Right? Perfect. I'm sure you can solve these sort of things from now onwards. It is just you have to remember it. Now, guys, our actual topic, that is salt hydrolysis. One of the confusing topics, right? But again, we'll be starting from the basics itself. So try to understand each and everything in detail. How do you define the salt hydrolysis? Before defining the salt hydrolysis, let me quickly show you the types of salt which we have. The types of salts which we have. Let's try to understand how many different types of salts we have. Then once you get to know how many different types of salts we have, then we can easily talk about what salt hydrolysis is all about. Right? Now, for example, if I ask you how salt gets formed, you'll directly say when acid reacts with a base, it directly leads to the formation of salt, and with that salt, you'll be getting water as well. Correct? For example, I'm taking HCl and I'm taking NaOH. HCl, when it reacts with NaOH, it will lead to the formation of NaCl. Correct? Now, which category of salt this NaCl is? Which category of salt this NaCl is? So basically, you have got Na positive, Cl negative. Na positive has come from NaOH. Cl negative has come from HCl. So, if you talk about these, this is the example of strong acid, this is the example of strong base. So, I would say this NaCl, it is the salt of strong acid and strong base. It is a salt of strong acid and strong base. As simple as that. Right? For example, let's say you have got CH3COH and you are making it react with NaOH. This CH3COH, it's a weak acid. NaOH, it's a strong base. Now, when they react, what they exactly are going to give? They are going to lead to the formation of salt. Salt is going to be CH3CONA. Right? This is the salt. And with that, you'll be getting water as well. Now, tell me one thing. This is basically CH3CO negative and Na positive. You see this CH3CO negative has come from CH3COH. Na positive has come from NaOH. So can I say this is again the salt? This is the salt of weak acid and strong base. Absolutely, this is the salt of weak acid and strong base. Right, people? As simple as that. Now, for example, let's say I have got HCl and I'm making it to react with NH4OH. So what do I get as the product? I'll be getting NH4Cl as the product here. This is the salt. So it is basically NH4 positive, this is Cl negative. Can I say this NH4 positive has come from NH4OH and Cl negative has come from HCl? This is a strong acid and it's a weak base. So I must say this is the salt of strong acid and weak base. So this NH4Cl, it is the salt of strong acid and weak base. Correct? And at the end, for example, you have got CH3COOH and you are making it to react with NH4OH. This is weak acid, even this is weak acid. Sorry, even this is weak base. Acid base will make it salt and the salt is going to be CH3COONH4. So it is basically CH3CO negative, NH4 positive. So just tell me, CH3CO negative has come from CH3COH. NH4 positive has come from NH4OH. So I would say it is again the salt of weak acid and weak base. So my dear students, first of all, you should be able to distinguish the category of the salt. You should be able to distinguish the category of the salt. I'm damn sure from now onwards, you can easily distinguish which type of salt do we have. Right? Perfect. I hope you can easily distinguish from now onwards which type of salt exactly we have. Whether we have given with the salt of weak acid, strong base, weak acid, weak base, strong acid, strong base, etc. Right? If you exactly got to know how to distinguish the salts, then let's try to understand what the salt hydrolysis exactly is all about. See guys, how do you define the salt hydrolysis? First of all, the interaction of ions of salt with water to produce either acidic or alkaline solution. The entire phenomenon is called a salt hydrolysis. What does that mean? Have a look. For example, you have got a salt AB. Let's say this is the salt AB, right? This is the salt AB. It actually contains A positive and B negative. Now, for example, you are introducing the salt in water. You are introducing the salt in water. In water, already you have H positives and OH negatives. In water, you already have H positives and OH negatives. Now, there's a possibility that the ions of the salt will interact with water. Let's assume that this A positive is going to interact with water. You tell me, with which ion of water this A positive is going to interact? I would say this A positive will interact with OH negative. So it will lead to the formation of AOH, and with that, you'll be getting this particular H positive as well, right? There was one more possibility. When you introduce salt in water, I can say the N ion of salt can also interact with water. So if the N ion has to interact, with which ion of water is going to interact? It's going to interact with H positive. So it will lead to the formation of HB. And with that, you'll be getting OH negative as well. The interaction of ions of salt with water to produce either acidic or alkaline solution. The phenomenon is called as salt hydrolysis. Over here, in the first case, it is the cation of the salt which interacted with water. In the second case, it is the anion of the salt which interacted with water. Do remember, when cation of the salt interacts with the water, this hydrolysis is what you call as cationic hydrolysis. This is what you call as cationic hydrolysis. Similarly, when anion of the salt is interacting with water, this particular hydrolysis is what you call as anionic hydrolysis. So we have to discuss these two hydrolysis in detail. Cationic hydrolysis, when the cation of the salt interacts with the water. Anionic hydrolysis, when the anion of the salt interacts with the water. Right? Perfect. Do remember one more thing. One important thing. It will make everything easy for you. Just remember it directly from now on. Right? Do remember that ion of salt interacts. That ion of salt interacts with water, which has either come from weak acid or weak base. It is basically that ion of salt which has either come from weak acid or weak base. That ion of salt is going to interact with water. It will make a lot of things easy for you. Just remember it directly, right? No need to go into the detailed explanation, etc., etc. We just need this statement. We'll be using this statement and trying to solve the equations. That's more than sufficient for you, right? Now, let's try to analyze. Let's try to understand all the things. First of all, these are the different types of salts. For example, you are taking NaNO3. Don't look at all the headings. Just look at NaNO3. Can I say I have got Na positive, NO3 negative? Can I say Na positive would have come from NaOH and NO3 negative would have come from HNO3? This is something which you already know. It is a strong base. This is a strong acid. So I would say the salt NaNO3, it is a salt of strong acid and strong base. As simple as that, right? Similarly, the rest of the things also you can check. Yeah, the rest of the things you can also check. For example, you have got KCN. It is basically K positive, Cn negative. K positive would have come from KOH and Cn negative would have come from HCN. This is the example of strong base. This is the example of weak acid. So KCN is the example of weak acid and strong base. That's how you exactly check whether the salt is of which type. Okay. Now, one by one, we are going to discuss certain things. So first of all, we'll try to understand the salt hydrolysis of that salt which is made up of weak acid and strong base. We are going to understand the hydrolysis of the salt of weak acid and strong base. Try to understand. First of all, the example of the salt of weak acid and strong base, that is CH3CONa. It is the perfect example of what? It is the perfect example of the salt of weak acid and strong base. Now tell me one thing. When you introduce the salt into water, it is going to lead to the formation of CH3CO negative, and with that, you'll be getting Na positive. This is understood, right? When salt is introduced in water, it will be broken down into its ions. Absolutely. Let's assume that the concentration of the salt was C, right? This was zero initially. Now this salt, imagine it got entirely converted into its ions. So concentration of this ion is C molar. The concentration of this ion in the container is also C molar, right? Now guys, try to understand. Tell me one thing. You introduce salt into water. There are two types of ions present in the container now. One is CH3CO negative, one is Na positive. Na positive has come from NaOH. CH3CO negative has come from CH3COH. CH3COH is a weak acid. So this particular ion has come from weak acid over here. So I would say this particular ion is going to interact with water. It's going to interact with water. I told you that ion of the salt, only that is going to interact with the water which has come from the weak acid or weak base. This particular ion has come from weak acid, right? So it is going to interact with water. So my first reaction will be the hydrolysis reaction. So what is happening in the hydrolysis reaction? I would say CH3CO negative. It is going to interact with water. And when it will interact with water, what it will lead to the formation of? The CH3CO negative will interact with the H positive of water. right? So it's going to lead to the formation of CH3COH, and with that, you'll be getting OH negative as well. So this is my first reaction which is happening, that is hydrolysis reaction, right? That's hydrolysis reaction. Now, my dear students, once this hydrolysis is done, whatever product you get in the hydrolysis reaction, that product undergoes dissociation. So second reaction is followed by dissociation. The product which is formed in the hydrolysis, right, that product undergoes dissociation in the second step. So CH3COH, since it's a weak acid, so it will undergo dissociation. It will remain in equilibrium with its ions. Its ions are CH3CO negative aqueous. With that, you'll be getting H positive aqueous as well, right? Now let me define some terminologies. The first reaction, that's hydrolysis. The second reaction, that is the dissociation reaction of the product which you get in the hydrolysis reaction. Till now, I used to write alpha, degree of ionization. But here in the hydrolysis reaction, I won't be writing alpha. I'll be writing H. H stands for degree of hydrolysis. Terminologies are different, meaning is same. Whatever alpha used to represent, same H is representing here. Alpha we used to call as degree of ionization. Here H I'll be calling as degree of hydrolysis. Right? Degree of hydrolysis. Since the equilibrium constant of this first reaction, I'll be calling it as KH. What is KH? This is something which I'll be calling as hydrolysis constant. KH is something which you call as hydrolysis constant. Similarly, this is weak acid which is undergoing dissociation. So its ionization constant is, for example, Ka. Right? Now, dear students, try to understand few important things which I'm going to tell you. If I ask you to write KH expression, you're going to write in the similar way as we used to write equilibrium constant. KH expression. It's going to be concentration of CH3COH raised power 1, concentration of OH negative raised power 1 divided by concentration of CH3CO negative. This is how you write KH expression. Similarly, if I ask you to write Ka expression, how exactly you're going to write? You're going to write it like this. CH3CO negative multiplied by H positive divided by concentration of CH3COOH. Perfect. Now, if I just do one thing, I'll be multiplying these two things. Let's see exactly what do we get. If I multiplied KH with Ka, what all things will get cancelled out? CH3CO negative cancelled. This term gets cancelled. So I'll be left with only H positive concentration multiplied by OH negative concentration. And you already know your H positive concentration multiplied by OH negative concentration. That's basically Kw. So I'm getting one result. KH is equal to Kw divided by Ka. This is the first question which is asked. Calculate the hydrolysis constant. Whenever you are supposed to calculate the hydrolysis constant of the salt of weak acid and strong base, it's always Kw divided by Ka. Kw value at 25 degrees centigrade, you already know that's 10 raised to the minus 14. And Ka will be given to us as per the question. So the first part of the question is done. KH value we calculated. Second part of the question is how do you calculate H? My dear students, how do I calculate H? What is H? H is basically alpha of the first reaction. How you used to get alpha? Alpha used to be equal to under root of K by C. So H you'll be getting under root of KH divided by C. Right? So it's going to be under root of KH. KH is nothing, that's Kw divided by K multiplied by C, where C is the concentration of salt. Right? Where C is the concentration of salt. This is the second question which is asked. The third question which is asked, calculate the pH of the final solution. Understand, I'm not going to derive this. I'm just going to give you the result. Right? And let's try to utilize these results afterwards. Tell me, which kind of salt do we have? Salt of weak acid and strong base. We have got salt of weak acid and strong base. So base is dominating. So pH has to be 7 plus ki 7 minus. It has to be 7 plus. 7 plus half of. Which one is weak among the two? It is acid. The one which is weak, take its P value. So P of K. And at the end, it's going to be log of C, where C is the concentration of salt. This is one more question which is asked. Right? So these are the three questions which can be asked from the salt hydrolysis part. Either you'll be asked to calculate KH, hydrolysis constant, degree of hydrolysis, or pH, right? Well, we have got other types of salts as well. But I'm not going to derive all these for the other salts. I'm just going to give you the table. Remember that table and try to solve the questions. That's more than sufficient. Now, what that table is, let's try to make that table. Let's try to make that table. Have a look. I'm going to make one simple table. So just remember the results and try to utilize the results. Over here, I'm writing the type of the salt. Right here, I'm writing KH. This is H. And this is pH. Right? These are the three things which can be asked from hydrolysis part. The first is salt of weak acid and strong base. Salt of weak acid and strong base. How do I get the KH value for it? So KH is just going to be equal to KW divided by which one is weak? It is acid which is weak. So KW divided by Ka. KW divided by Ka, as you saw over here. KW divided by Ka. What is H? H is equal to under root of KW divided by Ka multiplied by C, where C is the concentration of salt. Right? How do I get the pH? It is weak acid and strong base. Base is dominating. So 7 plus half of. 7 plus half of. Which one is weak? Acid is weak. So it is P of Ka plus log of C, where C is the concentration of the salt. Right? This is your first salt. Second, for example, you have got the salt of strong acid and weak base. Salt of strong acid and weak base. First is KH. KH is KW divided by which one is weak? It is base which is weak. So I'll be writing KB. Right? So formula here is under root of H will be equal to KW divided by. It's going to be KB multiplied by C. It's going to be KB multiplied by C. Now pH. It is strong acid. So pH is going to be 7 minus half of. Which one is weak? It is base which is weak. So P of KB plus what? Plus log of C. Plus log of C. Right? Now one more. That is the salt of weak acid and weak base. Salt of weak acid and weak base. So how do I write? Its KH. Its KH will be equal to KW. Since both are weak, so Ka multiplied by Kb. Right? Its H is just going to be equal to under root of KW divided by Ka multiplied by Kb. Right? And its pH, it's always 7 plus half of P of Ka minus P of Kb. So these are certain results which you have to remove in the salt hydrolysis case. Anything can be asked and directly formula based questions will come. Trust me on that. Right? Now we will at the same time take a note of one thing. Do remember, salt of strong acid and strong base, it does not undergo hydrolysis. Salt of strong acid and strong base, it does not undergo hydrolysis. You are going to let me know the reason in the comment section afterwards. So why salt of strong acid and strong base does not undergo hydrolysis, right? You are going to let me know the answer about that. Is every single thing clear till here? Just let me know once in the chats quickly. Is every single thing clear till here? Quickly. Are all the things clear? Yeah? Perfect, guys. Perfect. Let's try to see exactly where these types of questions are asked. Oh, by the way, the table was already given to us. Why did I do all these efforts to write all these things? Anyways, let's have a look. Look at the first question. This is the first question. Calculate the degree of hydrolysis and pH of the solution. Degree of hydrolysis and pH of the solution obtained by dissolving 0.1 mole of salt in water to get 100 liters of solution. So the salt is CH3CONa. So CH3CO negative, Na positive. So it is basically CH3COONa, which can be written as CH3CO negative and Na positive. CH3CO negative has come from CH3COH and Na positive has come from NaOH. So this particular salt, it is a salt of weak acid and strong base. It is a salt of weak acid and strong base, right? So first of all, you identified the salt. Now the concentration of salt is not given to us, but what is concentration? Concentration of salt is equal to number of moles of salt divided by volume of solution in liters. So how many moles of salt we have? 0.1. What is the volume of the solution in liters? 100. So it's going to be 1 by 1000. That means 10 raised power minus 3 molar. This is the concentration of the salt. What are we supposed to calculate? Calculate the degree of hydrolysis, H. Degree of hydrolysis is equal to under root of Kw divided by Ka multiplied by C. Now, I believe all the terms are given. Kw value at 25 degrees centigrade is always 10 raised power minus 14. Ka value for acetic acid is given to us as 2 into 10 raised power minus 5. Concentration of the salt, that's 10 raised power minus 3. Can't you solve the equation? Get the degree of hydrolysis. Get the degree of hydrolysis. As simple as that. Similarly, the second part of the equation is calculate the pH of the solution. Since it's a salt of weak acid and strong base, weak acid, so it's going to be 7 plus half of P of Ka plus log of C. I believe all the terms are given to us. So it's going to be 7 plus half of P of K. P stands for minus log, right? So it's minus log of K values given to us. 2 into 10 raised power minus 5, right? Plus log of C. C value is 10 raised power minus 3. So it is the matter of calculation only. You can easily kill it and solve it. That's all. Yeah? Is it clear? Is it clear to you quickly? So this sort of a question can be solved. Can be asked. Even one more similar type of question. Just have a look. Calculate the hydrolysis constant and degree of hydrolysis for NH4Cl, whose concentration is given. Also calculate the pH. Kb is given. Again, the similar type of question. So the salt that's given to us, that's NH4Cl. So it's going to be NH4 positive, Cl negative. NH4 positive would have come from NH4OH. Cl negative has come from HCl. So this is the salt of what? It is the salt of strong acid and weak base. So first of all, you identified the salt. It is a salt of strong acid and weak base, right? Now, after identifying the salt, what do I suppose calculate? Hydrolysis constant Kh. Hydrolysis constant Kh will be equal to under root of, hydrolysis constant Kh will be equal to Kw divided by, which one is weak? It is base, right? Divided by Kb. So Kw is already equal to 10 raised power minus 14. Kb value is given to us as 1.8 into 10 raised power minus 5. Solve it, get the value of hydrolysis constant Kh. So first part is done. Second, hydrolysis constant H, which will be equal to under root of Kw divided by Kb multiplied by C. So it has to be under root of 10 raised power minus 14 divided by Kb is 1.8 into 10 raised power minus 5. And concentration of the salt should be given to us 0.1 molar. So 10 raised power minus 1. So solve it, get the answer, right? The last part of the equation, that's pH. How do you get the pH? Since it's strong acid and weak base, strong acid means pH has to be 7 minus half of. It's going to be P of Kb plus log of C. Now use the values. 7 minus half of P of Kb. P stands for minus log. Minus log of this value, already in the last session I've told you. Minus log of this value is 4.74 plus log of C. C is the concentration of salt. Concentration of salt is 0.1 molar. That means 10 raised power minus 1. So log of 10 raised power minus 1 means it is directly going to be minus 1, right? It's directly going to be minus 1. So solve it, get the pH of the solution. That's all. So is it clear to everyone? Yeah? Is it clear? Well, I believe you can easily solve these sort of questions from now on. Gopika, we'll talk about that some other time, okay? Let's concentrate on the studies now. So again, you should be able to solve these sort of questions. Again, if you have a look, this is one more question. A 0.25 molar solution of pyridinium chloride. So salt is given, pyridinium chloride was found to have a pH of this much. What is Kb? Again, it's simple. Just identify the salt. Quickly, identify the salt. It is C5, H5, NH positive, Cl negative. Cl negative has come from HCl, strong acid. This has come from pyridine. which is weak base. So it is a salt of weak base and strong acid. It is a salt of weak base and strong acid. Salt of weak base and strong acid. How do you calculate its pH? It's going to be 7 minus half of P of Kb plus log of C. Right? So pH is given to me as 2.75 is equal to 7 minus half of. P stands for what? Or let's get the pKb value first of all. P of Kb plus log of C. C is the concentration of salt, which is 0.25. 0.25 means 25 by 100, which is 1 by 4. It can be written as 1 by 4, just to make the calculations a bit easy, right? So how exactly you're going to write it? It's going to be half of P of Kb plus log of m by n is log of m minus log of n. Log 1 is 0 minus log 4. Log 4 is 0.6, right? Is equal. It's going to be 7 minus 2.75. How much that will be? That will be 4.25. 4.25. So it's going to be P of Kb minus 0.6 is equal. How much is going to be? It's going to be 8.5, I believe, right? So P of Kb has to be equal 9.1. Perfect. So what is P of Kb basically? P stands for minus log. Minus log of Kb is coming out to be 9.1. Perfect. It's coming out to be minus 9.1. Right? So you can write the answer like this. Log of Kb is equal to minus 9.1. Let's say the answer is given in terms like this. So Kb should be equal to 10 raised power minus 9.1. This can be the answer which can be mentioned, right? Or if you want to use the anti-log, you can use the anti-log as well. You can use the anti-log as well, right? Perfect. Perfect, guys. Is that clear? Is that clear? Let me know once in the chat quickly. Sir, English mat karo, please. Bro, this is the English channel. English channel है ये. यहाँ पे अंग्रेजी में ही बात होती है. Quickly, people. All the things are clear? Perfect. So there are a few more types of questions which can be asked from salt hydrolysis, but those questions we can only solve once we get to know, first of all, what buffers are. First, we have to understand buffer. Once we understand buffer, once we get certain results, then there can be some other questions in which buffer is related to salt hydrolysis. Those are some good questions basically, right? In which majority of the students make mistakes, right? But again, this part also will be doing from the basics itself. Now tell me once in the chats if every single thing is clear till here, quickly. Quickly. Quickly, people, everyone. All right, so let's get to know exactly what buffer solutions are. Let me show you the definition. Then I'll make you understand what these buffers exactly are. Buffer solutions, let me tell you, these are special type of solutions. These are some special type of solutions whose pH does not significantly change on adding small amount of acid or base into it. These are some special type of solutions in which pH does not significantly change upon the addition of small amount of acid or a base. So what do? They resist, they show resistance towards the change in pH. They show resistance towards the change in pH. Why they show resistance towards the change in pH? Why their pH does not significantly change on adding small amount of acid or base? You'll get the idea in some time. Why it happens? You'll get the idea, right? First, try to understand this particular definition. So what is the buffer solution? Buffer solution is the one which shows the resistance towards the change in pH. Buffer solution is the one whose pH does not significantly change upon the addition of small amount of acid or base into it, right? Now, before making you understand why exactly it happens, let me first of all tell you what are the different types of buffers. Well, we have got two types of buffers basically in our syllabus which we have to study. One is simple buffer, one is mixed buffer. Simple buffer, it is made up of a single substance. It is made up of a single substance. For example, you have got a salt of weak acid and weak base. If you take a salt of weak acid and weak base in the container, it can behave like a buffer. It will behave like a buffer. If you take a salt of weak acid and weak base, for example, you have got CH3COONH4. This is the salt of weak acid and weak base. If you put it in a container, right, you'll find its pH won't significantly change upon the addition of small amount of acid or base, right? So it's behaving like a buffer. There are mixed buffers too. What are mixed buffers? Mixed buffers, they are the mixture of two substances basically. What is simple buffer? Simple buffer is made up of only single substance. There's a single substance which behaves like a buffer. But mixed buffers, these are made up of two substances. There'll be two substances present in the container, right? And these mixed buffers, we classify them into acidic buffer and basic buffer. And this acidic and basic buffer we have to study in detail basically, right? So let's try to understand what this acidic buffer is, what the basic buffer is, and how they exactly work. This is actually something which is in our NEET syllabus, right? Nothing apart from this can be asked. So first of all, acidic buffer, how it is made up of. Acidic buffer, it is made up of weak acid and the salt of same weak acid with a strong base. For example, you have got CH3COH. It's a weak acid, right? What the CH3CON is, it is the salt of same weak acid which it has formed with strong base, right? It is the salt of same weak acid which it has formed with strong base NaOH, right? So whenever you find weak acid and the salt of same weak acid which it has formed with a strong base in the same container, you'll be calling it as the acidic buffer. Similarly, what is the basic buffer? Basic buffer, whenever you have a weak base and the salt of same weak base which it has formed with a strong acid in the same container, you'll be calling this particular mixture as the basic buffer. So what is acidic buffer? What is basic buffer? Acidic buffer, weak acid and the salt of same weak acid with a strong base. Basic buffer, weak base and the salt of same weak base with a strong acid, right? So first of all, you need to identify, you should be able to identify which one is your acidic buffer and which one is your basic buffer, right? Now let's try to understand how these buffers exactly work. Try to understand. First of all, imagine that in the container, you have got a weak acid and this is the salt of same weak acid with a strong base. So should I be calling it as acidic buffer? Absolutely, I should be calling this as the acidic buffer. Now try to understand. CH3COH, it's a weak acid. If CH3COH is a weak acid, can I say it's going to remain in equilibrium with its ions, and its ions are CH3CO negative, and with that you get H positives, right? This is the weak base, which is in equilibrium, for example, with the ions. Let's say its concentration is C. This is 0. This is 0. Let's say its degree of ionization is alpha. So this is C minus C alpha. This has to be C alpha. Even this has to be C alpha. This is something which we all know already. Now, in the same container, we are adding CH3COONA. We are adding CH3CONA, which is a salt. And this particular salt, it will completely get dissociated into its ions. Its ions will be CH3CO negative, and with that you'll be getting Na positive, right? In the same container, you are introducing a salt. Let's assume its concentration is C1. This is 0. This is 0. Now this is a salt. It will get 100% dissociated. So this will be 0. This will be C1. This will be C1. Now you tell me one thing. There was a concept which I discussed with you in the last session. That was common ion effect. My dear students, do you see one thing? In the same container, we have got weak electrolyte and a strong electrolyte present in the same container. Both are having one ion in common. Which effect is going to operate here? Common ion effect is going to operate. And because of common ion effect, what is going to happen? This reaction shifts in the backward direction, due to which alpha value will decrease. And that decrease in the value of alpha, is something which you call as common ion effect. Right? This is something which I'm damn sure you already know. Correct? So basically, this is something which is happening in the container. This is something which is happening in the container. Now, imagine, my dear students, you are adding some small amount of acid into it. Imagine that you're adding some small amount of acid into it. You're adding some small amount of acid into it, right? You're adding H positives. For example, just to make you understand, let's imagine that, let's assume that you are adding 10 H positive ions. If you're adding H positives in the container, can I say strength of acid should increase? Because you're adding some extra H positives, 10 H positives in the container, for example. So strength of acidic strength of the solution should increase, right? Right? Or I can say pH of the solution, pH of the resulting mixture, it should decrease because you're adding 10 H positives. But what exactly happens when you're adding H positives? Already this particular reaction was in equilibrium. Already this particular reaction is in equilibrium, right? Now, when you're adding H positives, what will Chatelier principle do? You're adding acid. That means you're increasing H positives. If you're increasing H positives, equilibrium will shift in such a direction which will neglect the effect of change. Equilibrium will shift in such a direction which will nullify the effect of change. I hope you remember that. Since you're adding small amount of acid into it, but at the same time, this equilibrium will shift in such a direction in which the concentration of H positive will decrease. You're adding H positives, but equilibrium will try to decrease the H positives. How equilibrium will try to decrease the H positives? When it will make the reaction to move in the backward direction. It is further making sure the reaction moves in the backward direction. And when the reaction moves in the backward direction, CH3CO negative is reacting with H positive and making again CH3COH. So concentration of H positives is decreasing. No doubt you have added 10 H positives, but understand and imagine, for example, out of those 10 H positives, 9 H positives reacted with CH3CO negative and formed CH3COH. So effectively, no doubt you have added 10 H positives, but effectively there is increase of only 1 H positive. All the 9 H positives they participated in the backward reaction, right? Effectively, there will be the effect of only 1 H positive increase. So I had expected that I'll decrease the pH. I had expected that I'll decrease the pH by adding 10 H positives. But the effect of 10 H positives is not considered here. The effect of only 1 H positive is considered here, right? So what is going to happen? What is going to happen? We were expecting, for example, the pH will decrease by 2 units by the addition of 10 H positives. But effectively, there is only increase of 1 H positive. So will the pH decrease by 2? No. For example, the pH decreases by 0.1 only, right? So can you see this particular solution? Its pH is not significantly changing upon the addition of small amount of base into it, right? So can you see this particular mixture, it is showing resistance towards the change in pH? Any such solution which shows resistance towards the change in pH, that's something which we call as buffer solution. So this is how this buffer exactly works. I hope you got it, right? We were expecting the pH should decrease by 2 units by the addition of 10 H positives. But effectively, there is not the addition of 10 H positives. Effectively, there is the addition of 1 H positive only, effectively, right? So pH won't be decreasing by that amount which we expected. No, right? That particular solution in which pH does not change significantly upon the addition of small amount of base or acid into it. That's something which we call as buffer. So it is working like a buffer. Yeah. So I hope you exactly got to know how this buffer exactly works, right? Similarly, you can see the addition of base also, right? By the addition of base, what will happen? Say by the addition of base, that means you are adding OH negatives. When you'll be adding OH negatives, so OH negatives will start reacting with H positives, right? They'll lead to the formation of water. So H positive concentration will decrease, but equilibrium will again try to increase H positive concentrations. Perfect. It will make sure the reaction moves in the forward direction. So basically, whatever you expect, that exactly does not happen. Okay, so in short, buffer is the one which shows resistance towards the change in pH. Perfect. Now guys, there is one result which I would want you guys to remember directly. How do you calculate pH of the buffer? pH of the buffer, it is P of Ka plus log of concentration of salt divided by concentration of conjugate base. P of K plus log of concentration of conjugate base divided by concentration of acid, right? Or you can directly write as log of concentration of salt divided by concentration of acid, right? You can remember this particular result. I'll show you its application in some time. First of all, remember this. This is how you calculate pH of the acidic buffer. Similarly, if you have the basic buffer, how do you calculate pOH? You do not calculate pH of the basic buffer directly. You first calculate pOH of the basic buffer. pKb plus log of concentration of salt divided by concentration of base. This is how you calculate pOH. Once you get the pOH, then you can calculate pH by the formula pH plus pOH is equal to 14, right? Now I'm going to solve certain questions so that you can understand what kind of questions are asked out of this. Hey guys, I'll be starting with a basic question, with a complete basic question. Calculate the pH of 1 liter solution containing 0.01 molar CH3COH. So basically in the container you have got CH3COH and CH3COONA. The concentration of CH3COH, it is 0.01 molar. The concentration of CH3COONA, it is 0.02 molar. So can I say in this particular container, what do we have? We have got a weak acid and the salt of same weak acid. The salt of same weak acid with a strong base. So should I say that we have got the acidic buffer in the solution? I mean in the container? Absolutely, we have got acidic buffer. How do you calculate pH of the acidic buffer? pH of the acidic buffer is equal to P of Ka plus I'll write log of concentration of salt divided by concentration of acid. It is basically concentration of conjugate base, actual, right? Divided by concentration of acid. So it is pH is equal to P of Ka. P of this value is 4.74, you already know that, plus log of concentration of salt. Salt concentration is 0.02 molar. Divided by acid concentration is 0.01 molar. So it's 4.74 plus it's going to be log of 2. Log of 2 is 0.3. So the value is going to be 5.04. So 5.04 is going to be the pH of the final solution. Right? Is this clear to everyone quickly? Did you exactly get to know how to tackle with these sort of questions? And this was the basic question. Now slowly you'll get to know the level of the questions. I hope this is clear. Let's try to solve few more questions. Look at this particular question, guys. Try to understand what the question says. Calculate the pH of the solution obtained on mixing 100 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. So as per this particular question is concerned, you are making CH3COOH to react with NaOH, right? You are putting these two acids and base in the same container. So what is going to happen? CH3COH, when it reacts with NaOH, it leads to the formation of what? It leads to the formation of CH3CONA, and with that you'll be getting water. Try to understand. It's a good question and simple at the same time. At time t is equal to 0, if I ask you, how many millimoles of CH3COH are there in the container? See, molarity of CH3COH, volume of CH3COH, both are given. And you know, molarity multiplied by volume in ml, that gives me the millimoles. So millimoles of CH3COH will be 0.1 into 100. That means 10. So you have got 10 millimoles of CH3COH in the container initially. Now tell me how many millimoles of NaOH do we have? Molarity multiplied by volume. So we have got 10 millimoles of NaOH as well. So this has to be 0. This has to be 0. Now, my dear students, if you remember in mole concept, I have told you, whenever you are given with the amounts of all the reactants, which concept do we use? We use the concept of limiting reagent basically, right? Now we use the concept of limiting reagent. Balance the reaction first, which is already balanced. Identify the limiting reagent. 10 by 1, 10 by 1. Both are getting the same value. So both will be completely neutralized. So I'll be left with nothing of this. I'll be left with nothing of this as well. Now take 1 as the reference and get the product formed. 1 mole gives 1 mole. So from 10 millimoles, you get 10 millimoles. So from 10 millimoles, you get 10 millimoles. Now you tell me, since you introduced acid and base in the container, now you tell me after the reaction is complete, what are we left with in the container? In the container, there is no acid left. There is no base left. There is only salt and water left. In the resulting solution, finally in the container, there is salt and water left. And you know, salt and water, what they do? They'll do the salt hydrolysis, right? They'll do the salt hydrolysis. Now imagine and understand which salt this is. This is the salt of weak acid and strong base. So salt of weak acid and strong base will undergo hydrolysis, right? And how do you calculate the pH? When salt of weak acid and strong base undergoes hydrolysis, how do you calculate pH? It is 7 plus half of. It is P of Ka plus log of C, right? So it's going to be 7 plus half of P of Ka. P of Ka. P of Ka value is equal to 4.74 plus log of C. C is the concentration of salt. C is the concentration of salt. Well, I just know the millimoles of salt. So millimoles of salt divided by total volume in ml. Total volume is 200, right? So 10 millimoles of the salt divided by total volume in ml. That gives me the concentration. Now it is just a matter of calculation. Just a matter of calculation and get the pH of the final solution. Did you get to know how did we deal with this particular question? So first of all, we understood at the end of the reaction what is left in the container. Accordingly, we applied the formula. Accordingly, we applied the formula. Yes? Perfectly done. Perfect, guys. Let's try to solve a few more questions so that you can understand it properly. By the way, after solving this equation, you'll get the answer as 8.72. Let's try to solve a few more. Calculate the pH of the solution obtained on mixing this and this. Okay. Now, again, in this question, we are making CH3COH to react with NaOH. And you know, when CH3COH reacts with NaOH, it leads to the formation of CH3CONa, and with that, you'll be getting water. With that, you'll be getting water. This has to be the reaction, first of all, right? Now, tell me initially, how many millimoles of CH3COH we have? Since we know its molarity, we know its volume. Molarity multiplied by volume in ml, it gives me the millimoles. So, millimoles of CH3COH we already have. How many millimoles of NaOH do we have? Molarity multiplied by volume in ml. So, 5 millimoles of NaOH we have. So this will be 0. This will be 0, right? Now, again, I'll be using the concept of limiting reagent to get to know that after the reaction is done, what is left in the container. Now, first of all, identify the limiting reagent. 10 by 1 is 10, 5 by 1 is 5. The one which gets the lesser value, that has to be the limiting reagent. So, NaOH is the limiting reagent. So, it will be completely consumed, right? Now, 1 mole reacts with 1 mole. 5 millimoles would have reacted with 5 millimoles of it. I had started with 10 millimoles. Out of 10, 5 are reacting. So I'll be left with 5 millimoles of weak acid as well. At the end of the reaction, 5 millimoles of CH3COH will be also left. Now, 1 mole gives 1 mole. So from 5 millimoles, you'll be getting 5 millimoles. Even this will be 5 millimoles. Now, finally check it out. Finally check it out. What is left in the container? Finally check it out. Check it out. What all things are left in the container? Are we left with a base? No, it's consumed. We are left with some millimoles of weak acid, and this is the salt which is there in the container. And there is water as well. There is water as well. Now, my dear students, which salt we are left with? We are left with weak acid. Sorry, which acid we are left? We are left with weak acid. So there is weak acid in the container. There is salt as well. Which salt it is? It is the salt of weak acid which it has formed with a strong base. So can I say this weak acid and its salt with a strong base, they'll be leading to the formation of acidic buffer, right? Acidic buffer. Now at the same time, salt plus water, they can show salt hydrolysis. Whenever you'll be stuck, which formula to use, whether to use the buffer formula or salt hydrolysis formula, you'll be always giving priority to buffer. You'll be giving priority to buffer. Okay? You'll be giving priority whenever there'll be confusion, right? Whether to use buffer formula or salt hydrolysis formula, you'll be always giving preference to buffer, right? So how do I calculate pH? I'll be using the buffer formula. pH will be equal to P of Ka plus log of concentration of salt divided by concentration of acid, right? P of Ka already you know that's 4.74 plus log of concentration of salt. Concentration of salt will be millimoles of salt divided by total volume. Total volume is 100 plus 50, 150. This is the concentration of salt divided by concentration of acid. Millimoles of acid divided by total volume. So this whole term is 1, log of 1 is 0. The final answer is 4.74. So 4.74 is the pH of the final solution, which we were supposed to calculate, right? Is it clear? Is it clear, guys? Quickly. Yes. Let me solve one more question. Look at this particular question. Say exactly how you guys are going to solve this. Calculate the pH of the solution obtained on mixing 50 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. I'm just changing the data in the questions. I'm just changing the data. Rest everything is same. So again, your CH3COH is reacting with NaOH, and it will lead to the formation of what? CH3CONa, and with that you're writing water as well. Correct? Now, initially at time t is equal to 0, how many millimoles of CH3COH we have? Molarity multiplied by volume in ml. So we have got 5 millimoles of this acid. How many millimoles of NaOH we have? We have got 10 millimoles of NaOH. So this has to be 0, even this has to be 0. Right? Now, which one is the limiting reagent among the two? It is CH3COH. It will be completely consumed. How many millimoles of NaOH will be left? 1 mole reacts with 1 mole. So 5 millimoles will react with 5 millimoles. I had taken 10. Out of 10, 5 are reacting. So 5 will be left. So 5 millimoles of NaOH are still left in the container. Now, 1 mole gives 1 mole. So 5 millimoles are going to give 5 millimoles. Similarly, this will be 5 millimoles. Perfect. Now tell me one thing. What all things are left in the container? What all things are left in the container? You're not left with the acid. Acid is done and dusted. There is a strong base left in the container. There is a salt left in the container. There is water also formed in the container, right? Now, this and this, they will lead to the formation of salt hydrolysis. This and this, should I be calling this as basic buffer? You won't be calling it as basic buffer. No, you're writing wrong. It is not a basic buffer. Basic buffer means weak base and it's salt with strong acid. This is not weak base. It's a strong base. It's not a basic buffer, right? Do remember one thing. First, just to make sure you do all the questions correctly. Whenever you get confused whether to use salt hydrolysis formula or buffer formula, you'll be giving priority to buffer. Number 1. Number 2, between salt hydrolysis and strong acid, left, you'll be giving priority to strong acid. Salt hydrolysis and strong base, give priority to strong base. Okay. Now, these two, hydrolysis, and there's a strong base. There's a strong base, right? So which one to prioritize? So should I give priority to salt hydrolysis or strong base? I'll give priority to strong base. So strong base is going to decide the pH of the resulting solution. So which strong base is left in the container? NaOH. This strong base left in the container, it would have got dissociated further as Na positive plus OH negative, right? How many millimoles of NaOH are left? 5. This will be 0, this will be 0. This will be 0, this will be 5, this will be 5. So tell me the total millimoles of OH negative which are left in the container. Total millimoles of OH negative which are left in the container are 5. So if I ask you, what will be the concentration of total OH negatives present in the container? Millimoles of OH negative divided by total volume. So 1 by 30. So this is the concentration of OH negative present in the container. So calculate POH. P stands for minus log of OH, minus log of 1 by 30. Solve it, get the POH. Once you get the POH, then you can get the pH as well, which is 14 minus POH. Right? Perfect. Clear, guys? Again, these sort of questions, you can try it out with the help of this particular question. This is one more question, which is your homework question. This is not basically one question. These are 2 questions. These are 2 questions. Try them the similar way. The way I solve the question, in the similar way, you guys are going to solve them, right? You have to check basically what is left in the container. Whether you have to use the buffer formula, whether you have to use the hydrolysis formula, whether you have to give priority to strong acid, whether you have to give priority to strong base, right? So that's why I'm giving you this homework question. You guys are going to try it out. Okay. Now, guys, there is one more small topic, that is buffer capacity, which is represented by phi. How do you define the buffer capacity? How do you define the buffer capacity? It is defined as number of moles of H positive or number of moles of OH negative. Number of moles of H positive or number of moles of OH negative added per liter of buffer. Just a second. Let me write it like this. Number of moles of H positive or number of moles of OH negative added to 1 liter of buffer. Added to 1 liter of buffer divided by change in pH. This is the simple result by means of which we can calculate buffer capacity. Now you must be thinking how this particular result is to be used. I'll be giving you one question. Just a second. Just a second, guys. I'll be giving you one question on this so that you can understand what kind of question can be asked out of this. One simple question I'll give you and you will understand all these things in detail. Which question should I give you? Okay, one small question I'm giving you. The question is like this. 0.4 grams of NaOH. 0.4 grams of NaOH when added to 200 ml of buffer. When added to 200 ml of buffer solution, increases the pH by 0.01. Calculate the buffer capacity. Basically, buffer capacity, it gives us the idea about the efficiency of the buffer. More the buffer capacity, lesser will be the change in pH. Right? More the buffer capacity, more is the efficiency of the buffer. More is the efficiency of the buffer. What is meant by the term more is the efficiency of the buffer? What is meant by the term more efficiency of the buffer? Quickly. What is meant by the term more efficiency of the buffer? What does buffer do? It shows resistance. More efficiency of the buffer means more resistance towards the change in pH. More resistance towards the change in pH. Right? Okay. So let's try to solve this one. Buffer capacity is equal to number of moles of H positive or OH negative added per liter of the buffer divided by change in pH. Just tell me one thing. You are adding 0.4 grams of NaOH. Can you let me know how many moles of NaOH you are adding? Mass of NaOH divided by molar mass of NaOH, right? So it's going to be 4 divided by 400, 1 by 100, 10 raised per minus 2. So these many moles of NaOH you are adding. These many moles of NaOH you are adding. So if you are adding these many moles of NaOH, can you let me know how many moles of OH negative you are adding? So basically you are adding same moles of OH negative, right? Because NaOH, it dissociates as Na positive plus OH negative. 1:1:1 stoichiometry, right? So these many moles of OH negative you are adding. But you are adding these many moles of OH negative to 200 ml of buffer. So can I say in 200 ml of buffer, we are adding 10 raised per minus 2 moles of OH negative. So in 1 ml of buffer, we are basically adding 10 raised per minus 2 divided by 200 moles of OH negative. So to 1000 ml of buffer, we'll be adding 10 raised per minus 2 divided by 200 multiplied by 1000. So it will be 5 into 10 raised per minus 2, right? So these many moles of OH negative basically we are adding. These many moles of OH negative we are adding to 1 liter of buffer, right? That's what we have to calculate. Moles of OH negative or H positive added to 1 liter of buffer. So we got to know towards 1 liter of buffer, we are adding 5 into 10 raised per minus 2 moles of OH negative divided by change in pH. Change in pH is 0.01, 10 raised per minus 2. So the buffer capacity came out to be 5. Done and dusted, right? Simple. Clear, guys? One more question I'm going to give you, and let me see if you can solve that or not. The question is 100 ml of 0.1 molar solution of KOH is added to 200 ml of buffer. Is added to 200 ml of buffer. Change what? Change the pH. Change the pH from 4.2 to 4.4. Calculate the buffer capacity phi. Give it a try. You should be able to solve this sort of equation as well. It's again simple, guys. Have a look. As per the question, you are adding KOH, whose molarity is this, volume is this, right? So if I ask you how many millimoles of KOH you are adding, molarity multiplied by volume in ml. So you are adding 10 millimoles of KOH. You are adding 10 millimoles of KOH. 10 millimoles of KOH. So if I ask you how many moles of KOH you are adding, so millimoles added divided by 1000. So it's 10 raised per minus 2. So these many moles of KOH you are adding. So if I ask you how many moles of OH negative you are adding, you'll directly say 10 raised per minus 2 moles of KOH we are adding, right? Because KOH dissociates as K positive plus OH negative, 1:1:1 stoichiometry. So these many moles of OH negative you are adding to 200 ml of buffer solution. So towards 200 ml of buffer solution, you are adding 10 raised per minus 2 moles of OH negative. So in 1 ml of buffer, you are adding 10 raised per minus 2 divided by 200 moles of OH negative. So towards 1000 ml of buffer, you are adding 10 raised per minus 2 divided by 200 multiplied by 1000. The value will be again 5 into 10 raised per minus 2. So these many moles of OH negative basically you are adding to the buffer. These many moles of OH negative you are adding to 1000 ml of buffer. You are adding to 1 liter of buffer. So calculate the buffer capacity. Number of moles of H positive or OH negative added to 1 liter of buffer. So in 1 liter of buffer, how many moles of OH negative you are adding? 5 into 10 raised per minus 2 divided by change in pH, final minus initial. It will be 0.2, right? 0.2 means 2 into 10 raised per minus 1. 2 into 10 raised per minus 1. So it's going to be 2.5 multiplied by 10 raised per minus 1. The value will be 0.25. So 0.25 is the buffer capacity of the buffer. Is this clear to everyone quickly? Is this clear to everyone quickly? Let me know once in the chats. Yeah? So my dear students, I'm sure that you can easily solve questions based on buffer from now onwards, right? Do you want me to solve this particular question, or will you be able to solve this question on your own? The question which I gave you as the homework, will you be able to solve this? Or you want my help in this? Do you want me to solve this question or not? I want everyone to say it. Okay, this is your homework question. Give it a try, right? If not, then do let me know in the Telegram. Okay. Now, there is one last topic that is left. What is that? That is solubility. This is the last topic of ionic equilibrium, right? It is again one simple topic. Now, first of all, what is solubility? What is solubility product? And what kind of questions can be asked from this one as well? It's again simple. Again, I'm telling you. How do you define the term solubility? Let me first of all tell you, the solubility, it's represented by S, right? It is represented by S, number one. Number two, the solubility is expressed in moles per liter. Now, what is solubility? As per the definition, it is defined as the maximum moles of solute which can be dissolved in a solution. The maximum moles of solute per liter that can be dissolved in a solution. Now, what does that mean? What does that mean? Let's try to understand what this solubility is. My dear students, for example, just to make you understand, for example, you have got water in this container. Just to make you understand, you have got, for example, water in this container, for example, right? Do you know between the water molecules there are basically some vacant spaces present? Absolutely. Between the water molecules there will be some vacant spaces present. Now, for example, you are adding some salt in it. Let's say you're adding some salt in it. You're adding some solute in it, right? Let's say you're adding NaCl into it. Now, this NaCl which goes into the water, where does it go? Where does it go? First of all, the NaCl which goes into the water, it tries to fill the spaces between the water molecules. It tries to fill the spaces between the water molecules, right? And whatever NaCl goes in the spaces, first of all, when this NaCl goes into water, it dissociates in the form of Na positive plus Cl negative. So these are basically Na positives and Cl negatives which go into the spaces between the water molecules, right? The maximum moles of solute added, the maximum moles of solute that can be dissolved in 1 liter of solution. The maximum moles of solute dissolved per liter of solution, that defines solubility. For example, if I say the solubility of the salt is 5 moles per liter, what does it mean? That means in 1 liter of solution, there are 5 moles of solute present. There are 5 moles of solute present. In 1 liter of solution, there are 5 moles of solute present, right? Perfect. If I say solubility of the salt is 10 moles per liter, what does that mean? That means in 1 liter of solution, there are 10 moles of solute present. There are 10 moles of solute present, right? I hope you got the idea of what the solubility is. Maximum moles of solute, maximum moles per liter which can be dissolved in the solution. That defines the solubility of the solution. Now, there are few things which you need to know. That salt whose solubility is greater than 0.1 molar, you call that particular salt as the soluble salt, right? That particular salt whose solubility is between 0.01 to 0.1, you call that as the slightly soluble salt. And that particular salt whose solubility is less than 0.01 molar, you call that as the sparingly soluble salt. Sparingly soluble salt, right? So based on solubility, we classify salts into 3 types. One is soluble salt, slightly soluble salt, and sparingly soluble salt. And in this particular topic, we have to deal with the sparingly soluble salts, right? We have to deal with the sparingly soluble salts. Now try to understand few things what I'm going to say. There are 2 statements which are mentioned. My dear students, a sparingly soluble salt will be considered as a weak electrolyte. A sparingly soluble salt whose solubility is less than 0.01 molar, that will be considered as a weak electrolyte, and we are always going to keep it in equilibrium with its ions. Point number 1. Point number 2, this point is important, and try to understand this particular point what I'm saying. For example, you have got a salt AB. You have got the salt AB, right? This is A positive aqueous, and this is, for example, B negative aqueous. Try to understand exactly what I'm going to say. In the saturated solution, the concentration of ions represent the solubility of a sparingly soluble salt. First of all, what is the saturated solution? Saturated solution is the one in which furthermore salt cannot be dissolved, because all the spaces between the water molecules would be occupied, right? That is the saturated solution in which all the spaces are covered between the water molecules. For example, you have got water in this container, and you are going to introduce AB solid in this water, right? Let's assume that this water in the container, let's assume there are definitely spaces in between water molecules, and these spaces can accommodate maximum of 5 moles of salt. These spaces between the water molecules, let's assume that they can accommodate maximum of 5 moles of salt, right? So for example, if I'm introducing 10 moles of AB in this container, out of 10 moles between the spaces, only 5 moles can be accommodated. And those 5 moles which are going to get accommodated between the spaces, those 5 moles will be present in the form of ions, right? Those 5 moles will be present in the form of ions. So at this point, should I say the solubility of the salt is 5 moles per liter, or should I say it is 10 moles per liter? The solubility is 10 moles per liter, right? No doubt you're introducing 10. Out of 10, 5 moles are adjusted in the spaces in the form of ions. Right? The remaining 5 moles, they are going to settle at the bottom only. The remaining 5 moles, they'll be present at the bottom only. As simple as that. Now, 5 moles per liter. 5 moles per liter. So, this much amount of salt, these 5 moles amount of salt, it will be present in the spaces in the form of ions. Now tell me, 1 mole of AB would have given 1 mole of A positive. So 5 moles would have given 5 moles of A positive. Similarly, 5 moles of B negative will be present in the solution, will be present in the spaces, right? So can I say whatever is the solubility of the salt? In this particular case, whatever is the solubility of the salt? Solubility of the salt is 5 moles per liter. Same is the concentration of ions here. Same is the concentration of ions in the solution, right? So do remember this particular thing. In a saturated solution, the concentration of ions is 5 moles per liter. That is actually the solubility here, right? So concentration of ions, they represent the solubility of sparingly soluble salt. So I had taken a sparingly soluble salt whose solubility, for example, is S. If the solubility is S, then this has to be S, this has to be S. So, and the units are going to be moles per liter. Units are going to be moles per liter only. Right? So the concentration of these ions, they represent basically, what do they represent? They represent the solubility of the sparingly soluble salt. Yeah? Perfect. Is that clear? You got the idea? Let's say the solubility of the salt is 10 moles per liter. That means 10 moles of the salt will be present in the solution, that too between the spaces between the solvent molecules in the form of ions. Let me know honestly in the chats whether you got this particular concept or not. Then only I can move ahead. Then only I can move ahead. My dear students, try to understand. Try to understand one thing. Let's say you are taking a saturated solution of AB solid, right? AB solid. You are taking a saturated solution of AB solid, right? Let's assume its solubility is S moles per liter. Its solubility is S moles per liter. That means S moles of salt is present in the solution, in the form of ions. Now tell me the concentration of ions. Tell me how many moles of A positive and B negative will be in the solution, in the spaces. Use the stoichiometry. 1 mole gives 1 mole. So from S moles, you'll be getting S moles. This will be also S moles. This is something that's understood, right? Perfect. My dear students, if I write the expression of equilibrium constant over here, expression of equilibrium constant will be concentration of A positive at equilibrium raised power 1, concentration of B negative at equilibrium raised power 1 divided by concentration of AB solid. Correct? Now this is a constant, this is a constant. So KEQ multiplied by AB, multiplied by concentration of AB. It's going to be concentration of A positive multiplied by concentration of B negative. And these are the concentrations at equilibrium. So basically the salt and its ions, they are present at equilibrium, right? In the saturated solution. They'll be at equilibrium basically. So these are the concentrations at equilibrium. These are the concentrations at equilibrium. Now tell me one thing. This is constant, this is constant. Multiplication of these constants makes it new constant. That is what you call as KSP. So how do you write the expression for KSP? Concentration of A positive at equilibrium, concentration of B negative at equilibrium, raised to the powers of the stoichiometric coefficients. Right? Raised to the powers of the stoichiometric coefficient. This KSP is something which you call a solubility product. This is what you call as solubility product. Right? This is what you call a solubility product. Perfect. This is what you call a solubility product. Now, I'm going to show you exactly how do you write the expression of solubility product for different types of salts. Let's get to know about that. Rina, there will be no break. This chapter will be ended in just half an hour more. Just be with me for half an hour, that's all. The chapter will be ended. Right? Okay? So how do you write the expression for KSP? In order to write the expression of KSP, you just need the concentration of products. You do not need the concentration of reactant. Yeah? You do not need the concentration of reactant. Okay. For example, have a look. Have a look. This is a salt AB, which is in equilibrium with its ions. In the solution, this AB salt is in equilibrium with its ions. Right? AB salt is in equilibrium with its ions. Now try to understand. Do you understand why this equilibrium sign is in between? Any one of you has thought why this equilibrium sign is in between? So basically, let me make you understand this in this simpler way. Try to understand. See, this was water in the container. Let me just make you quickly understand this. Why this equilibrium size is in between. See guys, let's say this is water in the container. This water can accommodate maximum of 5 moles of salt. 5 moles of salt. I am introducing 10 moles of salt. 10 moles of AB. Out of 10 moles of AB, 5 moles will be adjusted between the spaces, and the remaining 5 moles of AB, remaining 5 moles of AB salt will be there in the container at the bottom. These are the 5 moles which are present at the bottom, and the rest of the 5 moles are present in the solution in the form of ions, right? So at the bottom you have got AB solid. In the solution there are A positives and B negatives, because whatever salt is there in the solution, that salt is in the form of ions, right? So at the bottom you have got AB solid, and in the solution you have got A positives and B negatives, right? Roaming around. Now for example, if one, or let me tell you one thing like this. If for example, one A positive and one B negative, if they interact in the solution, they will lead to the formation of AB solid. But at the same time, one more molecule of AB solid will come out from the bottom and will go into the solution in the form of ions. So these two, they'll be in equilibrium with each other. These two, basically, they'll be in equilibrium with each other, right? So A positive, B negative, they are in the solution. AB solid is at the bottom. So by chance, if one A particle, one A positive, one B negative, if they interact, they lead to the formation of AB, and that AB will settle down. At the same time, from the bottom, AB, one of the AB will dissociate into the ions, so that the equilibrium is maintained between the two. Now, leaving this part aside, leave it aside. Now try to understand what I'm going to say. Tell me one thing. Let's assume the solubility of this salt is S moles per liter. S moles per liter is the solubility of the salt. Now, what will be the solubility of A? What will be the concentration of A positive? S moles per liter. B negative? S moles per liter. Now, if I ask you to write KSP expression is simply going to be concentration of A positive at equilibrium, that's S raised power stoichiometric coefficient. Concentration of B negative at equilibrium, that's S raised power stoichiometric coefficient. So KSP expression is going to be S square here, right? KSP expression is going to be S square here, right? KSP expression is S square. For example, you have got the salt in this format. AB2 solid, it gives A dye positive plus 2 times B negative. This is how it's going to get dissociated. Let's assume its solubility is S. This will be S. This will be 2 times S. Because 1 mole gives 2 moles. From S, you get 2S, right? So this S, this is the concentration of A dye positive in the solution. And this 2S, it is the concentration of B negative in the solution. Try to write the expression for KSP. KSP expression is concentration of A dye positive raised power stoichiometric coefficient, concentration of B negative raised power stoichiometric coefficient. So KSP has to be equal. Concentration of A dye positive is S, concentration of B negative is 2 times S raised power stoichiometric coefficient, and the value comes out to be 4S cube. This is the KSP expression for this particular type of salt AB2, right? Yeah? Perfect. I hope this is clear. And similarly, my dear students, let's try to understand this one. Let's assume that you have got one more type of salt, AB3. You have got one more type of salt, AB3. First of all, how it will undergo dissociation? It will undergo dissociation as A tri positive plus 3 times B negative, right? That's something which you all must be doing. Now, for example, its solubility is S moles per liter. So what is the concentration of A tri positive? 1 mole gives 1 mole. From S moles, you get S moles. 1 mole gives 3 moles. From S moles, you get 3S moles, right? So you got the concentration of these ions which will be present in the solution. Now write the expression for KSP. KSP expression will be equal. Concentration of A tri positive raised power stoichiometric coefficient, concentration of B negative raised power stoichiometric coefficient, right? So KSP expression has to be equal. This will be S, this will be 3 times S raised to the power 3. So it's going to be 3, 3, 9, 3, 27 S raised power 4. This is how you write the expression of KSP for this particular type of salt, right? Yeah? Perfect, guys. I hope this particular point is clear to you. Now, for example, let's say you have got the salt of this type, AXBY. If you do not know how to dissociate a salt, let me just show you quickly how do you dissociate the salt. First of all, just crisscross these two factors. So it is going to be, first of all, let me tell you one thing. The charge present on A will be plus Y. The charge present on B will be minus 6. Just crisscross to get the charges. Now, how many A particles do we have? We have got XA particles and A is present in the form of plus Y. Similarly, how many B we have? Y, and B is present in the form of minus 6. Let's assume its solubility is X. So this has to be X times S. This has to be Y times S. I hope this is clear. Try to write the expression of KSP. KSP expression is equal to concentration of A plus Y raised to power stoichiometric coefficient X. Concentration of B minus X raised to power stoichiometric coefficient Y. So KSP expression has to be equal to A plus Y concentration is X times S whole raised to power X. Concentration of B minus X is Y times S whole raised to power Y. So KSP has to be equal. It's going to be X raised to power X, Y raised to power Y, S raised to power X plus Y. So in general, this is how you write the expression for KSP. In general, this is how you write expression for KSP. Is this clear to everyone? Is this clear to everyone? Is it clear, people? I hope this particular concept is again clear to you. Now let's get to know what kind of questions can be asked out of these particular topics which I told you. Anyways, one more last example. Have a look. You have got A2B3. How do you dissociate it? A2B3. The way I told you a few minutes back. A2B3. How do you dissociate it? This 3 has to be the charge here. This 2 has to be the charge here. How many A particles you have? 2 A particles. The charge present on A is plus 3. How many B particles you have? 3. And the charge present on B is minus 2. This is how you are going to dissociate it, right? Perfect. Let's say its solubility is S. So this has to be 2 times S. This has to be 3 times S. In short, now you can write the expression for KSP. Perfect. So let's try to solve some questions so that you can understand the types of the questions which can be asked. One basic question with which I'm starting with. Right? Have a look. As per the question, you are given with MgOH whole twice. MgOH whole twice. First of all, how this MgOH whole twice will get dissociated? It will get dissociated as Mg di positive aqueous plus 2 times OH negative aqueous. This is how it's going to get dissociated, right? Now, dear students, let's assume its solubility is S. This will be also S. This will be 2 times S. What is the expression for KSP? KSP expression will be S multiplied by 2S square, which will be 4S cube. You need to get the solubility. Solubility in water is going to be KSP divided by 4 whole raised to the power what? Whole raised to the power 1 by 3. So what is KSP? KSP value is 3.2 into 10 raised to the power minus 14 divided by 4. Whole raised to the power what? Whole raised to the power 1 by 3. So this value will be 0.8. 0.8 into 10 raised to the power minus 14 whole raised to the power 1 by 3, which can be written as 8 multiplied by 10 raised to the power minus 15 whole raised to the power 1 by 3. The value is going to be 2 into 10 raised to the power minus 5. Since you got the solubility, whose units you are going to write in moles per liter, right? So this is the solubility of MgOH whole twice in water, which we were supposed to calculate, right? Perfect. It's a simple and basic question. Let's move on to one more. My dear students, first of all, do remember Hg2Cl2, how it undergoes dissociation. It's a special case. It undergoes dissociation like this. Hg2 di positive plus 2 times Cl negative. This is how it will undergo dissociation in water. This is how it will undergo dissociation in water. As per the question, KSP of the salt is given. We have to calculate solubility. Let's assume its solubility is S. This is S. This is 2 times S. So if I want to write the expression for KSP, it is concentration of Hg2, that is S raised to power stoichiometric coefficient 1. This is 2S raised to power 2. So it's going to be 4S cube. So S you are supposed to calculate. So S has to be equal to KSP divided by 4 whole raised to power what? Whole raised to power 1 by 3. So what is KSP? KSP is 10.8 into 10 raised power minus 23 divided by 4 whole raised power what? Whole raised power 1 by 3. Perfect. Right? So this can be 108 divided by 4. 108 divided by 4 means 27. 27 into 10 raised power minus 24 it will be. Whole raised power 1 by 3. Right? So it is 3 multiplied by 10 raised power minus 8. And it's going to be moles per liter. This is how you get the solubility here. Yeah, this is how you get the solubility. Let me show you one more question so that you can understand it properly. Okay, understand one more type of the question here. The solubility of Ag2O3 in water is this much. What is its solubility in 0.01 molar Na2CO3? Till now, we were talking about solubility in water. Now, we have to calculate the solubility of Ag2CO3 in Na2CO3. In Na2CO3. First of all, Ag2CO3. Tell me how will it undergo dissociation? It will undergo dissociation as 2 times Ag positive, 2 times Ag positive plus CO3 dinegative, right? Let's assume its solubility is S. This has to be 2S. This has to be S. Now, as per the question, the solubility of Ag2CO3 in water, that's given. So S value is given. So try to get the KSP value first. KSP value will be 4S cube. So it's going to be 4 into 10 raised power minus 12. S is 1 in 10 raised power minus 3. So it's going to be 4 in 10 raised power minus 12. So this is KSP which you got. This KSP which you got. Then solubility of Ag2CO3 in water is given. So by that, I calculate KSP. Now, what is its solubility in 0.01 molar Na2CO3? Now, if you put the same Ag2CO3 in Na2CO3, this Na2CO3 will get completely dissociated as 2 times Na positive plus CO3 dinegative. Now, what about its concentration? Its concentration is 0.01 molar. This is 0, this is 0. It would have got dissociated completely. So, this is 0, this is 0.02, and this is 0.01 molar. Now, my dear students, in the same container, what do we have? In the same container, we have got a weak electrolyte and a strong electrolyte. And both are having one ion in common. So, which effect you are going to operate? You are going to operate common ion effect, due to which this particular reaction will shift in backward direction, due to which the solubility will decrease. And this decrease in the solubility is something which I'll be calling as common ion effect here. So, if I ask you what is the total common ion concentration? Common ion concentration is S plus 0.01. S plus 0.01. Assuming that S value is already less. Now, due to common ion effects, S value would have further suppressed, due to which S plus 0.01 makes it 0.01 molar. This is the concentration of common ion, CO3 dinegative now, right? Perfect. Now, guys, KSP. How do I write the expression for KSP? It is concentration of Ag positive raised power 2 multiplied by concentration of CO3 dinegative, which is equal to 4 into 10 raised power minus 12, right? So, Ag positive concentration you already know. That's 2 times S raised power 2. Perfect. Concentration of CO3 dinegative, that is 0.01. So, 10 raised power minus 2 is equal to 4 into 10 raised power minus 12, right? So, it's going to be 4S square 10 raised power minus 2, and this gets cancelled. So, it's going to be 4 into 10 raised power minus 10. So, 4 cancel. S will be equal to 10 raised power minus 5. It's going to be moles per liter. Now, if I ask you what is this S? This is the solubility of same Ag2CO3, but not in water. Not in water. This is the solubility of Ag2CO3 in Na2CO3. With the help of what? With the help of common ion effect, we calculated it, right? With the help of common ion effect, we calculated it. Perfect. Okay, one more question. Calculate the solubility of silver phosphate in milligrams per milliliter. It will be a lot of calculation calculated in moles per liter. Okay, first question in pure water. Second question in a solution that is 0.02 molar in AgNO3. So these are two questions. First of all, we have to calculate the solubility of silver phosphate, Ag3PO4. Ag3PO4. In water, how it undergoes dissociation. 3 times Ag positive aqueous plus PO4 trinegative aqueous, right? So I'm going to solve the first question. Solubility of silver phosphate in water. Let's assume this is S. So this has to be 3S. This has to be S. Write the KSP expression. KSP expression will be this raised power 3, S raised power 1. So it's going to be 27, 3, 3, 9, 3, 27, S raised power 4. KSP value is given to us as 2.7 into 10 raised power minus 23 divided by 27 whole raised power 1 by 4, and this is equal to S basically, right? So it will be 10 raised power minus 24 raised power 1 by 4, so that's 10 raised power minus 6. So 10 raised power minus 6 moles per liter is the solubility, right? When you solve it, it's going to come out as 10 raised power minus 6, because this will be 0.1, so it will be 10 raised power minus 24 into 1 by 4, 4146. 10 raised power minus 6 is the solubility. This is the solubility of silver phosphate in water. This is the solubility of silver phosphate in water. But my dear students, when I solve the same question, if I want to calculate the solubility of silver phosphate in AgNO3, what exactly I should do? Solubility of silver phosphate in AgNO3. What exactly should I do? Ag3PO4, I'm introducing in AgNO3. Now tell me how this AgNO3 will undergo dissociation. Ag positive plus NO3 negative, right? Its concentration is 0.02 molar. Initially this was 0, this was 0. 100% dissociation, so 0, 0.02, 0.02 molar. Now tell me one thing. Weak electrolyte, strong electrolyte, both are having one ion in common. Which effect will operate? Common ion effect. Due to which the solubility of this weak electrolyte will decrease, right? And eventually you can neglect solubility S. So what is the total common ion concentration? 3S and 0.02. So 3S plus 0.02. This is the total common ion concentration, which can be further written as only 0.02 because solubility is suppressed due to common ion effect, right? Yeah. Perfect. Now guys, try to understand one thing. Write the KSP expression again. KSP expression is going to be concentration of Ag positive raised power 3. So 0.02 raised power 3. Concentration of PO3 tri-negative raised power 1. So S raised power 1. KSP value that's given to me as 2.7 into 10 raised power minus 23 is equal. This will be, is the 0.02 only? Check it out. Yeah. This will be 0.02, matlab 2 into 10 raised power minus 2 whole raised power 3. So it's 8 into 10 raised power minus 6. 8 into 10 raised power minus 6. 8 into 10 raised power minus 6. 8 into 10 raised power minus 6 multiplied by S. So from here you can get the S value. It's 2.7 into 10 raised power minus 23 divided by 8 into 10 raised power minus 6. The answer will be again in moles per liter only. So this is the solubility of silver phosphate in what? In AgNO3. First you calculate the solubility of silver phosphate in water. Then you calculate the solubility of silver phosphate in AgNO3 with the help of what? With the help of common ion effect. Yes, these lectures are enough for mains as well. Yes, these are enough for JEE mains as well. Okay. Perfect, guys. All clear? All clear? One question I'm giving you as the homework. Let me see if you can solve this or not. One question as the homework. What is the solubility of FeOH whole twice in a buffer with pH 6.5. KSP for FeOH whole twice is equal to 8 into 10 raised power minus 16. This is the question, which is your homework question, and do give it a try, guys, right? So with this, your ionic equilibrium chapter is also done and dusted, right? Our next chapter will be, I think first we'll do the concentration terms. We are left with concentration terms, right? We did not finish concentration terms in mole concept. So we'll be doing the concentration terms on Saturday, and Saturday 6 p.m. it will be. Concentration terms in one shot. Concentration terms, molarity of dilution, molarity of mixing, molarity of reacting, non-reacting, acid bases, molarity of ions, every single thing. Molarity of ideal solutions, non-ideal solutions. All those things will be done on Saturday at 6 p.m. Perfect. Hint for this question. You need hint for this question? So as per this particular question, okay, let me give you the hint. First of all, tell me how this FeOH whole twice will undergo dissociation. It will go undergo dissociation as Fe di positive plus 2 times OH negative. Its solubility is S, this is 2 times S. Now we have to calculate the solubility of FeOH whole twice in a buffer whose pH is? The buffer whose pH is 6.5. If pH is 6.5, that means pOH will be 7.5. If pOH is 7.5, that means OH negative concentration is 10 raised power minus 7.5, right? So write the expression for KSP. KSP expression is concentration of Fe di positive, that's S, multiplied by concentration of OH negative, raised power 2. Concentration of OH negative already we got 10 raised power minus 7.5 raised power 2. So KSP has to be equal to S multiplied by 10 raised power minus 15. KSP value is given to us 8 into 10 raised power minus 16 divided by 10 raised power minus 15 is equal to S. So S value is coming out to be 8 into 10 raised power minus 1, or you can say 0.8 moles per liter. So this is the solubility. Clear? Clear? Now got it? It was supposed to be your question, but anyways. Hello, I give you one question as the homework in the buffer. You give that question a try. Okay, do let me know its answer. Perfect. Hello guys, with this our ionic equilibrium is also done.
Unacademy. Let's crack it.